This course is CS50's Introduction to Programming using a language called R, a popular language for statistical computing and graphics in data science and other domains. This course was developed by Carter Zenke and Dr. David J. Malin from Harvard University. You will learn to use RStudio, a popular integrated development environment. You will learn to represent real-world data with vectors, matrices, arrays, lists, and data frames. You'll also learn to filter data with conditions and apply functions and loops. You'll learn to write functions to modularize code and raise exceptions when something goes wrong. By the end of the course, you will learn to package, test, and share R code for others to use.
Hello world, this is CS50's Introduction to Programming with R, a popular language for statistical computing and graphics in data science and other domains. My name is David Malin.
And my name is Carter Zenke.
Whereas CS50, otherwise known as CS50X, focuses on computer science and programming more generally, this course, CS50R, is entirely focused on R. You can take CS50R before CS50X, during CS50X, or after CS50X.
In this course, we'll first explore how to represent data in this language called R, learning about structures for data, called vectors and data frames. We'll then graduate to transforming data, in particular, filtering with these things called logical expressions that you can use to analyze subsets of data that you have. We'll then consider how to transform our data using functions and loops, and we'll introduce paradigms like functional programming. From there, we'll stand on the shoulders of those who've written R code before us, all in the pursuit of tidying our data and making it easier to analyze. Then, once our data is tidy, we'll be able to visualize it more easily too. Toward the end of the course, we'll test our programs to ensure they behave as we intend, and once they do, we'll package them up. This course then will take you from knowing nothing about R to sharing your knowledge of R with the world. We're excited to see what you'll create. This is CS50's Introduction to Programming with R. Well, hello one and all, and welcome to CS50's Introduction to Programming with R. My name is Carter Zenke, and I'm so excited to embark on this journey to learn this language called R with you. Now, it's likely that you have never programmed before, and if so, that's okay, but you might be asking, what is a programming language actually anyway? Well, it turns out a programming language is something that we humans had created to actually talk to computers and have them solve problems for us. And you might have heard of lines of code, things that actually tell computers what to do. And you may have heard of programs being lines and lines and lines of code telling computers step by step what it is we want them to do. And you might have heard as well, there are other languages you could learn, like C, like Python, like R, like JavaScript. And so you could be asking yourself, why would I learn R? Well, R, it turns out, is this language built from the ground up to work with data. And so if you are interested in data, or some of these fields here, like data science, data visualization, research, or statistics, R could be a language for you. And although this course won't actually teach data science or statistics or the math behind them, you will emerge being able to use R for these disciplines. Now actually, just recently, researchers used R to model how COVID-19 was spread. And this is a visualization built entirely in R to model how COVID-19 was spread on a cruise ship. You might have also heard of 538, these data journalists who actually write articles with data. They use R to analyze data, to write their articles and share visualizations like this one, so we can actually understand insights from data too. So without further ado, let's actually begin by writing our very first R program. And to do that, we'll need what's called an integrated development environment, or an IDE for short. Now, code, at the end of the day, is just text. And you could use any text editor to write code. But it turns out that when you actually want to write lots and lots of code, it's helpful to have a tool to do that with. And that's what this IDE will be doing for us. Now, let me introduce you over here to this IDE called RStudio. Now, RStudio is an IDE built exclusively and particularly for R. And here it is. You'll notice off the bat that I have this kind of greater than sign here with a blinking cursor. And this indicates what we're going to call the R console. It's a place I can actually type R statements and have them run kind of line by line by line. It's a great place for me to actually execute or to run one line of code at a time. So let's actually type our very first line of R code here to create this file called hello.r, in which we'll write actual full-fledged program. So to create a file using this console in RStudio, I can type file.create, open parentheses and close parentheses, and then the name of the file I want to create. So here I'm going to create, in this case, hello.r, just like that. Now notice that hello.r ends in .r, and that is actually very particular. You might have heard of files ending in like .jpg for images, or maybe .csv for data files. In R, we denote our R programs with this .R here. So let me run this R statement here by hitting Enter, and now I should see, well, I see true kind of yelling at me right here. What this means is that this file was created. And we'll also see this kind of bracket 1 here, which will become more apparent as we go on. But it turns out that because R works a lot with data and lists of data, it's often handy when you have lots and lots of data to give us an indicator of where in that list we are. So we'll see this come in handy a bit more later. But for now, with this list of one value, like true, it just says 1 for now. Well, where was this file created? Like, I claim it was created, but where was it created? So RStudio has this file explorer that I can open on the side here. And this file explorer shows me the contents of some particular folder on my computer. Even if you don't know much about computers, you probably know about files and folders. And so here it seems like I am inside of the users/jharvard folder. And inside of that folder, RStudio and R created for me this file called hello.r. Now, RStudio works by default in a single folder, and that folder, it turns out, is called our working directory. If I ask R to create a file for me, it will create that file in the working directory. Or if I ask it to find some data file and read it into my R program, it will first search in that working directory for me here. So let's open up this R file and actually write our first R program. I'll hit this hello.r file icon here. Let me close my file explorer for now, because it's not important at this point. But now I'm introduced to this new component of RStudio, in this case, my file editor. So as we saw before, this R console down here is great for writing single R statements, single lines of R code. But this hello.r file is great for writing more than one line of code, tens of lines, hundreds of lines, creating a full-fledged program here. So I have this blinking cursor, which means I can just go ahead and type some text. And let's type in some text that will be our very first R program. I'll type print, P-R-I-N-T, followed by an opening parentheses and a closing one. And inside those parentheses, let me type hello, comma, space, world, just like this. And now I've typed in some text, my first line of R code. I can save this file by clicking on this little save icon here. Or on Mac, I could do Command S, or on Windows, I could do Control S. So let me hit the save button here. And now this program is saved on my computer. I could run it if I wanted to. Now, you may be used to running programs by double-clicking on them or finding some icon and clicking on that to open the program and run it. But I don't see those icons here. And that is intentional. This is a program we've made ourselves, which will require a different way of running it for us. And even if you don't know much about computers, you probably know computers speak this language called binary, or like ones and zeros. And right now, we just have P-R-I-N-T, parentheses, quotes, hello world. Like, that doesn't look like ones and zeros to me. So there has to be a way to translate or interpret this R text we've written into ones and zeros the computer actually understands. So R is more than a language. It's also an interpreter that takes this text we've written and converts it to the ones and zeros the computer understands. Now, to kick off that process, that interpretation process, I can actually click this button over here that says Run. So let me go down to the console first, and let me clear the console so it's very clear what's happening here. I'll type Control-L to clear the console. And now, if I go to this line of code, line 1, and hit run, I should see my first R program saying hello to the world over here. So let's take a step back first, though, and think about what it is we have just done. So here in R, we have created our very first program. And we've done so using something that's called a function. Now, in languages like R, and lots of others too, you'll have access to these things called functions. And functions let you tell the computer to take some action, do something to solve some particular problem. In this case, our problem was displaying some text, and this function that we saw called print helped us do just that. So let's go back and show you this program again. When I come back to RStudio, we saw that this function is called print. You can probably guess that yourself here. And we know it's a function because I use these parentheses here. This is convention in R to denote a function by its name, followed by parentheses, followed by some particular input to that function. Now print, when the R developers designed it, it doesn't print some predetermined piece of text. Like it doesn't always print hello world, doesn't always print hello to somebody else. Instead, it prints the text that I want it to print. And so we'll see, as we learn programming together, that these functions can take inputs. And more precisely, these inputs are called arguments to the function. They're inputs that change how the function actually runs. Now, what is it that print did? Well, down below in the console here, I see that it printed hello, comma, world. And this is what's known as the side effect of the function, something visual that happened. Side effects could also be something that happens via audio, something else I see. Whatever happens as the function is running, that is known as its side effect. And this is our first program in R so far. But let's pause here and ask what questions we have on R, RStudio, or this first program we just wrote called Hello World. So a question about why we would use RStudio as opposed to VS Code. Well, if you're familiar with VS Code, you would know that it can work with a variety of languages like Python and C and others. RStudio, though, is tailor-made to work with R. And as we'll see later on in the course, there's a lot of features of RStudio that make working with R much easier, particularly with visualizations and plotting. So we'll see that later on in the course as well. Also a question about why we would use R instead of Python. Well, Python tends to be this really big language that can be used for lots and lots of things. And if you think of libraries in Python, like NumPy, you can certainly do work like you would do in R with those libraries. RStudio, though, is more of a precise tool. It's built from the ground up to work with data, whereas Python is more of a general tool for solving lots of different problems. R then comes with some optimizations that make working with data a little more efficiently. But in general, you could use either Python with NumPy or other libraries, or R to work with data overall. Now a question from Luis.
Could you show us how to change the working directory for the console?
So a great question about actually changing the working directory. We saw earlier that RStudio defaults to having some kind of working directory, but you could change that if you wanted to. Well, in R, there is a function dedicated to changing that working directory, and I can show you what that looks like over here. Let me come back to my RStudio environment, and in particular my console. So changing the working directory, that really only requires one line of R code, so I could then clear my console down below here and execute that line of code in the console. The function to do so is set WD, just like this, and then in parentheses, you can then type the path or the folder you want to change your working directory to. So if you do want to do that, you can do it using the setWD function here. Now, we've completed our very first Hello World program, but odds are things aren't always going to go as smoothly for you if you're just beginning with programming. And even if you're more experienced, you might encounter these things called bugs or these errors in your code. So let me reproduce, kind of intentionally here, a bug that could happen in my program. Let's say as I was typing, I didn't type print, I instead typed prin. Let me save this program here, and let me run it to see what happens. I'll hit run. And well, now I see down in my console, error in prin, parentheses, hello world, could not find function prin in this case. So this error is hopefully telling me, like, look, there is no function called prin. And hopefully by seeing this, I should then actually know, well, oh, I didn't mean to type prin, I meant to type print instead. So I can go back and fix it. And this process of actually going back and fixing our programs is known as debugging, finding those bugs in our code and getting rid of them by looking through these errors and talking to a colleague or trying to fix them overall. So here, let me go back and clear my terminal, my console down below. I'll run this line of our code, or run this line of this program here again, and I'll see, once again, hello world. So this is a pretty good program, but I argue we could do a little bit better with it. Like, we don't just have to say hello to everyone. We could try to say hello to a particular user. And so our next step here will be to actually ask the user for their name and then say hello to that particular user. Now, to get user input, there is a function in R for that. It's not print. It's instead called readLine. So let's use the readLine function here. I'll type R-E-A-D, read, line, this is all one word, and then parentheses, opening and closing, and it turns out that readLine takes an argument too. This argument will then be the prompt. It prompts the user with. So I'll ask the user, what's your name? Just like this, and I'll save the file here. So let me go down and clear my console. I'll then run this line of our code, and I'll see what's your name. I could type in this case, my name is Carter, hit enter, and I see Carter. So it's not so much a greeting as much as it is just kind of saying my name back to me. And I think we could still do better than that as well. Let me clear my console, and ideally I want to say something like this. I want to say hello Carter. So I could use print again. Maybe on line 2 now, I choose to say print and then hello, comma, Carter. And I'll save this file again. Well, now I have not just one line of R code, but 2. And when R goes to interpret this program, it will read these lines of code top to bottom, left to right, executing each function along the way. But it turns out that this run button over here, it says run, but what it really does is it only runs one line of R code at a time. For example, I could run just line 1, or I could run just line 2. But what we have here is really a full-fledged program. It's more than one line of code. It's 2. So to run the entire program, I need to use a different approach, a different button in this case. And that button is this source button up top here. Source in this case means to run the entire source file here. So let me go ahead and source. And let me say, what's my name? My name is Carter. And I see hello Carter. But there might still be a bug in this program. Let's try it one more time. Let me clear the console. I'll source again. And what if my name was like Mario from the Nintendo universe? I could type, well, my name is Mario. Hello Carter. OK, let's try it again. I'll do source. And I'll do, maybe my name is Princess Peach. So Princess Peach here. And well, it's still hello Carter. So it seems to me like we need to do something more dynamic than just printing out hello Carter. We need to actually print what the user has given us at the console. So for that, we'll actually need this new concept in programming called a return value. Functions don't just have arguments and side effects, they also have return values. And in this case, readLine will return to us as its return value the user input. You could think of it a bit like a metaphor of asking your friend to go out and ask somebody for their name, and they might write it down and return it back to you, the programmer, so you can use it later on in your code. That's kind of what return values are in this case. But if I have a return value, I'm going to need some place to store it, some place to reuse it later on in my code. And for that, we'll need something called a variable or an object. A variable is some name for a value that could change. So let's see how we could use both return values and objects in R to make this program more dynamic. Let me go to line 1 here, and let me try to give this return value of readLine a name I could reuse later on. Well, if the user types in Carter, I want to refer to that value via some name, and maybe the right name is just simply name. So I'll type name here. And now if I want to store the return value of readLine, that is whatever the user typed in, inside this object called name, I could use this syntax, these particular characters here, the less than sign and a dash. And notice if we read this kind of right to left, first, readLine will run as a function. It will prompt the user for their input. The user will type that input in, and then readline will come back to us and give us back whatever the value is that the user typed in. And then these lines of code over here, name space less than this dash here, will store it underneath this name called name. This arrow, this leftward arrow, is called the assignment operator. We're assigning whatever return value from readline to this new object called name. So let me just for now get rid of this line 2 and just focus on this particular piece right now. Let me source this file. And now let me say my name is Mario. I'll hit enter. And I see nothing yet because there's no print. But now, if I open up this new pane in RStudio, let me go ahead and go to my environment pane, I'll actually see what the value is for this object we created called name. So it seems like RStudio is telling me that I have this object called name, and its value now is Mario. This is part of our environment. The environment is the place we actually store our objects while our program is running, so we can then reuse them later on in our code. So I've kind of captured this user input and stored it in this object called name. But let's see how we could use it now. I'll come back to RStudio. And let me go back to line 2. And let me now print, in this case, let me print hello, comma, name, just like this. I'll kind of close my environment over here. And now let me source this particular file. I'll type Mario, that's my name. And now I'll hit enter. And I see, well, hello, name. So this isn't exactly what we wanted. I actually printed out literally hello, comma, name. So I think we'll need to find some other solution here. We solved one problem, which was getting the user input and storing it somewhere. But I mean, how do we reuse that later on? Well, if I'm being observant, I might notice that what I'm really trying to do is combine some pieces of text. Like this text here is hello, comma, space. And the text I'm trying to combine is whatever the user typed in, or that is whatever is being stored in this name object I have over here. So I'm trying to combine hello, comma, space, and this text from the user, Mario. Now, this is a common problem in programming, trying to combine pieces of text. So common that it actually has its own particular name. This is called string concatenation, where concatenation means combining together these various pieces of text, or these strings. So let's break it down. And here, of course, we have the very first part of our greeting. This is some piece of text, or from here on out, called a string. A string because it's kind of characters strung together into one piece of text. Strings begin and end with these double quotes here. So I have hello, comma, space, and that is one particular string. But then the user comes in and they type in their own string, let's say like Carter. And now my task is to combine these together into a single string and print that back out to the user. So my goal here is to do effectively this, turn these two separate strings into one individual string. Now R, handily enough, comes with a function to do just this. So let's explore that function here. This function is actually called paste. Paste as in P-A-S-T-E. And paste allows me to concatenate various strings. So let's try this one here. If I want to use paste, I use it the same way I would any other function. I could use the function name and then opening and closing parentheses. And then paste will take as input any number of strings I want to concatenate or paste together in this case. So let's say the first string, as we said, is hello, comma, space. Now the next string is something new. It's actually going to be whatever is stored in this name object over here. So if I want to provide another input to paste, I should actually separate it now with a comma. So after the first input to paste, the first argument, I'll then give it a second input or a second argument. And this one will be literally name in this case, this object we stored that has that value the user themselves typed in. And now paste, its return value will be the combined version of these two strings. So let's try it. Maybe I'll store the return value inside its own object called greeting. I'll use the left arrow, this assignment operator, to store the return value of paste in this object called greeting. And then down in print here, I won't print hello name literally. I'll instead print whatever is stored in the object called greeting. So as I run this, let me open up my environment so we can see how these values change over time. Let me go ahead and click source here. My name, in this case, is Carter. I'll hit enter, and I see hello Carter. So if I go back to my environment here, I see I not only have this object called name storing Carter, I also have this object called greeting storing the concatenated versions of, in this case, the string hello, comma, space, and then the string Carter itself. But if you're being particularly observant here, what do you notice as a bug in this program? Let me ask our audience here. What do you notice as a bug in this program?
There are 2 spaces.
Yeah, there are 2 spaces. So I only wanted 1 space, but it seems I have somehow gotten 2. Like greeting here has hello, comma, space, space, Carter. So why is that? Well, I could spend a lot of time kind of banging my head wondering why is this not working, or I could look at something called documentation. So programmers, when they write functions like paste, they also write documentation that tells me exactly how to use paste and what the expected output of paste might be. So let's look then at the documentation for paste. I can actually access documentation if I use this special character in R called the question mark. And if you want to remember this, I was trying to think of like just being confused. Like, what do I do? The question mark is that symbol. Then I follow it with the function name, in this case, paste. So now, over in the right-hand side, let me make this bigger for us over here, I'll actually see the documentation for paste. Whoever created this function called paste helpfully wrote this documentation to guide me on how to use paste itself. So I'll see up top, the goal of paste is to concatenate strings, like we just talked about. That much is pretty obvious. But down below, I think, is the helpful part. This down below will tell me what kinds of inputs paste could potentially take. And I'll see the same thing we saw before, paste, followed by some parentheses with various what we'll call parameters here. So these are still inputs to paste, but they're potential inputs. And because they're potential ones, we'll call them parameters. Arguments are the actual values we pass to paste. Parameters are the potential ones here. Now I see, if I go down here, some dot, dot, dots. These dot, dot, dots mean that paste could take really any particular number of arguments. That could be any number of strings I want to concatenate in this case. I then have over here, though, this named parameter called sep. And it says sep equals, quote unquote, with a space in the middle. Now this is what's called a named parameter. It has a given name because it has a special use case in this case of paste. Now the equal sign means the default value for this parameter is going to be this value here, the quote space unquote. So it seems like this parameter called sep might be what's making this extra space actually happen in my output. And if I go back to the documentation over here, let me scroll down a little bit so we can see. I'll go down to the arguments, and you can see that sep is in fact a character string to separate the terms. So my job now is to think about what would I change the value of sep to be to remove that extra space. Well, I can go back to my program, and ideally, I don't want any characters to default separate the strings. I just want to have them put together with no spaces in between. So to use this named parameter called sep, I can then have another input to paste. I could follow it with a comma, just like this, and then use that named parameter, sep, in this case, and set it equal to some new kind of value. In this case, quote, unquote, or really no spaces at all. So let's try this now. I'll clear my console, I'll run source, and then I'll type Carter again, and now I'll see hello, comma, space, only one space, Carter. Now, if you're like me, you might think, I'm going to often want to concatenate strings that don't have any spaces in between them. And it's going to be a lot of typing to always type comma sep equals quote unquote. If you're writing many lines of code, you don't want to do this over and over and over again. And in fact, some R users got tired of just this, and they wrote their own function where the default is sep equals quote unquote nothing. This function is called simply paste 0. Paste 0, where 0 means there's nothing in between these concatenated strings. I now don't need to supply the input sep because the default will always be no particular space at all. Now I'll rerun this program, source, and say Carter, and I'll get that same output. Now, one other way to do this, because there's always more than one way to do something, is I could maybe just omit the space altogether. Like I could say hello, comma, and make that my string. And I could then assume that paste will go ahead and actually add the space in for me. I could run source just like this, type in Carter, and now I'll see hello Carter again, completing our program here. So let me pause and ask what questions we have on paste, string concatenation, or our program so far.
So what's the difference between the paste function and the cat function? Because I think both of them are used for string concatenation.
Yeah, good. So if you are familiar with R, you might have also heard of this function called cat. And cat itself stands for concatenation. Cat and paste have two similar use cases. They both involve combining strings together, but they have slightly different outputs. So cat has the side effect of printing whatever you've concatenated to the console. Paste, on the other hand, does not. Paste only returns to you, kind of silently, the concatenated version therein, and you can then use that later on in your code. Cat, I believe, does not actually return to you the result, it just kind of prints it to the screen as a side effect. So two very different use cases, but the same kind of goal here. All right, let's continue, and let's keep improving our program here. So one thing you might notice is that I have this object called greeting, and I'm just on the next line using that very same object. And this seems just a little bit redundant because I'm just storing this value from paste in greeting and immediately giving it back to this function called print. Well, to have this same result and actually reduce some number of lines of code, I could do the following. I could actually remove the idea of storing the result of paste in any given object, and I could simply run paste and immediately pass the value or the return value from paste as the input to print. Now this is arguably the most complicated line of code we've seen so far, so let's break it down just a little bit. This, what we're doing right here, is known as function composition. I'm making one function run and then immediately passing the output of that function as input to the next. So this is our line of R code. And we said before that R runs lines of code kind of line by line, top to bottom, left to right. And that's mostly true. But in this case, we see there's more than one function to run or action to take on this particular line of code. So what is R to do? Well, what R will always do is look first for the function that is innermost in the parentheses. So in this case, that is the paste 0 function. That is concatenating or combining hello, comma, space, and then name over here. Now, what this will do is make the return value of hello, comma, let's say, space Carter, and then pass that immediately as input into print, just like this. And once that's done, print can then do its job, and of course, just print out something like hello Carter. So always think about the innermost function running first and passing its return value as the input to the next innermost function, and so on and so forth. So let's go ahead and try this out. I'll come back to RStudio here, and here I have paste as opposed to paste 0, but kind of the same thing as we saw before. Let me go ahead and click source here. I'll type Carter, and we'll see that I get the very same result without storing, in this case, an additional object. Now, an extension of this might be the following. I could take readline, and notice how it's just simply storing the value in name, which I immediately pass as input to paste. I could do this. I could take readline and put this right there, and now I have 3 functions nested inside of each other. But let me actually ask you, why might this not be a good idea? Let's think about other people who might read this code, or think about working together on projects. Like, why might I not want to do this or go this far with the design of my code here?
As I think because it doesn't explain the code perfectly to the user.
Yeah, it's kind of hard to read. Like if I saw this line of code here, I would have to kind of think to myself, okay, which function is happening first? Well, it looks like it might be readline. And then what happens next? Okay, paste happens next. So it's a lot for me to think of as I'm reading this program. And even though it is shorter, I would say it's not necessarily better. So these are questions about the design of programs. Which way to write the code is better? We have the same result, so they're both correct. But there are still different ways to design it and trade-offs to consider in terms of readability as well. So let's come back and let's try to fix up this program a little bit. I would argue that it's probably cleaner if we instead have readline on a separate line of code. I'll put this first on line 1, and I'll go back to storing this object called name, and I'll pass it in as input to paste here, just like this. Now we just talked about the idea of making our code more readable, and it turns out that R comes with a feature that can let me do just that. I can actually leave myself some notes to self called comments that will help me understand my code using the English language. So if I want to write a comment or a note to myself in my code, I can do so by typing this hashtag here, followed by a space, and I can then type the comment I want to type. I could say maybe this line asks user for name, just like this. And the next line, well, what does this line of code do? This line of code says hello to user, just like that. Now comments, by convention, go on the line above the line of code that they are talking about. So in this case, I know this comment on line 1 refers to the code on line 2, and this comment on line 4 refers to the line of code on line 5. But comments are very helpful when you actually are working on a larger project. You come back later, don't know what you did. Comments can then help you understand exactly what to do and what you had done prior as well. So this was our hello world program. We said hello to the world. We said hello to some users. Let's get working with some data now. And in one case, we might want to work with data in terms of, let's say, counting votes for an election. So let's go ahead and try to simulate an election between some fictional characters from the Nintendo universe, in this case Mario, Peach, and Bowser. So to create this new program, I'll go to my console again, and I'll type file.create. And in this case, I want to count some votes. So I'll call this program count.r, just like this. I'll hit enter, and I'll see that this file was created. So now if I open up my window over here and go to files, I should now see that count.r is available to me as a file to write this program in. I'll open up count.r, and now I have a blank slate of a program to write. So we have 3 candidates to keep track of votes for Mario, Peach, and Bowser. So let's let the user actually type in those votes and return to them or print out the total number of votes that happened in this election. So maybe I will ask the user, using readline, to enter votes for Mario, just like this. And I'll also ask the user to enter votes for Peach, just like this, Princess Peach. And I'll also use readline to ask the user to enter votes for Bowser, just like this. Now, it's likely I'll want to use whatever the user types in later on in my code. So why don't I store the return value of readline in an object I could reuse later on? Maybe I'll call this one Mario, and this one Peach, and this one, let's go for Bowser, just like this. So I'll save it. And again, the goal was to kind of add up these total number of votes. Well, maybe I'll make a new object called total to store those total number of votes. And I'll have something that will assign that total number here. Well, it turns out that to actually add data together, I can use in R this plus sign, this plus operator. So I'll say Mario plus Peach plus Bowser. And that should return to me the total number of votes the user has actually entered in the console. And if I want to then print that back out to the user, well, I could use print and paste again. So I'll use print, paste, and then total votes, no space, because paste will actually add it for me, and then total itself down below here. So a few things we've seen before, and a few new things. What's new is this arithmetic. we've seen now we just use this plus operator to add together some numbers. And R has more than just the plus operator. It has several others as well. It has addition, as we just saw with the plus sign, subtraction with this minus sign or a dash, multiplication with this star or asterisk operator, and division just like this with the / here. There are other operators too that we'll talk about later on in the course, but for now, these 4 will help you do some basic arithmetic that can help us solve some really interesting problems in this case. So let's come back, let's run our program. I'll come back to RStudio, and I think that this should work. I'll go ahead and run source, and I'll enter votes in this case for Mario. Maybe I'll say Mario has 100 votes, and Peach has 150, and Bowser has 120. And now I should see the total number of votes that were cast in this election. I'll hit enter, and I'll see another error. It says error in Mario plus Peach, non-numeric argument to binary operator. The other error, I'll admit, was easier to understand. This one's less easy. So at least it tells me where the error happened. It said it happened in Mario plus Peach. So it seems like maybe on line 5 here, when I tried to add the user's input for Mario to the user's input for Peach. And it says the reason, a non-numeric argument to the binary operator. So the binary operator, I'll tell you, is this plus sign here. But the non-numeric argument, it seems like it's telling us that Mario and Peach, those aren't numbers at all. So let's take a peek at our environment where we stored those actual objects. Let me take a peek over here. And what will we see? If I go to environment, maybe remove this down below here, I see some old things here, like greeting and name, that I didn't get rid of before. But I also see Bowser, Mario, Peach, and what do you notice? Well, it seems like before we had, let's say, greeting that was a character string. And we knew it was a character string because it had quotes around it, right? But we see the same thing now for Bowser and for Mario and for Peach, which implies to me that these are still character strings. They're not so much numbers. Now, I think R is now telling me that it needs numbers to be able to add these things together. It can't add a character 120 with the character 100. These need to be actual numbers. So let's see what we can do about that. Let's come back to RStudio here, and let's actually introduce this new idea of a data type or a storage mode. In R, we have various ways of storing data. We've seen one so far called a character string, but there are lots of others too. Among them are these, characters we just saw, and then double and integer. These are both numbers. Double refers to a decimal number, like a 1.5 for instance. Integer refers to a whole number, like just 1, plain and simple. And there are more too, but these are the ones that matter here. So it seems to me like readline, when it returns us the input from the user, it returned a data type of character, or a storage mode of character. But what I really need to add these numbers together is a double or an integer, these numeric storage modes down here. So let's see if there are functions that could help us. There actually are. So among them are this idea of as.character, as.double, and as.integer. These are functions that can actually take some particular object and convert them to the storage mode we want. So I could give as input to as.integer some object, and it will return to me then that same object, but now as integer. And this is known as coercion, changing the storage mode of an object using a function like this to convert it to some particular new storage mode. So let's try these out. I'll come to RStudio again, and I will then try to convert this data to an integer before I actually add it together. That's on line 5 and below. Let me go ahead and use as.integer. I'll type as.integer Mario, and as.integer Peach, and as.integer Bowser. Well, in this case, hopefully that should work. Let me go and hit source again, and I'll enter, let me clear my terminal first. I'll enter 100 votes for Mario, 150 for Peach, and 120 for Bowser. And I still see that they're not numeric. So one common mistake is that simply running the function here is not enough to change this particular object. I need to then reassign the return value of this function to the object itself. So for instance, if I want to update the value of Mario, I need to reassign it as the return value of as.integer. Or I need to update the value of Peach by reassigning it as the return value of this function here. And same with Bowser as well. And now I think if I run this, fingers crossed, let me come to my console again, run source, and I'll choose 100 for Mario, 150 for Peach, 120 for Bowser, and I'll see the total votes was 370. Now, this is a bit of a longer program than we've seen before. This is like 11 lines total. There's probably a way to actually clean this up a little bit, though. One way would be to immediately try to convert the input from the user to an integer. So I could use function composition, and I could instead immediately pass the return value of readline as the input of as.integer. And same for Peach, and same for Bowser. Let me actually clean this up, have a parentheses there and a parenthesis here. And now I can get rid of lines 5 through 7. And now it's just a little bit shorter. And I'd argue that this is actually a good use of this particular function composition, because now I'm immediately seeing that, OK, I want an integer from the user. Let me go ahead and try this again. I'll click source, and now I'll see 100, 150, 120, and I still see 370. Now, this is pretty good, but let's think of a corner case or some other scenario where there are more than 3 candidates. Well, in this case, I don't want to be stuck always typing plus some new candidate. What I want to use instead is likely a function called sum. Now, R, because it works so often with data, has this function called sum that can take as input any number of numeric arguments and sum them up for me. So let's use sum instead. In total here, I actually want to return the result of calling sum with 3 arguments, 3 inputs. The first is Mario, second is Peach, and the third is Bowser. So now sum will look at all 3 of these numbers, add them up, and store them now in total. So I'll clear the console, run source, and I'll type in 100 votes for Mario, 150 for Peach, and 120 for Bowser. And now I'll see total votes was 370 as well. So we've improved our program so far, and we've seen how to use these storage modes to add data together. Now, what questions do we have on this program here, or storage modes in general?
Can we enter an argument like an array to this sum function?
Yeah, so I heard you mention this idea of an array. And if you're familiar with other programming languages, you might have heard this idea of an array, like some list of data. And the question is, could we give sum not these 3 separate values, but actually an array or some list of data? In fact, we can. And I'm going to suggest we actually take like a 5-minute break and come back to learn more about these structures we can use to represent data just like that. See you in 5. Well, we're back, and so we've seen so far how to write programs that take user input. But odds are, as you write more R programs, you won't rely so much on the user to actually enter data for you. You'll instead read data from a file, like a CSV file, for instance. So let's take a look at ways you can actually represent data and how to use those representations now in R. Well, you often find data is stored in these things called tables. And here is an example table. I'm trying to represent here candidates like Mario, Peach, and Bowser, and the number of votes they received at the poll, so this is actual physical polling location, and via mail, from mail-in ballots, let's say. So notice how this table has both rows, this kind of horizontal orientation, and columns, this vertical orientation. In particular, there are 3 columns with names. So one is candidate, where I have the names of my candidates, in this case, Mario, Peach, and Bowser. Over here, I have this column called poll, representing the number of ballots or votes that Mario, Peach, and Bowser received at the actual physical polling location. So let's say Mario got 37 votes, Peach 43, and Bowser 84 now. Well, for the mail column, there's also going to be some numbers here as well. Let's say Mario got 63 mail-in votes, Peach got 107 mail-in votes, and Bowser 36. So this then is our table of rows and columns. And one kind of analysis we might want to do on this table is called a tabulation. That is, figuring out how many votes we received by poll or by mail, and also how many votes each candidate received. So we could ask the question, how many votes did Mario receive overall? That would be a tabulation along these rows here. We could also ask how many votes did we receive at the actual physical polling location. That would be a tabulation along this column here. So there are two questions we can actually answer using R. But R, at least immediately, doesn't give us a way to represent a table exactly like this. If you want to store this data kind of long term, you'll need to do so in a file. And one popular way of representing data like this inside of a file is to use a CSV file, or a comma separated values file. So here is the same representation of that data, but now as a CSV file. Notice here I have those same column names, candidate, poll, and mail, and I still have those same column values, Mario, Peach, Bowser, 37, 43, 84, and so on. But what you might notice is that the columns are now separated using these commas, and that makes sense. This is a comma separated values file, or a CSV file. Every row is still on its own row in the file, but now these columns are represented now with these commas. So let's see how we could use R to read in this CSV file and give us an actual table of data to work with. I'll come to RStudio here, and one of the first things I actually might want to do is clean up my working space. If I want to see what's currently in my environment, I can type this function, ls, at the console and hit enter. And now I'll see all the objects that I still have in my environment from some prior programs. Now, I probably want to get rid of these as I'm writing some brand new program. So to do that, I could use this function called rm, which stands for remove, whereas ls stands for list. I could use rm, and it turns out that rm takes a named argument called list, that is the list of values I want to remove from my environment. And I'll say that this list is what was the result of calling ls. That is, it will include Bowser, greeting, Mario, name, Peach, and total, all of these prior objects I no longer want anymore. So I'll hit enter on this, and I'll type ls again, and now I'll see character parentheses 0, which basically says there's nothing here right now. There's an empty string, nothing at all in my environment. So now my environment is clean. There are no objects here. Let me actually create a new program, one called tabulate. So I'll do file.create tabulate.r to represent how we're going to tabulate this table of data and find the number of votes for each candidate and each voting method. Let me do enter here, and I'll see that file was created for me. I'll go to my File Explorer and open up tabulate.r. So actually notice here in my File Explorer, I do have this file named votes.csv. And if I click on it, I can actually see, if I click View File here, what's inside this file. And notice here, I have the same exact thing we saw on the slides. Candidate, comma poll, comma mail, and then one row for every row in my data set. So our goal then is to read this CSV and store it in R so we can actually get back a table of data to work with, now entirely in R. Well, one function I could use to read data from a file like this is actually called read.table. Read.table, and I can give read.table the name of the file I want to read or to open, to load inside of R. So that file name was votes.csv. And because votes.csv is in that working directory, I can just refer to it by its plain and simple name. So a read.table has a return value. It's going to give me back a table of data. So I'm going to actually store that, let's say, in this table called votes. And now let me run just this line of our code. I can do that by hitting run over here, or on Mac I could type Command Enter. On Windows I could type Control Enter. I'll do Command Enter on Mac. And now I see, according to the console, I have now read the votes data table here. So if I want to see what it looks like, there are a few ways to do that. I could actually look at my environment. Let's try that first. I'll go to Environment, and I'll see the following, that votes seems to have 4 observations of one variable. So observations actually refers to the number of rows in this table I've gotten back, and variable refers to the number of columns I've gotten back. And you might already be thinking, this doesn't seem right, because I thought I had at least 3 rows, and I thought I had at least 3 columns, and I seem to have 4 rows and 1 column, so something might be wrong here. If we want to see exactly what happened, I can use this function called view, capital V, and I can pass as input the object I want to view in this case. If I run this line of our code, I should now see a separate tab that shows me exactly what is stored in this object. And I would say these results are not good. This is not what I want it to look like, because again, we only have 1 column that R seems to have named V1. And instead of 3 rows, there are 4, where 1 row is actually the names of the columns that I wanted to be the case. This is just not what we want. So it seems like read.table needs more information on how to read this particular file. And one thing it might need to know is, what is the separator between each of my columns? Well, because this is a CSV file, that separator is none other than a comma. So read.table, like paste, takes a named argument called sep, and this will set to be an actual comma. So now read.table knows to look for these commas and use those to identify what is a column inside of this data file. So let me then rerun this line of code and now view it, and I'll see we're getting better. So here I have 3 columns, although one is called V1, one is called V2, the other is called V3. And I still have 4 rows, so it's not quite there, but we're getting close. One other argument to read.table is in fact this one called header. So header can be either true or false, yes or no. Do the column names exist in this file? In this case, they do. So I'll say header equals true. I'm essentially saying that yes, the column names are inside this file. You should look for them, and you should use them. So let me rerun this. I'll rerun line 1. And now line 2, and now I think we're in a pretty good place. So R actually has stored inside its environment this table for me to use. I see 3 columns, candidate, poll, and mail, and now 3 rows. I could do something to make this a little more readable. Often when we have lots of arguments to these functions, it's better to put them on separate lines. So according to the style guide for R that kind of tells me how I should be structuring my file, I should do something a bit like this. I should put each argument on a new line in my code, and then make sure that this closing parentheses is all the way against the left-hand side. So this allows me to more quickly see what arguments I have supplied to read.table, but the result is exactly the same, of course. Now, CSV files are pretty popular, and it doesn't make sense to me to always be writing sep equals comma, header equals true. And in fact, people who work with R, they come up with their own function called read.csv to make this much easier for us as programmers. So instead of read.table, which can work on a variety of actual data files, I might instead use read.csv because, of course, I have simply a CSV here. So let's try this. I'll run just read.csv given the file name, hit enter here, and it's the same result, but now with much less typing, much fewer arguments. Read.csv just seems to know more naturally how to read these files called CSV files. OK, so we've successfully read this CSV file. But the next question is, what exactly has it given back to us? Like, certainly it's a table. But in R, this table has a special name, and this special name is a data frame. Now, a data frame is what we're going to call a data structure, some way of organizing our data that allows us to do things with it much more quickly. And those things for a data frame might involve accessing the columns, or accessing the rows, or performing things like tabulations, as we'll see in just a little bit. So here, again, is our data frame, but now it's called votes, just like this. And let's say I actually want to access some particular columns or some particular rows of this data frame. Well, because it is a data frame, R gives me some special syntax, some special actual characters I could type to access those columns and those rows. Now, one way is to use what we call bracket notation, where I could take the name of this data frame, use brackets, and then supply the number of the row and the number of the column that I want to see. So for instance, let's say I wanted to access this particular value, Mario, in the first column and the first row. Well, in that case, I could type votes bracket 1, comma, space 1 for the first value in the first row and the first column. But more often, you want to access not just one particular value, but all the values in a column or all the values in a row. And to do that, you can simply omit one or the other, the row or the column value. So here, to access all the candidates, I could type votes bracket comma space 1, omitting the row number, but only supplying the column number, the first column here. That will give me this list of Mario, Peach, and Bowser. What if I wanted the poll numbers? Well, I could do votes comma 2, and that would give me 37, 43, 84, and same for male, but now with number 3. So let's try it in R. I'll come back over to RStudio and go back to my program. And our goal again was to sum up, let's say, the number of votes we got at the polls, so I could at least see those values if I do votes bracket and then comma 2, just like this. Let me clear my console and run this line, and now I see those same values, 37, 43, 84. Same thing here, 37, 43, 84. Even though in my console they're kind of turned on their side like this, these are in fact the same values I've seen in my table. But what could go wrong here? Well, if we think about this, what's to stop me from rearranging these columns, from maybe making male second column and poll the third? If my program can't update based on that kind of rearrangement, it's not a very good program. So there is another way to actually access columns, in this case using their names. So instead of the number of the column I want to access, I can use its name, which is much more robust. If I change the ordering of the columns, I can still access the column I want to access. Now the syntax for this looks a bit as follows. I would use the data frame's name, votes, followed by a $sign. And then I would get back, in this case, I would actually type the name of the column I want to access. And I would then get access to that particular column. So votes, $sign candidate, that gives me access to this column of candidates. Same thing with poll, votes, $sign poll, and same thing with male, votes, $sign male. This $sign has nothing to do with currency. It's just a way to actually access a column by a particular name that it has. So let's come back to RStudio and try that out now. Let's say I want to access the poll column. Well, instead of using the bracket notation with the comma 2, I could use votes $sign poll. And now let me clear my terminal, my console down below. Let me run source. And oops, let me actually instead run this particular line here. I'll get 37, 43, 84, just as we saw before. So let me pause here and ask, what questions do we have about these data frames so far?
Can I ask if I can get some particular value from some particular row by accessing the votes or the main column, votes bracket or $sign, the column, then $sign the value?
Yeah, great question. So we saw earlier there's some syntax that can get us access to some particular value in this data frame. Let's see that in action a little bit here too. So I'll come back to RStudio, and let's say we want to access Mario's number of votes they received at the polls. So this would be the second column and the first row. And in R, we tend to index things, that is, start counting from 1. So the second column and the first row. So here, let me go ahead and try to access that particular value. I could say votes, like we saw before, open and close brackets, and I know, again, this is the first row, so I'll put that as the 1 here, and then the column number, which in this case was the second column, counting from 1, so 2. This should, if I hit enter on this line of code, or command enter, should show me that in fact Mario has 37 votes at the polls. I could do the same for Peach, let's say. Peach has 43. Bowser has 84. So that is a way to actually access individual values in our data frame. One other way to do this, though, is take advantage of another data structure. So it turns out that when we access the columns of data frame, what we're getting back is no longer a data frame. What we're getting back instead is what R calls a vector. A vector is simply a list of data that is all of the same storage mode. If you've heard of arrays in C or lists in Python, a vector is a similar idea, but it's simply a list of values all of the same storage mode. So to visualize this, let's go back to our data frame here. And let's say I want to access this particular column of votes. Well, I could access it using votes $candidate. And when I do that, what I really get back is this separate structure that is just the values from that particular column. And now, because this is a new structure, I could actually use that same bracket notation to ask for particular values from this list of data. Now again, we start counting from 1 in R. So this is our first value, second, and third. If I want the first value, the first candidate, I could use votes $candidate and then bracket 1. That will give me Mario. I could use votes $candidate and then bracket 2. That would give me Peach. And same thing with Bowser here. So we're kind of taking out or extracting this new vector, and we're able to access individual values in it. Now, one example I like to use is this example of building blocks here. So here we have our very own data frame composed of 9 individual pieces of data. Now, when I ask for some particular column from this data frame, what I'm effectively doing is taking out one column and treating it as a separate object I can use in my program. Now again, if I want the first value in this vector, I would simply take the one from the top, the second one down, the third one down. Now, in R, we also see that when we print out vectors, see them in our console, they aren't always kind of vertically arranged like this. Often, they'll be a bit more like this, where I might take, in this case, kind of put it on its side, a bit like this, or I would now get A, B, and C kind of left to right like this. Even though in our data frame it was top to bottom, we might get it represented kind of side by side, a bit like this. So same thing, ultimately, and there's this idea of kind of extracting this vector from our data frame. So let's try that now in R. I'll come back to RStudio, and let's go ahead and try to access maybe the first value of the poll column. Now we saw before, I could simply use bracket 1 on this new vector that I've created by accessing the poll column of votes. Let me hit Command Enter, and I'll see 37. Let me do the second value, and I'll see 43. So I think with this, we could start to answer one question we had, which was how many votes did we get at the polls in total? Well, one way to answer this is to say, let's sum up votes $poll, the first value in that poll vector. Then let's find that second value as well. Then let's find that third value, just like this, and sum all of those up. And if I hit Command Enter here, I'll see I have 164 votes at the polls. But just like we saw before, there's probably something that could be better designed about this particular line of code here. And that is, if I had more than 3 candidates, I'd be typing a really, really long line of code here. So what I could instead do is this. I could give sum, to our earlier question, the vector itself. Simply votes $poll, which we know is a list of values, a vector. I could give that entire vector to sum that will then know what to do with it and return to me, in fact, the sum of each of those elements of the vector. So we call sum here vectorized. Sum knows what to do when it gets not just a single value as input, but an entire vector. And R is really built from the ground up with these vectorized functions that can take whole lists of data and operate on them very, very efficiently in this case. So here we've answered that question of how many votes do we get at the poll. Let's take that next one, which was how many votes do we get in the mail? Well, I could do now sum, and then give the mail column, which is in fact a vector, and have that summed up. And we'll see we got 206 votes now in the mail. OK, So we've seen vectors and we've seen data frames, but we still have one other question to answer, which was how many votes did each candidate get? Now to do that, we have to sum up some values across columns here. 37 plus 63 is Mario's votes. 43 plus 107 is Peach's votes. And 84 plus 36, that's Bowser's votes. So let's try it. I could maybe treat two separate columns here. I could do votes and what's that one? Poll. OK, votes poll. Get the first value for Mario and add up, let's say, the first value in male, a bit like this. And that, I would argue, is Mario's total number of votes. What if we did maybe the second value in poll for Peach, and let's say the second value in male, also for Peach, 150, so that's Peach's total number of votes. Let's do votes and the third element in the poll column, and the third element in the male column, and that would then be Bowser's votes. And I hope you can tell by me being kind of bored while I'm doing this, this is like not the best way to do this. There is actually a better way that takes advantage of a feature of vectors in R, which is vector arithmetic. So not only are vectors handy at representing lists of data, we can use them to efficiently perform math as well. So if I wanted to sum up all of these vectors and find out how many votes each candidate got, I could simplify this and simply type the following: votes $poll plus, in this case, votes $male. And that would be it. But let's visualize this and see why exactly this works. So we said we had this idea of vector arithmetic. And here again is our data frame. So I want to effectively sum up these two columns and return to myself a new total for each candidate, for every row, in fact, that I have. Well, to do that, I can take out these two vectors, poll and male, and think of them separately now. Now I want to add these together, like we said. 37 plus 63, that's Mario's votes. 43 plus 107, that's Peach's votes. Well, to add these, I could use the plus sign, just like this. But if you're new, it's not quite obvious what's going to happen here. I mean, how could I add up these three numbers and these three numbers, and what is the structure of what I get back in the end? Well, it turns out that R uses a new vector as the result of this. And it actually computes the new values element-wise. Element-wise meaning it goes top to bottom in each vector and adds those two corresponding elements together. So first it looks at the first element in each column here, the poll column and the male column. 37 plus 63 is 100. Then it goes to the next one. 43 plus 107 is 150. Then it goes to the next one here. 84 plus 36 is now 120. And we now have a brand new vector by adding up or summing together these two distinct vectors overall. To go back to our visualization here of these blocks, so you could think of me taking a data frame just like this and kind of extracting these two vectors here. Let's say this one and let's say this one. Let me put this one to the side for now. And I want to do some math with these. So in this case, I'll look at the first element in each vector. In this case, 4, and in this case, 1, or 4 and 1. What is the addition here? Well, 4 plus 1 is 5. So the first element of my new vector would be 5. Then I go to the next two elements here. In this case, I have 5 and 2. What's 5 plus 2? That's 7. So the second element in my new vector would be 7. And then, later on, what do I have? I have 6 and 3. Those added together would be 9. My third element in my new vector would in fact be 9. So vector arithmetic gives us in the end a new vector by actually adding, or in this case, adding these elements together kind of element-wise in the end. So let's go back and see how this looks in RStudio. I'll come back to RStudio here, and I will then hit enter on this line of code, and we'll see that I get back a vector of 3 elements, 100, 150, and 120. So let's pause here and ask, what questions do we have on these vectors or vector arithmetic?
How the sum is being printed on a terminal without using the print function?
Good question. So you've noticed that when I press Command Enter, for instance, I'm seeing the results, whatever is stored in this object in my console, without using print. And that, in fact, is a feature of R and RStudio that when I run some particular line of code, I can then see the return value of that particular line, or whatever it computes for me, down in my console. It's kind of a handy feature of these things called IDEs that let me actually understand what's going on in my code all the more clearly. Good question.
I have a question for in data frames. So when we in the dollar notation, it returns a vector. What about in the bracket rotation? Suppose we are taking for a row 1 comma. Does it also return a vector?
A great question. So we just saw with the dollar notation, we get back a vector. Does it do the same thing then with bracket notation? So in fact, it does. Let me show you how it works in RStudio. I'll come back over here. And let's say I wanted to sum up these two columns still, but I don't want to use their names for whatever reason. I'll instead use their bracket kind of representations here. So I'll take the second column of my table here using comma 2, and I'll add together, in this case, the third column, just like this. I'll hit enter, whoops, hit enter, and I'll see I get back the same result. So each one of these is in fact a vector. Where you should be careful though is that there is some notation that looks a bit like this. Votes, in this case, bracket 1. Notice how I'm not actually asking for a row and a column. I'm only asking for some number 1. This will give me back, in this case, the data frame, but now only the first column of that data frame. So this, to be clear, is not a vector. This is the same data frame, but now it's only that single column of that data frame. So be careful here. You won't often use this notation, but you could get back a data frame if you use that kind of notation overall. OK, a good question. And let's now keep going towards solving our problem of tabulating this data. So we saw before that simply adding the male, the poll column in votes and the male column in votes would give us the total number of votes for each candidate. But I would argue that if I run line 3 here and I just get back some numbers, it's not super clear which candidate these votes belong to. So I can actually go ahead and add a new column to my data frame that includes these particular values here. 1 for Mario, 1 for Peach, and 1 for Bowser. And as long as my vector is of the same length as my number of rows in my data frame, I should be able to actually add this as a new column to my data frame. Now to create this new column, I could simply kind of wish it into existence a bit like this. I could say votes $total. And I know there is no column called total, but I can kind of make one. I could say, let's assign this vector to be the new column total in the votes data frame. If I run this line, I'll see I don't get a result, but I do, at least in votes, see there is a new column called total that now includes those same elements in my vector, top to bottom. OK, so we've solved that problem. And our next step might be to now save this file again, to keep track of it later on, to share it with a friend. And to do that, I could use the write.csv function. We saw read.csv, but we also have write.csv to actually save this file as a CSV. Let me try it. I'll say write.csv, and I'll call this one, let's say totals.csv for the total number of votes. Now, write.csv actually needs 2 arguments. One is the file name, like we just said here, but even before that, it needs to know what data frame to write to the file. So in this case, it's our votes data frame. Now, by convention, in its documentation, we see the first argument to write.csv is that data frame. The second is the name of the file itself. So let me clear my console. Let me run write.csv, and now, if I go to my File Explorer, I should see down below, totals.csv, and now let me view File, and I should see something a bit like my data frame. There's a few other features here, though. I see that there's like these numbers here, 1, 2, 3, and this empty number, this empty value up here. These are, in fact, the row names of this data frame. So not only do data frames have column names, like we saw here, they also have row names. And by default, they start counting at 1, then going to 2, then 3, then 4, and so on. And I can actually tell write.csv whether or not I want those row names printed in my CSV. You often won't, because it kind of makes a wacky format where you have this empty value up here, and it's probably just not worth it for you. So you could specify the following. You could say row.names equals false, meaning that write.csv should not write any row names to the CSV, even though they exist in the data frame. So let me go ahead and clear my console. I'll do Command Enter here, and now I should see if I go back to totals.csv, I now have a much cleaner CSV without those particular row names. If I did, though, want to access those in R, I could use these functions. I could say call names votes, which will return to me the columns I have inside of my votes data frame, or row names votes, which gives me access to the row names of this particular data frame as well. All right, so we've seen here how we've been able to save this data frame, how to read data from a file and save it back to a file as well. What we'll do next is actually take advantage of online data sets that other folks have written for us, and use those to explore data in R as well. See you all in 5. Well, we're back, and so we've seen a few examples of how to use R. So far, we've seen how to take user input and actually deal with that in our own programs. We've also found how to use data we put in our own file for ourselves. But often when you use R, you'll be working with not your own data, but somebody else's. And so we'll do exactly that here for the rest of lecture. Now, you may have heard of 538, as mentioned earlier in lecture. They work a lot with data. And they often put that data online for others to use and analyze themselves. In fact, they worked on a poll that asked people in the US about their voting habits. Do they plan to vote? How often do they vote? What encourages them or motivates them to vote? Or what are the reasons they actually don't vote in the first place? So here I have the URL that actually includes this data file online on the internet somewhere else. And if you look at the end here, you'll see the file name, nonvoters_data.csv. So this tells me that this data, even though it is online, is still stored in that same familiar file format called a CSV. And now on the second line of code, I can still use read CSV. All I'm doing now, though, is telling read CSV where to look, where to go find this data file on the internet and bring it down for me here in my own R environment. And I'm storing the result now, that data frame, as a data frame called voters. So let's take a peek and see what's inside. I'll come to RStudio over here, and let me do the function view, and I'll view voters. And whoops, let me first run these lines of code. So let me run line 1 to create a new object called URL. Let me run line 2 to actually load that data. And now, once I have those objects loaded, let me go ahead and view voters. And this is the data frame. It is a big one. If we scroll all the way to the side, you'll see lots of numbers, lots of columns. If you scroll down, you'll see lots and lots of rows. And one question you might have is, well, just how many rows and columns are there in this data frame? One way to answer that, at least in our code itself, is to use these functions nRow and nCall, which stands for number of rows or number of columns, respectively. So let me try nRow to get a sense of how many rows we have in this data frame. I'll do nRow voters. And it seems like, down on my console here, there are 5,836 rows of data. Now, each row of data represents a particular voter, or maybe a non-voter, somebody who lives in the US and was asked to fill out this poll where they talk about why they vote or why they don't vote. But in the end, each row is its own voter. Now let's see how many columns we have. nCall voters. It seems like we have 119 columns, which is a lot of columns. Each column in this case represents a question asked to that voter. And if I go back to the voters view here, I might see, like Q1, for instance, it seems like the voter who was given the ID 470,001 answered 1 to question 1. And so it's a little arcane right now, but thankfully 538 has given us a tool we can use to interpret some of this data. In fact, that tool is called a code book, and you might often use the same in your own work with data analysis, where a code book tells you exactly what questions or columns mean in some particular context. So in this case, I do see Q1 or Q2 underscore 1 or Q2 underscore 2, and if I'm new to this data set, I don't know what the heck that means. But I could look in the code book that 538 gave me, in which case they say Q1 asked participants this, Q2 asked participants this, and so on and so forth for all questions we have inside our data set. So let's actually take a peek at one particular column. I know this column exists because I looked in the code book to find it out. There's a column called voter underscore category that actually tells us how each voter represented themselves in terms of their voting habits. So to access that column, as we saw before, I could use voters, the name of the data frame, followed by a $, followed by the name of the column, voter category. And if I hit Command Enter here, well, I'll see at least some of the results from that column, some of the elements here. And now you'll actually see why that bracket 1 that we saw initially is kind of useful now. As we work with bigger and bigger data sets, notice that that bracket notation tells us exactly where in our list or our vector we are. Notice how this one here means this always, that is the first element in our vector of all of these responses. This always, well, that's the 7th element in our vector of all these responses. And same thing for this rarely / never. That is the 13th element, and so on and so forth all the way down. Now there's more than what looks to be 900 or about 1,000 entries in our vector here. We just can't print all of them because it would be a really, really long output to our console. Now, I'm curious. I saw a lot of values here, but I want to know exactly what ways voters could have categorized themselves. Like, out of all of these responses, what are the unique ones? And turns out R has a function called unique that I can use to actually figure out what are those unique values in this vector. So let me give this vector called voter category, or the column voter category from voters, to this function called unique. Just like this. I'll do Command Enter to run this line, and now I'll see I only get back 3 elements. Always, sporadic, or rarely / never. So it seems like voters could have categorized themselves in one of 3 categories. They always vote, they sporadically or occasionally vote, or they rarely / never vote at all. So interesting data here. There's another actual column I'm interested in too, which happens to be question 22. So if I look at that here, I'll type voters question 22 and hit Command Enter. And here I'll see all the responses for this particular question. And it seems to me like I'm seeing some numbers, but also these NAs. And before we dive into that, let's take a peek at what this question is actually asking users. So it turns out this question 22 is asking users this. You previously indicated that you are not registered to vote. Which of the following reasons best describes why you are not registered to vote? And users are given several responses, 1 through 7, I believe, where 1 was, I don't have time, 2 was, I don't trust the political system, 3 was, I don't know, and so on and so forth. And it seems to me like when we saw this data set, we had some numbers here, 1 through 7, but we also had a lot of these NAs. And I'm curious if you have a sense of what those NAs might be. There's certainly not any of these options. What do you think those NAs might represent in this particular column of data here?
Not answered or not estimated to be in the list.
A great guess. So maybe it means something like not answered, or there's just no data there. And in fact, if we look at the context of this question, I think we can actually figure it out like you did. It says, you previously indicated that you are not registered to vote. So in the US, we often have to register ourselves to be able to vote. But some people have done that, and some people haven't. It seems like this question was asked to only those participants who did not register to vote, or who were not currently registered to vote. So it would make sense then that people who actually are registered couldn't have answered that question. and in which case we don't want to have like an empty string or some sort of number there. We could instead use one of R's special values. Now, R comes with these special values to indicate something very special. In this case, NA means not available. There could be data here, but there isn't. That's what NA in particular means. There are others too. You might see inf and negative inf. These mean infinity or negative infinity. Numbers that are so big, R can't represent them appropriately well. We saw NA here for not available. We also have N, lowercase a, N, which stands for not a number. You could think of, if I tried to ask you, well, what is infinity divided by infinity? And you'd probably look at me confused. You would say, that's not a number. And I would say, yes, that's exactly correct. R says NaN is that result in this particular case. And we also have this value called null, capital N-U-L-L, which is similar in spirit to NA, but slightly different. NA, as we said before, stands for not available. There could be data here, but there isn't. Null is simply a special value meaning absolutely nothing. I can have a vector of NAs, meaning that maybe I have 5 NAs in this vector. There are 5 places data could be, but I can't have a vector of null. Null is literally nothing. It means absolutely nothing at all. So different slightly from NA in this case. So let's go back to our RStudio here, and let's take a peek at this particular column. So it seems like I have a lot of NAs, and one thing I'm interested in is what kinds of unique values are we seeing inside of this particular column. So I could use unique again and hit Command Enter, and now I'll see if I clear my terminal, run it again, I'll see clearly that I have several different possible values here. I have NA, 7, 6, 2, -1, 1, 4, 5, and 3. And this makes sense. Like we saw earlier that people were given several options, 1 through 7, and we have people who didn't respond, either with NA or 1 through 7 for those other responses there. What we don't have actually is -1, and I actually tried kind of hard to figure out why -1 is here, and I couldn't. So sometimes data is just messy. There are values you don't know and can't deal with, so just keep that in mind as you work with data sets other people have given you. Now, one more column that I found interesting was this one. So it was voters, question 21. Question 21. And the question 21 asked this. It said, there will be an election for president, members of the US Senate, House of Representatives, and other state and local offices. Do you plan to vote in that election? And it gave people a few potential options here. 1 meant yes. 2 meant no. 3 meant unsure or undecided. I don't know if I'll vote in that election. So let's see what we actually got back as responses for this particular question. I'll come back to RStudio here. And why don't we take a peek at voters question 21. I'll hit Command Enter. And here is the first 1,000 or so entries to this particular question. So we see a lot of 1s, which could mean yeses. I see some 2s, which could mean no, 3, unsure, undecided. I do see a -1 down here, which seems to be showing up for some unknown reason. But we could get a better sense if I used unique. So I'll use unique, voters question 21. And now I'll see, again, my unique responses are 1, 2, 3, or -1. So at this point, I'm kind of getting tired of looking at my vector here and trying to convert in my head between these 1s, 2s, 3s, -1s to the actual responses participants gave. And it turns out there is a way in R to make it much easier for myself to work with data that's exactly like this. This data has some set number of categories of responses, as we saw with unique here. The categories are, in this case, 1, 2, 3, or -1. Those are the only possible values that could be stored in this vector. And we also know that 1, 2, and 3 correspond to some real-life actual phrase that participants actually responded to in this poll. So to help us represent this kind of data, we can use something that R calls a factor. A factor. Now I can create a factor using the factor function, and a factor function takes a vector like the one I just had here, and converts it into a factor. So let's try that. I'll say factor voters Q21, just like this, and I'll hit Enter again, Command Enter. And I'll see a very similar thing. If I scroll up, I have all the same data. Everything is just as it was. But now down below, I see levels. Levels. And what does that look like to you? Well, we just saw before, we have several unique categories of data inside this vector, -1, 1, 2, and 3. And it seems like this factor took those unique values and made it this factor's level. So the unique possible categories of data inside of this factor here. So factors are great for representing this categorical data, data that can actually be in one category or another. Now, one thing I could do is try to make it easier to read these categories as English phrases. And to do that, I could pass factor another argument, this one called labels. So not only do I give it my vector that has certain categories of data, I also give it some labels to apply to each of those categories one after the other. So here, let me use labels as the argument, and let me give it a vector itself. So we saw before, down below, that we have a set of levels, number of categories in this data, -1, 1, 2, and 3. But now I could actually give those levels, those categories, some particular name. So I'll give it a vector itself. And I'll make a vector in R using this C function, which stands for combine. I'll create this vector where -1, let's say, maps to or corresponds to this value as a question mark. I don't know what the heck it is. Maybe 1, though, we saw was yes, and 2 was no, and 3 was unsure or undecided, exactly like this. So now notice that when I look at my levels, -1, that corresponds to the first label, question mark. What the heck is it? I don't know. Then yes, that corresponds to the level 1. Then level 2 corresponds to no. Level 3 corresponds to unsure or undecided. And now, if I clear my console and run this particular line of code, well, now I have something much more user-friendly. I can actually see not 1s, 2s, and 3s, but now labels for those 1s, 2s, and 3s. And here I see yes, unsure, undecided, no. Let me see if I can find a question mark here. Yep, there's one. So 517 seems to be a question mark. So now I've converted this vector into my own factor. Now, it's also not a good idea to have data we don't know what to do with. Like I said, this -1, I really don't know where it came from. And in that case, I could tell this factor, when it's being created, to exclude that value altogether. I could use the exclude parameter, the argument here, and say I want to exclude some vector of given values that are part of this vector that I want to just take out altogether. So I'll say -1 is the value I want to exclude. This is a vector of length 1, but the value I want to exclude in this case is -1. And now I can actually remove this label here, because my only categories will now be yes, no, unsure, undecided, or underneath the hood, that 1, 2, or 3. So let me clear my console again. Let me rerun factor here. And now let me see, well, now my data is getting much cleaner. I have yes, no, unsure, undecided. And if I go back to that 517 that we saw a question mark in up here, let me see if I can find it again. 517, almost there. I see now it's an NA, which stands for, of course, not available. We excluded it altogether from this particular factor. So what questions do we have now on taking vectors and converting them to these factors that involve categories of data and labeling those categories of data?
Why have we used factor instead of S factor like before?
So we've just seen here this function called factor, but there is a function called as.factor, similar to what we saw before, as.character or as.integer or as.double. We could use, I think, either one to get the same result. In general, though, let me look at the documentation. Let me go back to RStudio here. Let me pull up the documentation for factor. Let me clear my console. Let me do question mark factor. So this is here how we're supposed to use that factor function. We can see here some of the arguments, the actual parameters I gave, like the labels here as well. Let's now try to find the documentation for as.factor. As.factor. Let me go back over here, type as.factor. And now I'll actually see, the same documentation page. And so to me, this is symbolizing that these are very closely related. If I were to scroll down here, I could see I think I see it here. Is.factor, as.factor are the membership and coercion functions for these classes. So essentially, if you want to make a new factor from a vector, you would use factor. If you have something that you want to convert to a factor that is already something else entirely, like maybe not even a vector, you might be able to use as.factor. So I hope that at least gives you some idea of the difference between as.factor and factor as the function itself. All right, what other questions do we have? Let's take a few more.
How is a factor different from a table?
Good question. So we saw that a table has rows and columns in it. A factor, though, is simply a list of data, a bit like a vector. It's one-dimensional. And let me show you some slides that could hopefully actually help you visualize factors in general. So if I come back over here, let me find the right slide to go to. Here in general is this idea of a factor. So we had, of course, this vector that was previously only 1s, 2s, 3s, and 2s and 1s, -1. But when we convert it to a factor, we did the following. We found the unique categories of data in this vector, just like this, 1, 2, 3, and -1. What we then did is we sought out those categories and called them essentially levels. The categories of our data are the levels here. And we applied some label to each of those levels, basically saying -1 becomes question mark, 1 becomes yes, 2 becomes no, 3 becomes unsure / undecided. Now notice that this factor here is still a vector. Well, still kind of one-dimensional. It's a list of data. It's not two-dimensional like a data frame was or a table was. It's only one-dimensional. And when we apply these labels, we convert these 1s, 2s, 3s, -1s instead to yes, no, unsure, and question mark. And if we exclude something like we did with -1, we would then get NA instead of -1 in the end. So I hope that helps at least a little bit answering that question. Let's take one more here.
I wanted to understand whether, like, just like you showed how to exclude a negative value, what if I want to, there are a number of negative values in the data frame, and I want to exclude all of the negative values?
Good question. So the first part is you want to represent any negative values, and how do you do that? And the second part is how do we exclude those negative values, let's say. Another kind of similar case is, let's say we have lots of NA values. How do we get rid of them? So let me answer your first one and actually tee up that second question for next lecture. So come back to RStudio, and let's try presenting some negative values here. We saw before that I had this idea of -1. If I want to have some negative value in RStudio, I can simply put a negative or a dash in front of any particular value. So here, let's say, is -1. But to your question then of how we could exclude these values we don't want, that's a problem of filtering or subsetting our data, which we'll actually learn about next lecture. So we've seen so far how to represent data in R, how to take all kinds of data like votes, tables of votes, and represent them in R to manipulate them, and so on. What we'll see next time is how to actually transform that data, removing values we don't want, adding data we do. And for that, we'll see you all next time. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Goddard Tan, and in this lecture, we'll learn all about transforming data. We'll see how to remove unwanted pieces of data, how to subset our data and find certain pieces that we want to take a look at, and ultimately how to take different data from different sources and combine it into one single data set. So let's go ahead and jump right on in. Now, whether you're familiar with statistics or data science, you might have heard of this idea of an outlier, where an outlier is some piece of data that falls outside some standard range. Now here, for instance, is a graph of average temperatures in January up here in the Northeast United States. Notice first on the y-axis, I have the temperature in degrees Fahrenheit. That's what we use up here in the US. And then down below, I have the day of the month, 1 through 31. And it seems to me like these bars represent individual days of the month, and how high or low they go represents the average temperature on that day. Now, in the Northeast US, it can get pretty cold by default, kind of all the way down towards 0 degrees. But it could also get as warm as, let's say, 50 degrees or so. It's kind of shown by most of these bars. But in this data, it seemed like there were a few days that fell outside of that range. Like if I look down here on day 2, that seemed like a really cold day, somewhere like -10, -15 degrees. Day 4 seemed even colder, like -20 or so. And then day 7, that was really warm for January up here. It was like 60 degrees or higher. So it seems like these would be the outliers in this data set of temperatures. And for one reason or another, you might hope as a scientist, a data scientist, or a statistician to remove these outliers altogether and conduct some analysis without them involved. So let's see if we can solve this problem of outliers now using R. We'll come back over here to RStudio, our old friend, our IDE, or our integrated development environment that allowed us to write R code and to write R programs. So we saw this function last time called file.create that allowed me to create a new file in which I could write some R code. So I'll go ahead and type that same thing here, file.create. And in this case, I'll call this one temps.r for temperatures here. And I'll hit enter. And now I see true, again, which means this file was in fact created. And as we saw last time, I can go to my file explorer over here, which shows my working directory, the place I'm going to store these R files by default. And I can click on temps.r to now open it in what's called my file editor, where I can write more than one line of R code. Now, as we saw last time, one thing you'll often want to do in R is read some data from some file. And we saw these CSV files, comma separated value files that could store tables of data. Well, it turns out that R can also work with all kinds of other file formats, one of which is particular to R. This is called a R data file. And it turns out that using an R data file, you can store R's data structures, like vectors, data frames, like we saw last time, in a file itself, such that when I load them, I just see exactly what was in the environment in terms of that same vector or that same data frame. So let me try doing that. And to load an R data file, I can use this function conveniently called load. So I'll type load here, followed by some parentheses. And now I could type the name of the R data file I want to open. Now my colleague, let's say, has given me a file called temps.rdata. So I could open it using load temps.rdata, just like this. And now let me run this line of R code. I can do so if I type Command Enter on a Mac or Control Enter on Windows. I could also click this Run button here. Let me hit Command Enter, and I'll see, well, nothing really. But if I look in my environment now, if I open this other pane over here called Environment, I should actually see that I now have a vector called temps that seems to have 31 numbers as part of it here. So why don't I try to find, first off, the average temperature in all of January. And if I want to find an average, I could use this other function called mean, or I often call an average a mean. Well, I could type mean here and then give it this same vector temperatures. And if I run this line of R code, I'll hit enter and see the mean, the average of these temperatures, was 22.74 roughly degrees Fahrenheit. Now, if you're not familiar with averages or means, all I've done here is I've summed up all the values in this vector, and I have divided by the number of values that I have, producing some kind of typical value of the data set, also called the average. So this then tells us that in January, it seems like our average temperature is somewhere around 22 degrees Fahrenheit. But that's not why we're here. We're here because some of these data points seem to be a little anomalous. We had some really cold days and some really hot days, and maybe we want to remove those days altogether before we run this temperature analysis. So let me actually take a peek at this entire vector. I can do so by simply typing the name of the vector and hitting Command Enter to see it down in my console. And here are each of those 31 values. So one thing you might notice is that I can see these outliers now in the data below. It seems like that second day that seemed really cold, well, that day actually had an average temperature of -15 degrees Fahrenheit. And that fourth day, that was about -20 degrees. And same thing here, it looks like the seventh day was all the way up at 65, which is pretty warm over here. So one thing I might want to do is actually pull out these outliers to use them in my code. And we saw last time I could use this method of indexing into this particular vector that is trying to find particular values and pull them out to use in my code using their positions in this vector. Now it seemed like that second day was particularly cold, so I could find that temperature by using temps bracket 2, where 2 represents that second element in our vector. If I want to find it, I could use bracket 2, and I'll see, in fact, I get back -15. Same thing for the other one. I could use temps bracket 4, and that shows me -20, that other outlier in our data set. I could also use temps bracket 7, and that would show me this really warm temperature overall in this same vector. But this is where we left off last time, and what I want to do now, ideally, is not have these outliers represented individually, but really have a vector or a list of those outliers to work with. And I'd argue that I don't quite know how to do that just yet, but I can show you one trick we can use in R to get back a vector from a current vector. So let's think through what we've already done. We saw last time if we wanted to get some element from a vector, we could use this same bracket notation that we even just now used. I could use bracket notation and say, give me the second element inside of this temps vector. And this is known as indexing into this vector. I take the position of the element I want to find, put it in brackets, and I get back that very same element. So again, temps bracket 4, -20, temps bracket 7 is now 65, but it turns out that cleverly in R, we don't always have to provide a single index. If we want instead a vector from this current vector, maybe a vector that includes only some values, well, I could actually give as the index, not a single index, but a vector of indexes. And I could actually index into this vector using a vector of indexes. So let's take a look at that. I could instead type something like this. Give me 2, 4, and 7. Those elements at these positions, 2, 4, and 7. And notice here I'm using this C function we saw earlier, which stands for combine. This makes for me a vector that includes 2, 4, and 7. And now I'm indexing into temps using not a single value, but a vector of indexes. And what I'll get back is as follows. I'll kind of mark these as the ones I want to grab, and I will grab them out and turn them into their own vector for me to work with in R. So let's go ahead and try this transformation of this vector in R and see what we get back. I'll come back to my computer, and I'll go back to RStudio where we have our same temps vector. But now I don't want these individual values. I want a vector of the outliers. So I could modify how I'm indexing into this temps vector, and I could use instead a vector to index into it. I want to get back those values at locations 2, 4, and 7. And if I hit Command Enter here, I'll see I now have a vector of those outliers. And that's pretty cool. I think we do a lot with this. But one thing I haven't done yet is removed them. Like if I still look at temps now, I'll see that those vectors or those elements are still part of my vector. I haven't kind of taken them out to remove them altogether. If I wanted to do that, well, I'll need to take a different approach. And one thing I can do in R is use a simple minus sign or a dash and prefix my C function here, my vector of indexes. And what this will tell R is, I don't want you to grab these. I actually want you to remove them. This minus sign says take the elements at these indexes and drop them, remove them from this vector. So now if I run this line of code on line 3, what do I see? Well, all of my temperatures, but you'll notice that I'm now missing some. I'm missing those elements that were previously at positions 2, 4, and 7, or those outliers. So let's visualize this too. One thing that I've done over here is I've said, I actually want you to remove these values. And I've done so by putting this dash in front of this particular index, this vector of indexes here. And what R will now do is highlight these essentially and say, OK, I know you want to remove these particular elements. And it will then return to me, give me back a vector that includes not those elements anymore. It becomes shorter, so to speak, just like this. So now, back in R, I'm able to remove those elements from my vector. Now let's come back over here and let's see what more we could do with this. Well, one thing I wouldn't want to be in this scenario is the person who has to go through and find all of these particular outliers and tell me what their indexes are. Like if I had to go through thousands of pieces of data and figure out which ones were the outliers and which ones weren't, well, I'd kind of be wasting my time. What I'd love to do instead is really ask a question. Is this piece of data an outlier? Or is it not? Ask this yes or no question. And it turns out that in R, we can actually express those kinds of questions using a tool called a logical expression. A logical expression. Now, a logical expression allows us to, as programmers, to express these yes or no questions and get back a yes or no answer. In particular, logical expressions often use what we're going to call comparison operators. And here are a few of them here. Notice this one, this double equal sign, stands for equality. It allows me to compare two values, a left one and a right one, and ask, are they equal or are they not? Now this next operator, this exclamation point equals, that stands for not equals. It will take a value on the left and a value on the right and say, are these two values not equal? And similarly for the other one down here, you might have seen this greater than sign in grade school. This one stands for greater than. This one stands for greater than or equal to. This one less than. This one less than or equal to. But these comparison operators allow us to compare different values and get back a yes or no response. And actually, true to their name, these logical expressions return to us what's called in R a logical, where a logical is simply this value that is either true or false, yes or no. And so you'll see these values occur throughout your time in using R. Capital T, R, U, E, and capital F, A, L, S, E. These represent yes or no, true or false. Is this comparison true or not? Now you might also see them in terms of just T and F. This is like shorthand for these same logicals, but in general you might often see true or false here. So let's see if I could use these logical expressions to make my job a whole lot easier now as a programmer. I don't have to find these actual indexes going through data one by one by one. I'll come back to my code over here, and why don't I go back to RStudio. So here I have these indexes that I found by kind of combing through my data. But it would be nice if I could have R tell me whether some piece of data is an outlier or not. Well, one thing I could do is maybe try to find those temperatures that are lower than we'd usually see, like less than 0 degrees. Below 0 degrees is kind of this common benchmark for it was really cold. So let's look maybe first at the first element in this temps vector and ask the question, was that temperature lower than or less than 0 degrees? And this is my first logical expression. Now if I were to run this line of code, hit Command Enter here, what do I get back? Well, false. So it seems like temps bracket 1, if I were to run this and show you what that actually is equal to, 15. 15, of course, is not less than 0. Now, what if I did it for the second one? I could ask that same question, temps bracket 2, and then I could say 1 over here, and now I have true. So it seems like temps bracket 2 is negative 15. So in that case, actually, let me change this. This is not 1. It should be less than 0. So temps bracket 2 less than 0. Negative 15 is certainly less than 0. I could keep going and ask the same question for temps bracket 3. Is temps bracket 3 less than 0? Well, turns out it's not. If I see temps bracket 3 down here, looks like that value is 20. So I've gotten some of the way there. I'm able to ask these questions of individual pieces of data, but I'd argue my job, my life isn't that much easier right now. I still have to go through all of these indices, temps bracket 4, temps bracket 5, and so on, and my job is still to write lots and lots of our code to ask these questions. Now, thankfully, these comparison, or these operators here, they allow me to actually give an entire vector as input. They're what we would call vectorized. So I could, on line 3, instead of giving a single value from this vector, I could give it the entire vector and get back a vector in response. I could run line 3, Command Enter here, and now I have a whole vector of true or false values, these logical values. This is what's called a logical vector. And notice here that for every element inside temps, I actually asked this same question. Is this element less than 0? Is this element less than 0? And I see it seems like the second and the fourth are less than 0, just like we saw in our data. So let me pause here and ask, what questions do we have on these logical expressions and these logical comparison operators?
Can I access a tuple in the list?
So a question about tuples in lists, which are other structures we have in R. Tuples are similar to vectors, but they actually store more than one storage mode, for instance, both numeric and character types. We'll focus more on tuples and lists a little later on, but not particularly right now, though. Any other questions?
When you used the deletion operator with the minus sign, Is that modifying our source data?
Good question. So when I used that negative and I got back a vector that excluded some values, the question is, did that kind of save as a new vector? Did it change our environment at all? And the answer is, I get to decide that myself. If I go back to my code over here, let me go back to what we did before, where I had temps here as a vector, and I decided to, in this case, access individual elements of it, like 2, 4, and 7. I instead wanted to remove those. If I wanted to actually update temps to remove those in future lines of code as well, I would need to reassign this vector. I would say temps is reassigned, in this case, the exclusion of these particular indexes here. So I'm first going to remove these elements, 2, 4, and 7, and reassign it back to temps. And now, below this line of code, temps will always exclude those values for me. A good question. OK. So we've seen how we can ask these questions in our code to determine which of these values are outliers. And in fact, we can use these logical vectors, these logical expressions, to actually figure out automatically at which indexes we had these particular values being true or false. We can use a function called which, where which takes as input this vector of logical values and tells me which ones are true, or more particularly, it tells me the indices of which ones are true. Here I'll run line 3, and I get back both 2 and 4. So it seems like if I look at the logical vector itself, which was temps less than 0, notice how the second element of this vector is true, and so is the fourth. So if I were to use which would tell me at which indices is this logical vector true. So pretty helpful now. But I'd argue that I'm not really asking the question I wanted to ask. Like I wanted to ask, is this piece of data an outlier? And an outlier can be both low or high. So here I've been focusing on outliers that are low, but I also want to find outliers that are high, like let's say greater than 60 degrees. So for that, I could use another logical expression, like temps greater than, let's say, 60. And if I run or evaluate this logical expression, what will I see? Well, I'll see false, 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 but I will see true for that 7th day, because that was a pretty high temperature there. So there has to be a way for me to combine, let's say, these logical expressions and ask the question I want to ask. And it turns out we can do so in R using what we'll call logical operators. Logical operators let us combine 2 or more logical expressions to ask a more complex question in code. Now you might notice that I asked the question, is this value less than 0 or is it greater than 60? You often want to combine logical expressions with this idea of and or. And in fact, R gives you a way to do just that. Here I have 2 symbols. One is the ampersand, and one is this vertical pipe. The ampersand represents and. I can combine 2 logical expressions and use an and between them with this ampersand. If I want to use or, for instance, I could use this bar here. This represents or for me. So for instance, let's say I wanted to ask the question, is this temperature below 0 or greater than 60? I would put those 2 logical expressions on either side of this vertical pipe, and the pipe would symbolize that if either of those expressions is true, then the entire thing is true. For and, by contrast, both expressions on either side have to be true for the entire expression now to be true. And you can think of this a bit like English. Something is only true if this and that are true as well. Now, unlike our comparison operators that we saw earlier, these logical operators actually work differently for vectors of logicals and single logical values. So these single symbols, ampersand and the vertical bar, those work for vectors of logicals. If you have a single logical value that you want to combine between, you need to use this double character set here, ampersand, ampersand, or vertical bar, vertical bar. These work for the single value, true or false, whereas these work for vectors of true or false. So let's try actually implementing now this in code to see if I can get at my question now. How can I find the outliers in this data set? Well, here I have my 2 logical expressions, and I want to combine them to represent one larger logical expression. Well, as I said before, I'm interested in whether a temperature is below 0 or if it's above 60, just like this. So this now is my full logical expression, and I can evaluate it or run it if I do Command Enter on line 3. And now I'll see I've kind of combined my different expressions. I still see that these second and fourth values, this expression is true for those. They are less than 0. But I also see that on the element 7 here, that value is greater than 60, and so now that is true as well. If either of these expressions is true, less than 0 or greater than 60, I'll then see a true in this logical vector. And now I can go back to using which. I could use which to figure out at which indexes, which indices, these particular values are stored. So it seems like 2, 4, and 7. OK, so I think we're making some pretty good progress here. We've gone from using individual indices to now using entire logical vectors to automatically find for us at which places we have this condition being true. Some other functions to be aware of are these. One you might be curious about is this one called any. Any takes as input a logical vector and returns true if any of these values in that logical vector are true. So here I'm effectively asking not which values are outliers, but are any of them outliers? A yes or no question. And I'll get back in this case, yes, that some of these values are outliers. There are, in other words, some values true inside of this logical vector. I could also ask this question. Are all of these values outliers? Kind of a nonsensical question at this point, but you might use it in other cases. Are all of these values outliers? I can give this function, that same logical vector as input, run this, and I'll see false. No, not all of them are outliers. If any of them are false, I'll get back false. I need instead for all of the values in this logical vector to be true, for all to return true as well. All right. So one thing we might be wanting to do now is kind of tidy this up a bit. And so I could try to find those values in my temps vector by now using these logical expressions. And I could write as follows, temps bracket, and then in this case, let me go ahead and say which, and then let me type in the logical expression we decided on earlier. I'll say temps less than 0 or temps greater than 60. And now what will happen is, first, I'll evaluate this logical expression, finding all the values for which this expression is true. Which will convert that into some set of indices, at which point I'll pass those into temps. And now if I run line 3, I see my outliers without me going through the data myself. I could also decide to remove these values. If I tried to use a minus sign here, let's try this out. And I should see that same result, but now just dropping or removing those outliers altogether. But it turns out that which here is actually kind of redundant, that R allows me to do the following. I could actually index into my temps vector using nothing other than a logical vector. And what R will do is give me back all of the elements for which this logical expression evaluates to true. I think it's worth visualizing this, and we'll call this taking a subset with a logical vector. So let's imagine, for instance, we have our vector called temps and our logical vector now called filter, for instance. And notice how the values, both false and true in filter, align with those values I either want to keep or remove in temps. The values I want to remove, well, those align with false. The values I want to keep, those align with true. So now, instead of writing to temps some numbers, some indices to subset this vector, I could provide this logical vector instead, filter, just like this. And I'll mark those values to either kept or removed, aligning now with that true or false value we saw in filter. And once I complete this subset, I'll be left only with those values that aligned with true or those values I wanted to keep, -15, -20, and 65 now. When I come back to RStudio, I will go over to my console, and why don't I try just running this line of code as it is. I know that this logical expression evaluates to a logical vector. If I wanted to, I can make this more explicit like we did on the slides. I could say my filter here, as if I'm trying to remove some values but keep others, is this evaluation here. And now, inside of temps, I can put filter just like this. And now if I run line 3, inside of filter is this logical vector. I can then use this logical vector to subset, to access some elements of temps but not others, run line 4, and now I get back those particular outliers. Okay. Now, what questions do we have on these logical vectors and using them in this case as a way to index into or take a subset of our vector here? All right, so seeing none, let's go ahead and keep going, and let's introduce one more thing here. So I promised that we would try to actually remove these outliers altogether. And one thing I've done so far is I've found the outliers and put them in their own separate vector. I haven't actually removed them. Now, one thing that's helpful when you work with these logical expressions is the idea of kind of inverting the result you've gotten. If I get a true value, maybe I actually want to get the opposite, like a false value. Here, I could do the following. Let's say I want to filter to only those temperatures that are actually not outliers. This logical expression here represents a element being an outlier. I could, though, negate this and say I want to find a value that actually is not an outlier by putting in front of this exclamation point here. This exclamation point means not. It takes a true value and converts it to false, or a false value and converts it to true. So let's try this. I'll run line 3, just like this, and I'll update my logical vector. Now I'll run line 4, and I'll see that now I'm actually getting access to only those elements that are, in this case, not outliers. So again, this value, this exclamation point, this symbol, allows us to take a logical expression that evaluates to either true or false and negate it, get the opposite of that. In this case, true, or in this other case, false. All right. Let's see what else we can do. I'll come back to my RStudio over here. And one thing we also did is we kind of wrapped this logical expression, in this case in parentheses. This allows me to treat the entire thing as 1. Notice how I had 2 here, 1 temps less than 0 and 1 temps greater than 60. In this case, though, I wanted to negate the entire thing, so I wrapped that, in this case, in parentheses. And now I think we've kind of solved our problem. We've gone from, in this case, using these individual indexes to creating, in this case, a vector that excludes those outliers altogether. Now let's complete our analysis. I'll go ahead and try to save, at this point, a vector that doesn't include outliers. And I'll call it no outliers. So I'll go ahead and take my vector, temps, just like this, and I'll try to find, again, those values that were not outliers. I'll index into it using my logical vector, temps less than 0, or temps, in this case, greater than 60. And negating that, that means that this logical vector is taking the opposite now. And I could, if I wanted to, then find a vector of outliers, just like this. Temps, and then bracket, and then saying temps less than 0 or temps greater than 60, now not negated. And now I have 2 vectors, one that excludes the outliers and one that includes the outliers. And now, finally, if I wanted to save these vectors here, I could use this function called save that, similar to load, allows me to create an R data file instead of loading it into my environment here. If I type save, I can also then give save the actual vector I want to save to this R data file. I'll save, let's say, no outliers. And then the next argument is one called file. I could say file equals, and then say no underscore outliers dot R data. And if I run this line of code, line 6, I'll now have in my file explorer this data, R data file that says no outliers. I'm able to now save exactly this vector to my computer. And same thing now for outliers. I could save that one to a file called outliers.rdata as well. And I would argue this is our entire program, to open and load some vector, to find those outliers and to remove them, and now finally to save them to their own separate files. I could run this entire file with source up here and get all these results saved to my computer. Now before we move on, what questions do we have on these logical vectors or on this saving and loading of R data files?
Do we have if statements in the R?
Yeah, good question. So you may have heard in other languages of these things called if statements that let you ask questions in other ways. We'll actually see those in a little bit as well. Let's take one more question here.
What kind of data files is the type R data? Is it like a CSV file or?
Yeah, a great question. So A difference between a CSV file and an R data file is that a CSV file, at the end of the day, is just plain text. You can open it and see the text you have in your data file separated by commas. An R data file, though, lets us save an actual R data structure, like a vector or a data frame, to a file and load it and put it back into our environment. So an R data file is not plain text, but it does allow us to save an actual vector of data, a data frame, and make it easy to load that data later on. So R data files are particular to R and its own data structures, a way of organizing data, like these vectors and data frames, unlike a CSV, which can be used across many different languages altogether. A good question. Okay, so we've seen here how to remove unwanted pieces of data and how to do so using these things called logical expressions. Up next, we'll see how to take subsets of data and find those pieces of data we're actually interested in and ask questions of that piece of data instead. See you all in 5. Well, we're back, and so we previously saw how to remove unwanted pieces of data, like these outliers, using these things called logical expressions. Up next, we'll see how to apply those very same tools to now entire tables of data to find some subset of that data we're actually interested in. Now, to do that, we need to introduce this next data set, which is a data set involving these very cute baby chickens. And in particular, we have a table of data here, where each row represents an individual baby chick and how they grew up over 2 weeks of the very beginning of their lives. Here, notice how in every row represents a single chick, and every column has some piece of data about that chick. So here, line on column 1, this chick column represents a number for each chick, a way of identifying each chick uniquely. Now, this feed column tells us what kind of food that baby chick ate over the course of 2 weeks, and then this weight column tells us how much they weighed in grams at the end of the first 2 weeks of their life. Notice here how the feed column has food like casein, which is kind of like a protein, fava, which is like a fava bean if you're familiar, and then the weight column has their weight, in this case, in grams. So in this case, chick 1 seemed to have eaten casein and weighed 368 grams at the end of the first 2 weeks of their life. Now, one thing we'd be interested in is figuring out, well, what is the average weight of any given chick in this data set? We could certainly do that. We could look at all of the values in the weight column and average those and come to the conclusion that the average chick weighed, well, some amount, right? But I'd argue it's more interesting to find how much each chick weighed depending on what they ate. Like how much, for instance, did the chicks who ate casein weigh, and how much did the chicks who ate fava weigh? And what does that tell us about which food is more nutritious for these baby chicks? So let's see how we can use these same tools of logical expressions to now subset a data table like this and ultimately figure out these different averages across these individual different food groups. Let's come back to RStudio here, and I'll aim to create now a program that can subset this data and find for me the average weight of these chicks based on the kinds of food they ate over time. So why don't I create a new file here? I'll do so using file.create, and I'll call this file chicks.r for these baby chicks that we're going to grow up and see how they do. So now I'll open my File Explorer, and I'll see I have this chicks.r file along with a new file called chicks.csv. So my data in this table is stored inside of this file called chicks.csv. Why don't I go ahead and open this, and I can do so in the same way we saw last time using this function called read.csv. So I'll type read.csv and the name of the file I want to open, in this case chicks.csv. And of course, read.csv will return to me a data frame, that is a table of data that is now represented in R's own format. I'll say that this data frame is called chicks. And if I run line 1, I'll now have that data frame stored in my environment pane. If I want to view this, I could use that same function we saw earlier, view, and I could then give chicks as input. And now I see I have my table of chicks and the various foods they ate. So true to the slides here, we have individual chicks numbered to represent that individual particular chick. We have different kinds of feed or food the chicks were given. I see casein, fava, linseed, which is like flaxseed if you're familiar, meat meal, which involves various kinds of meat, soybean, the actual plant bean, and sunflower seeds. And here we have our weight column. Now I'll notice that unlike on the slides, like below fava here, I do seem to have some NA values, like the linseed value seems to be NA. Same with this one here for chick 9. Same for 11 and 12. Now, these NAs could mean a variety of things. They might mean we didn't measure this chick. They might mean we measured it incorrectly and didn't want to include that data. But regardless, NA, as we learned last time, stands for not available. There could be some data point here, but there isn't. So we'll probably need to handle that as we go through and do this analysis here. Now, I'll go back to my chicks.r file. And one thing I could do just off the bat is figure out how much do the chicks weigh on average across all different kinds of feed. If I wanted to find that out, I could use the mean function, as we saw just a little bit ago, and then give it as input the vector representing the weight column in chicks. And so here, all I'm doing again is accessing the weight column of chicks, which, as we learned last time, is a vector. Mean will take that vector and hopefully produce for me the average weight of these chicks. I'll run line 2, and I'll see NA. Well, let me go back to my data table again. I mean, I see NA values, but why do you think I would get an NA now if I try to find the average of the values in the weight column? Let me turn it over to our audience here. Why do you think I would get NA if I have NAs in the vector of weights I'm trying to find the average of?
I think because it's grouping the other values.
Yeah, so it's kind of, you'd say corrupting other values in some way, or it's trying to maybe modify them in some way. Now, one thing in particular about these NA values is that they mean something special. There should be data here, but there isn't. And if you're doing statistics or data science, that's actually a really good indicator that you should make a deliberate choice about what you want to do about those values. You could remove them, you could substitute some new value for it, but what you shouldn't do is just ignore them and treat them like they don't even exist. And so R has a way of telling me now, look, you have NA values here, you need to make a decision of what you want to do in order to actually compute what you're trying to compute. So one thing I could do, which feels most natural, I think, for this case, is simply remove those NA values. And if I wanted to do that, I could actually use one of mean's other parameters, which I learned from documentation, called na.rm. So recall from last time, if I want this function to have more than one argument, I separate each with a comma. I'll say comma here, and then na.rm equals, it turns out from the documentation, na.rm is either going to be equal to true or false. na.rm stands for whether I should remove rm these na values before I compute the average. By default, na.rm is false. I won't remove them, but if I don't remove them, mean won't know how to handle them and so can't compute the mean. But if I were to remove them instead, that is to make this parameter, this argument, true, well, then I would be able to compute the average because I will have dropped or removed those NA values and then computed the average from the rest of those values that are in my weight column. So let me run line 2 here, now that the na.rm parameter is set to true, and I'll see that the average weight across all the chicks seems to be 280.77 grams or so. So a healthy weight for these chicks. Now, what I argued was more interesting was the idea of trying to find how much the chicks weighed depending on what they ate. And we could use that to figure out what is the healthiest kind of meal for these chicks. Well, one thing I might be interested in first is how much on average do the chicks who ate casein weigh? But for that, I'm going to need to only deal with the chicks who ate casein. So one way to do that would be to subset my data frame, only find the rows for which the feed column is equal to casein. Well, as we saw last time, there is a way to do this based on the indices of this particular data, of the rows here. Notice how on the left-hand side I have individual numbers for each of these rows. These are the indices of these rows. If I wanted row 1, well, I could use bracket notation and ask for row 1. If I wanted row 2, I could do the same thing. So I'll go back to my chicks.r code, and I'll try that as like a first step towards this. I'll say chicks as my data frame. And we saw last time that we can use a bracket notation to access individual values or elements of this data frame. Now, because a data frame is 2D, it took two values, one for the row and one for the column, two indices to represent the position of the row we want and the position of the column we want. Turns out that by convention, the row number comes first, followed by the column number, separated, of course, by this comma. So if I wanted the first row, I could do this, 1 here, that first row, and I want all the columns, so I'll leave this part blank. If I run line 3 now, what will I see? Well, I'll see, just in this case, row 1. Now, like our vectors that we saw earlier, these data frames can take more than just individual indices as input. They can also take a vector of indices. So let's try that. I'll give, in this case, chicks, a vector of indices that will then return to me all the rows for which the feed column equals casein. That seems to me, just based on eyeballing here, that it's these rows, 1, 2, and 3. So I could use the 1, 2, and 3 here, create a vector of those values, and then get back, in this case, all 3 of those rows. So now I have indexed into my data frame's rows, now using a vector, and I've gotten back all the rows that I care about. So why don't we call this one, at least for now, casein chicks. Why don't I actually try to save this particular smaller subset of my data frame in this object called casein chicks, and now if I wanted to find the mean or the average weight for those chicks, I could use mean, but then I could ask for the weight column from the casein chicks data frame, this subset of our previous data frame. So now I'll run line 4, and I'll see that the casein chicks seem to weigh significantly more than other chicks, 379 grams on average. Now, what might we want to use now that we've seen how inefficient this might be? Well, as we saw before, I often don't want to use individual indices. You could imagine me, the programmer, going through and trying to find, okay, well, 1 through 3 is casein, 4 through 6 is fava, 7 through 9 is linseed. That's not how I want to spend my time. There is a very minor improvement I could make to this, which is as follows. I could actually represent this same vector with the following syntax. I could use 1, 3. I've saved myself a few keystrokes, and I've gotten, in return, the very same vector. This colon here, when it's between two individual numbers, gives us a sequential vector, all numbers between 1 through 3 inclusive. And I can prove it to you in the console. If I ran this line of code down below, 1, 3, hit enter, I'll see I get a vector, 1 through 3 inclusive. Maybe I could do the same for, let's say, the chicks that are eating fava. Well, I could go 4 through 6 and get back those particular row indices, but at the end of the day, I'm still actually defining the indices at which this particular condition is true. I could rely on something better. I could probably rely on these logical expressions and use those instead. So what kind of logical expression could help us out here? Well, we might notice that we really care about those chicks for which the feed column is equal to casein. So I could try to make a logical expression that involves this feed column of chicks. Why don't I try that? I'll go back to chicks.r, and now I'll try this logical expression here. Chicks and the feed column therein, when is that equal to casein? So recall that this is my logical expression. And because one part of it includes a vector, I'll get back a vector of logicals, of true or false values. Let me evaluate this expression by hitting Command Enter. And now I'll see I get back this vector of true or false. And it seems to me, if I look at this vector over here, that these first 3 values in the feed column are equal to true. True, 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 are equal to casein, in fact. So true, true, and true, these are equal to casein. The rest, though, are not. They're false. Now, one thing to notice when you're working with data frames is that really these elements of this particular column called feed, these kind of correspond to the rows of the data frame. Like if I go back to my visualization of my data frame, I might notice that the first 3 values in the feed column, well, those correspond to the first 3 rows in my data frame. And similar to vectors, data frames can actually be subset with logical vectors. So let's see how that could work here. I have to keep in mind this relationship between the first elements of my column and the actual rows of my data frame, but I think we'll see how we could use these expressions to help us subset this data frame. Why don't we visualize it a bit like this, where before we had seen that we had a data frame called chicks, and we could access it using bracket notation, entering in the indices for the rows or for the columns. But if I had some separate logical vector, like the one I just created, and I called it, let's say, filter, just for simplicity, I might notice that all of those same trues and falses, the way they align now with the rows of my data frame. So here, for instance, this logical vector was created by comparing the values of feed with casein. Those first three values were in fact equal to casein, but the kind of revelation here is that these same elements now correspond to rows of my data frame. I could take this very same logical vector and put it into the place where I would actually ask for the different rows of my data frame, and I would get back the following, something like this. I would mark, so to speak, certain rows to be kept at the end of this execution here, and certain rows to be removed, and I would ultimately end up with only those rows for which the logical vector evaluated to true. I would have, in fact, a subset of my data without touching any of the actual individual indices. So let's try it in R. I'll come back to RStudio here, and I will do as follows. I will try to prevent myself from using these individual indices, and I will instead use this logical expression. Similar to the slides, why don't I just call this logical vector filter, just like this. And why don't I run line 3. Now I have, in the case of filter, what do I have? I have a logical vector. Now I could use this logical vector to index into, to find a subset of my actual data frame here, if I use it instead of some individual indices to index into this data frame. Now if I run line 5, I'll have subset my data frame. And if I run line 6 now, I'll see exactly the same result. And I can even show you what casein chicks looks like. Let me show you in the console here. I'll see I in fact have the chicks that ate, in this case, casein. I could change this filter though. Let's say I want the chicks to eat something like linseed. I could use linseed here. And now let me rename casein chicks to linseed chicks and find out how much they weighed, those chicks who ate linseed. I'll rerun my code top to bottom. On line 3, I'll change my filter. I'll get back a logical expression representing those elements of feed that were equal to linseed. And then on line 5, I'll go ahead and subset my data frame again. And now I'll have only those chicks who ate linseed. And now could I find the mean if I run line 6? And so it seems like the NAs are still involved here. I need to now do the na.rm here, equal to true. I want to remove the NA values, and I could find on average how much those chicks who ate linseed weighed. Seems like it was 229 grams, that is. So let's go ahead and think through other improvements we could make to this program. Now, as I just saw, I don't want to have to write na.rm equals true every time I encounter these NA values. What I would love to do instead is actually just filter out these NA values to begin with. Maybe load my data set, but then as soon as I do, remove all the rows that have an NA value for the weight column. So for that, I could probably still use a logical expression, and one that comes to mind might be something like as follows. Let's say I want to figure out first which elements of the weight column, or really which rows in my data frame, are equal to NA, or let's say maybe not equal to. So I'll do chicks here, and I'll find the weight column of chicks, and I'll ask the question, which ones, in this case, are equal to NA? So I can maybe remove them later on. And you might notice that I get this little yellow squiggly sign in R and this little warning that says use is.na to check whether the expression evaluates to NA. I'm going to ignore that for now. I'm just going to run line 3 here and see what we get. I'll see I get a vector of NA values. And this has to do with the fact that R really wants you to know that NA values exist. If you have an NA value in your logical expression, it's going to make everything else NA, because R wants you to decide what are you going to do with this NA value. So it seems like this approach won't work. But thankfully, R does have other functions that we can use to be more deliberate about checking for NA values in some given vector or in some given data frame. Now in R, these are known as logical functions, functions that can return to us a logical value. And there are a lot of logical functions that are based on these special values we saw in R last time. You could imagine the is.infinite function. We saw last time there was a special value called infinite, or inf, that allowed us to represent a very, very large number. You could use is.infinite to test if some value is infinite. You could also use, as we just saw, is.na. Is.na looks at some given value and returns true if that value literally is na. If it's not, it returns false. Same for is.nan, or is.not a number. Remember that special value called nan? Well, this tests for that value. And same for null, that special value called null we saw last time. That will return true if we have the null value, or false if we don't. But I think the one we're going to care about here is is.na. So let's try that one out. I'll come back to my code over here. And why don't I try to use is.na on this weight column in chicks? I can pass as input to is.na this particular vector, this column called weight. And now if I run line 3, well, I'll get back a vector of logicals, a logical vector, and I should actually see which, in this case, elements of the weight column are equal to na. So it seems like, I mean, I might want to use which here, but it seems like 1, 2, 3, 4, 5, 6, 7. The 7th value seems to be na. Maybe the later one too. Let's actually use which for this. I'll come back to RStudio, and why don't I use which? Let's say which values, which elements of the weight column are equal to na, and I'll see that it is, in fact, seems to be the 7th, 9th, 11th, and 18th, 12th and 18th rows in chicks. Now that seems helpful, but I would ideally like to find those values that aren't equal to na and keep those instead. So if I wanted to negate this expression here, as we saw before, I could use the exclamation point, this not operator that says, if you gave me a false, give me instead a true. If you gave me a true, give me instead a false. So this will test which values are now not na in that weight column. I'll run line 3, and now we'll see we have more trues than falses representing all those values in our weight column that are not, in this case, na. So if I wanted to subset this data frame, I could use the same kind of trick we saw earlier of realizing that these individual elements of this vector correspond to the rows of my data frame. And I could subset, in this case, chicks as follows. We'd say chicks and give it this logical expression, which in fact returns to me a logical vector, and then use that logical vector to subset the chicks data frame to now only include those rows that in this case have a weight that is not equal to na. Now it would be good for me to maybe save this as the most recent version of chicks. Now on lines 1 and 2, I'm loading the chicks data frame, and I'm now saying immediately I'm going to remove any na values in the weight column just like this. So now when I use mean later on, I won't need to use na.rm because I'll know that all those na values in the weight column are gone for good. Now there is one more way to subset these data frames, as opposed to using this logical expression that is kind of serving as like an index into this data frame. There is actually a function called subset that works on data frames and takes both a data frame and a logical vector as input, returning for us all the rows for which that logical expression is true, that logical vector evaluates to true. So let's try this. Why don't I instead use subset here? I want to subset my data frame to only find those rows where weight is not equal to na. Well, I could still use subset. I could use subset here, which means the subset function, and I could pass as the first input to subset the chicks data frame. And now as the second input, the second argument, I now need to give it a logical expression to evaluate, to see which rows to keep and which rows to exclude. Now one thing is, I could say is not is.na. So this means any row that is not equal to na, and I could then give the weight column of chicks as input. notice here the syntax is a little bit different. I no longer need to use the $sign notation to actually access the row or the column of chicks. I instead just type in the column itself. And this works because subset takes as input the data frame. It will assume if I say wait, I'm talking about, in this case, the column in chicks. So this should have the same result. If I run line 1 and then line 2, if I view now chicks, I should see that all of those weights that were previously NA are gone from my data set. I could even use this, let's say, later on to figure out how much on average the chicks who ate, let's say, soybean weigh. Why don't I use subset again? I'll make an object called soybean chicks, just like this, and I will then subset the chicks data frame, the latest version of it, and I'll try to make sure that, in this case, the feed column equals, what do we say? Soybean equals soybean. Again, because I'm now using the subset function, I don't need to tell R that the feed column belongs to chicks. Subset will do that work for me. I can just give the column name and ask, where is it equal to soybean? And now subset will return to me all the rows in chicks where this expression is true. Let me run line 4 then, and let's see what's inside of soybean chicks. We'll see that now I have that subset of my data frame. And I could now run analyses like mean to determine how much on average did those particular chicks weigh. All right. Now, one more thing to keep in mind is that if I were to view this chicks data frame, just like this, if I'm being very astute, I might notice something a little bit off about it. So I have the individual numbers representing each chick here, but data frames in R also have what's called row names, individual indices for our rows. And if I wanted to find those row names, I could use this, row names, as a function. And I could run row names on line 4, and these are the row names of this data frame. Now, if you're being a little observant, what do you notice? Now that we've run line 2, what might be missing from these indices of our data frame? 1, 2, 3, 4, 5. What are we missing in the end?
I think it's the NA or not available variables.
Yeah, so we're missing, in this case, all of those row names that previously corresponded to those rows that had an NA value in the weight column. So we have 1, 2, 3, 4, 5, 6. Oh, and where's 7? Well, 7 we saw earlier actually had an NA value in the weight column, so we removed it. But it's really not good practice for me to actually have these row names not now ascend one after the other in sequential order, to have these missing values here. So I need to reset them. And I can do that using a special value that we saw earlier called null. I'll come back to RStudio here. And if I want to reset the row names for this chicks data set, I could do as follows. I could not just print row names or see what they are. I could assign them some value. And R has a handy trick where if I assign the row names of some data frame to be null, capital N-U-L-L, that will reset them to count sequentially, 1 up through the number of rows we have. Now null, remember, meant literally nothing. There's intentionally no value at all here. It means nothing at all. But when I assign this value to be the data frame's row names, it kind of gets rid of them, and R decides to build them back in. So let's try this. I'll run line 4, and now I'll check on the row names again, and I'll see that we're back to now being in sequential order. So whenever you take a subset of your data, consider updating the row names to make sure that things are staying just as they should, and you have the actual row names in ascending order to index your data, in this case, properly. Now, what final questions do we have on subsetting these data frames? What questions do we have?
So when you introduce the isNA function for and in conjunction with the which function, we had the indices that had NA on them on the weights vector. would we have an easy way to count how many NAs we had in the vector? Because maybe if we had a bigger data frame, we would have like a hard time counting the number of indices that it returned.
No, a really good question, Bruno. And so one thing you'd be asking yourself is, how do I figure out exactly how many NAs I had in the first place? Well, we can use a little handy trick of these logical values, the true or false values, which is that at the end of the day, a true corresponds to a 1 and a false corresponds to a 0. So let's actually see this in action, see how we can actually count up our number of these true or false values. I'll come back to RStudio here. And our question was, how many NA values did we have in the weight column of chicks? Well, we used, remember, is.NA to test and see which elements of the weight column were equal to NA. If I use is.NA here, I get back this logical vector. And actually, right now, all of them are false because I actually am still working with the updated version of chicks that removed those NA values. Let me run line 1, which will reload the CSV. And now let me run line 3, which now has those NA values added back in. Now I'll see that some of these values are true. That is, there are some places in the weight column of chicks that are equal to NA. Now, a useful trick when you're trying to count up these kinds of values is to keep in mind that true underneath the hood corresponds to the number 1, and false underneath the hood corresponds to the number 0. And I think if I were to do this, if I were to do in the R console as.integer, this value true, this would take the value true and show me its true integer representation. Let me run enter here. I see 1. Let me do as.integer for false to see what it really is underneath the hood. That seems like it's a 0. So I could take this vector of trues and falses, and I could sum it, just like this, where sum will allow me to count up all the possible values in here. And because true is always equal to 1 and false is always equal to 0, what I'll really get back is the number of trues that are inside this vector, or the number of values in the weight column of chicks that were equal to NA. So I'll run line 3, and I'll see that there were 5 values in chicks that were equal to NA. If I view chicks now, I think we should see that we count for ourselves 1, 2, 3, 4, and then down below 5, exactly 5 values of NA. So you can keep in mind this when you're trying to count up your number of NA values that you might have. Okay, we'll take a quick break here and come back to talk more about how we can not just choose the subset of data ourselves as programmers, but give the user more control over choosing which subset of data they want to see. We'll be back in 5.
Well, we're back, and so we've seen so far how to take subsets of our data, but what we'll do now is turn more control over to the user and let them choose a subset of data they want to see. Now, R in general has this idea of a menu, where you present the user with some options they could choose from. For instance, if we show them our feed data, we could ask them which subset of data they want to see. Is it the casein subset, the fava subset, the linseed subset, and so on? And the user could type in down below which number subset they want to see, whether it's 1 for casein, 2 for fava, or 3 for linseed. So let's go ahead and input something like this in R now and show the user the subset of data that they want to see. I'll come back over to RStudio here. And I actually already have a program typed up here, one that will implement a bit of this idea already. So notice here how I am still reading in my chicks.csv file, and now we're removing any weights that are NA, just like we saw before. I'm now going to determine which options I should show to the user. And I could do that using this function called unique, where I'll pass in the feed column of chicks and get back all the possible options that are inside of that feed column. And then, down below, what will I do? Well, I'll prompt the user with options using this new function we haven't seen yet called cat. Cat actually concatenates character strings and prints them out all at the same time. So here, I'll cat, or print, the 1 dot followed by the first feed option, probably casein in this case. Then, on the next line, I will cat 2 followed by the second feed option, which will be something like linseed, let's say. And I'll go through all of my possible feed options. And at the very end, I will ask the user to enter some feed type, some number of the subset that they want to see. So let's see this in action here. I'll go ahead and go to the top and click source now. And so something seems to be working here. I have actually the feed options being shown as I want them to be shown. But what I don't see are these options on new lines. Like I would rather have 1 dot space casein followed by 2 dot space fava, not all of these on the same line. So I think we'll need some new character here to solve this problem. And in fact, R does have a special character that we actually use to solve this problem. In general, these kinds of characters are called escape characters. And one escape character is this one here, \n, which if I were to use it, it won't print out a \n to my console. It will instead print out a new line. And this \t, well, this is actually a special one too. If I type \t, I won't see \t. I'll instead see a tab. So these are helpful for us. And in general, these escape characters don't actually print out the way you type them. They print out something special, like a new line or a tab or something else entirely for other escape characters too. So let's use now \n and see if that can help solve our problem. I'll come back over to RStudio, and let me now add in this \n to each of my cat functions here. I will also concatenate on each line this \n, just like this. And hopefully, when I finish typing all of this in, I'll be able to see each of these feed options on some new line of my console here. \n and \n. And all I'm doing here is essentially adding in some new lines to concatenate to each of my options. So let me clear my terminal down below, and I'll click source now. And now I'll see that all of these options are on their own new line because what I'm doing is first printing out 1 dot, then I'm going to print out the first feed option, then I'm going to print out this \n to move to that next line here, ultimately allowing me to see all of these options top to bottom. Now let's pause here and ask, what questions do we have on these escape characters or this program so far?
As we concluded from the first 2 lectures, I think programming with R is not safe enough because it saves arguments or variables. Then after it, you can't change it or you can't access the first element. So how we can program defensively with these available features?
Yeah, a good question, and I like the way you're thinking. Like, we need to think of how we can program defensively. And so one way to think defensively here is to think through what possible input the user could give us. If I look at this particular prompt, I offer the user that they could type in 1 through 6 here. But what if they typed in like a 0 or a 7? Like, they could very well do that. And so we'll see how we can actually handle those kinds of cases in a little bit. But first, I would argue that this, although it works, isn't exactly the best designed program we could write. I do have the right kind of menu for the user to see, but I could probably improve the design of my code too. So let's come back to RStudio and think through how we could improve the design of this code using R's vectorized features. So here, if you notice on line 9 through 14, there's no reason for me to type all these lines of code. And if you find yourself ever accessing one element of a vector after another just to print something out to the screen, you could probably think to yourself, there has to be a better way to do this. And in fact, there is. One thing that you might often think about is transforming your output to the user and turning it into a vector itself. So here I have all of my formatted options in terms of individual lines of code. But it would be really, really nice if I had a vector of these formatted options, and I could then pass that vector to cat, for instance. Now, cat can take a full vector as input and separate those elements with some character I tell it to. Now, for instance, I could, if I had this vector called, let's say, why don't we call it formatted options, and that is a vector itself, I could pass that vector to cat and tell it, in this case, to separate every element with a \n. And so long as this vector of formatted options included 1 for casein, 2 for linseed, and so on, it would then be able to print all of them out at once, separated by a new line. Exactly what we just did, but now using only 1 line of code. Now the challenge is, though, how do I get these formatted options in terms of their own vector, and how can I pass them, in this case, to cat?
Well, I think we need another part of our program now. I'll say, let's make a section to format our options, and to do so a little better than we did before. So I claim that ideally we want to create an object called formatted options that looks a bit like this. This object is a vector, and it includes for the user all of their menu options. So this is 6 total options, each one here, 1 for casein, 2 for fava, 3 for linseed, and notice how I've kind of appended these numbers in each case. 1 dot space, the food option, 2 dot space, the food option, 3 dot space, and the food option. Now I'm kind of noticing a pattern in this vector here, which is that for the most part, every option I have begins with a number, 1 to 6 down here. Then we have a period followed by a space in every element of this vector. And then the next thing I see is we have whatever food option corresponds to this particular option, like casein, fava, linseed, or meat meal. Now when you're using R, and you're using vectors, it really pays to think in a vectorized way. So I could actually think about this single vector as the combination of 3 different ones, these right here. Maybe I have one vector of numbers, 1 through 6, one vector of just that dot space, which I've quoted here to show the space, in fact, one vector of just those dot spaces, and one vector, which we already have, of those feed options to show to the user. And it would be really nice if I had a function to basically combine these various vectors into a single one, to take these 3 and concatenate them into one single list of formatted options. Now, you actually already know what that vector is. In fact, that vector, not that vector, that function, you know what that function is? That function is paste, and its sibling paste 0. Paste can still work with these vectors, but concatenate them now element-wise. So let's try using paste to vectorize our formatting here and improve the design of this code in R. I'll come back to RStudio here. And again, our goal is to create this vector called formatted options that has the number prefixed to each of our options to show to the user. Now, if I wanted to do that, I claimed we could use paste 0, but instead of giving paste 0 several individual options, I could give it a few different vectors. So maybe the first vector to give to it is the number vector. I want to first begin my input with those numbers, and so I could do as follows. I could say 1:6. That represents the number of the vector, the number vector that I have. If I go down the console here, I can prove to you that 1:6, that is in fact a vector of 1 through 6. Okay? Now the next part was to incorporate that dot space in the middle. And I claim, before I show you this, that I can actually get away with not putting this in its own vector, but instead putting it as a single value, and R will repeat that value for me, or recycle it for me, as we'll see. Then the third input in this case is the actual option that the user should see in terms of the feed options. So I'll type feed options here, which as we saw, if I go down our console here, is just a vector of the options we want to show the user. So visually, what I've done here looks a bit as follows. I've given as input to paste 0 these 3 vectors here. One of numbers, 1 through 6, one of this single element, dot space, and one of our feed options, casein, fava, linseed, and so on. And when I concatenate all of these together, I'll get back a vector of 6 elements, element-wise concatenating these here. So the first one seems pretty straightforward. I'll take 1, concatenate it with dot space, concatenate that with casein, and I'll get back 1 dot space casein. But the problem becomes, what do I do on this next element? Well, 2 concatenates with what? Turns out that R actually recycles this single value to the next element too, a bit like this. So now I'll concatenate 2 dot space fava, and I'll get 2 dot space fava. I'll recycle this value again for linseed, getting 3 dot space linseed, and recycle it again and again and again until I reach the end of the full length of these vectors here, getting in the end my full list of formatted options. So let me come back now to RStudio, and let me try to see what's inside of formatted options. Let me go over here, and let me first run, let's say, line 9. Let me now see what's inside of formatted options. And here we actually see our formatted vector of options to print to the user. Now, what questions do we have, if any, on how paste has now handled these vectors as input?
could we make our concatenation a little bit more flexible, maybe using the length of our feed options vector? Because maybe if we added another chicks that ate additional foods, maybe we could make it a little bit more adaptable. So that is my question.
Yeah, a good question about making our program more adaptable and flexible here. Let's go ahead and try to implement that and see what it could do for us. I'll come back to our studio here, and let's go back to our program. And I think you've rightly noticed that if we ever had more than, for instance, 6 feed options, this would no longer work. What's more flexible would be to actually dynamically find the length of the feed options we have, or how many we have in total. And I could do that using this function called length, just like this. And as input to length, I'll give this feed options vector, and length will return to me now however many elements are inside of that vector. For instance, if I go down to the console and show you what this evaluates to, I can clear my console here and type this in, 1 colon length of feed options, and I'll see 1 through 6. But if the length was ever 7 or 8 or 9 or 10, I would get back 1 through 7, 8, 9, or 10, making this more dynamic overall. So a great improvement to make here. I think there's still other improvements we can make, though. So if I were to run this program as a user, and I were to enter the feed type I wanted to view, like casein, well, I don't actually see anything. So I'll need to now figure out how to find the subset of data the user has asked for. Well, if I go down to the bottom of my program now, I could write that piece of code. And make a port here that says print selected option. And I'll go ahead and try to find the subset of data the user asked for. Now, they've given me a number, like 1, 2, 3, 4, 5, or 6. I'll probably need to convert that to the feed option they hope to see. So why don't I make a new object, one called selected feed, like this, that will really take the user's number and convert it to the actual character representation, whether it's casein or linseed or so on. To do that, I could still use the feed options vector, which has, of course, our feed options as characters inside of them. And maybe I could use as the index the user's number they selected. Because if they asked for number 1, they want the first feed option, or number 2, the second feed option, and so on. So here, I'll index in using the user's feed choice and get back now their selected feed as a character. And finally, I could print out the subset of data they had asked for. So I'll print the subsetted version of chicks where the feed column is equal to the user's selected feed, just like this. So now my program should hopefully work a little bit better. If I were to save it and click source, I'll now be able to type in, let's say, 1, and I'll see that subset that corresponds to the casein chicks. Let me go ahead and clear my terminal again and click source. And what if I did 2? Well, I'll see the fava chicks. That seems to be going pretty well for me. But as we've talked about, I think it's worth thinking defensively here still. So if I click on source, what if I were being malicious as a user and I type in something like this, 0? What do we get? I'll hit enter. So I won't see really a friendly output at all. I'll see this empty data frame, and I'll also see 0 rows or 0 length row names. Ideally, I would show the user something different, something like invalid choice, for instance. But to do this, I think we'll need more tools in our toolkit. I'll need to be able to respond to what the user has entered and take some other path in my program. Now, thankfully, in R, we have access to what are called conditionals, where conditionals let us run some piece of code conditionally, depending on whether some logical expression is true or false. We have, in particular, a keyword called if that will run some block of code if some condition or logical expression is true. So let's try out this if keyword here and see if it can help us out in our program. I'll come back to our studio, and maybe before we decide to show the user their selected subset, what if I were to handle this invalid case? I might do something like this. I could say handle, maybe invalid input, and why don't I use this if keyword? I'll say if, and then in parentheses, I'll supply some logical expression, some condition that if it is true, I'll do some code that will indent and put inside these curly braces here, this body of our if statement. So what should my condition be? Maybe if the feed choice is less than 1, so it's 0, -1, -2, or so on, or let's say, or the feed choice is greater than 6, just like this. I think that should handle things for us. And notice here, we're actually seeing now this double bar for the or, because we're comparing now two single true or false values, not a vector of values here. So what do I want to do if this condition is true? I want to tell the user that they entered an invalid choice, just like this. Let's try it. I'll go ahead and click source now. And notice how if I do enter a valid choice, like 1, I don't see that line of code that says cat invalid choice because this condition was not true. If it's not true, I won't do the code that is inside of these braces here. But what if this condition is true? I enter some number like 0. Let me try this. I'll click source, and now I'll type 0, and I'll see invalid choice, but I still see that output I didn't want to see. Now, why is that? Well, if I go back to my program here, and I read it top to bottom, well, it seems like if I enter 0, I will print out invalid choice, but then I'll still go on and show the subset that I didn't want to show in the first place. So thankfully, we do have other keywords that can make these conditions kind of mutually exclusive. Either do this or do that. And these keywords look a bit like this. We have one called else if and one called else. So let's use these here as well. I'll come back to my program, and what if I wanted to consider what I should do when the user enters a valid choice? Well, I don't want to print out invalid choice, and I do want to print out the right subset. So let's say in the case that the user has entered an invalid choice, I only want to print out invalid choice and not the subset that they want to see. I'll type else here, and now I'll make this kind of mutually exclusive. I'll take this code and put it here. And now what will happen is if the user enters an invalid choice, like 0, I will print out invalid choice, but I will not do the code that is now inside of this else block. Let me try it. I'll click source, and I will then type 0. And now I'll only see invalid choice. What if I did something else? What if I did source and I did, let's say, 1? Well, now I see exactly the right input. So these conditions here are kind of mutually exclusive. Now, we could use the else if keyword, which lets us say else and then ask if some condition is true again. Else if, let's say, maybe the feed choice is valid. I'll say feed choice is maybe greater than, or feed choice is between, let's say 1, so greater than or equal to 1, and let's say the feed choice is less than or equal to 6, so between 1 and 6 inclusive. This, I would argue, would still work. We're going to first check if the input is invalid, and if it's not, we're going to check if it is valid. So I'll click source here, and now I'll run top to bottom. I'll type maybe 0, and I'll see invalid choice. If I do here maybe a 1, I'll see the casein chicks as well. But I think this is a little less efficient than simply having just an else here. Well, why? Well, kind of logically, if the input is not invalid, it kind of has to be valid. So why should I ask this question again if it is valid or not? I could remove this if here and simply use an else, but an else if is good if you still have one more question you want to ask if some other condition is not true. Let me go ahead and clear this here and go back to what we had before. I'll click source, and now I'll clear my terminal. And actually, let me get out of this program. I'll type Control-C. Let me click source now. I'll type 1 for casein, see those chicks, and I'll type source again, click source again, and now I'll see 0, and I'll see invalid choice. So I think this is really the best designed version of our program yet. We can handle these various cases of user input and show the user the input they want to see, now making use of these conditionals. And so when we come back, we'll see how to combine data from different sources. We'll be back in 5. We're back, and so we've seen so far how to remove unwanted pieces of data from our data frames, from our vectors, and we've also seen how to subset our data as well. Now, we'll take a look at how we can combine data from different sources into one big data set. Now, for this, we'll introduce the idea of an e-commerce kind of data set, where here, let's say, some giant like Amazon is trying to keep track of customers and the purchases that they made. So here in this table, every row corresponds to some purchase made on something like Amazon.com. Notice how every customer here has their own unique ID. And one identifies me, and one might identify you, but at the end of the day, every customer has their own unique ID. Now, for every transaction, every checkout on Amazon, for instance, we might keep track of the sale amount, how much this user spent on Amazon.com. So it seems like user 9971, they spent $29 when they checked out.
user 7934, they spent $71, and so on. Now, when you have lots and lots of this kind of data, it might actually not be stored all in one table. It might be partitioned across several different tables, a bit like this. And it will be your job as the programmer to combine data from these different sources into one data set so you can answer and ask the questions you have about this data. Let's come back to RStudio and actually show an example of combining data from these different sources. So here in RStudio, I will create a program called sales, where I'm trying to combine sales data from different parts of the year. I'll name this file sales.r, and I'll create it. Now, if I go to my file explorer over here, I'll notice that I have that program sales.r, but I also have these 4 CSV files. It seems like one is called Q1, the other is called Q2, and Q3, and Q4. Now, we saw last time this idea of Q representing a question, like in a poll given to some potential voters. Here, though, Q means something different. If you're familiar with business, you might have heard of the fiscal year, kind of like similar to the calendar year, but the year in which they actually keep track of accounting and so on. Turns out that that year is broken down into 4 different parts called quarters, 3 months at a time. So Q1 stands for the first quarter in the fiscal year, Q2, the second quarter, Q3, Q4, and so on. So these are the 4 parts of the year of sales that this company had. Now, we were given this data in terms of each of those quarters. Why? Maybe a colleague just gave it to us like that. We need to figure out how to piece this data together now. So let's open up sales.r and see how we could accomplish that task. Come back to my computer here, and let me open up sales.r. And now, let me see if I can first read in each of these individual data files. Maybe I'll call the first one simply Q1 for the first quarter, the first 3 months of this fiscal year. I'll read the CSV called Q1.csv, and I'll do the same for Q2, Q2.csv, the same for Q3.csv, and now the same for Q4.csv, just like this. And now if I were to run all 4 of these lines of code, top to bottom, I could do so with source, and I would see in my environment now, I would see that I in fact have 4 data frames, 1 for each CSV. Let's take a look at one of them. So I'll view Q1, and I'll see the very same table we saw a little bit earlier. I'll see customer IDs in one column and sale amounts in the other. Remember, every row here represents some purchase that was made from this commerce company. Okay, so it seems like Q1 and even Q2, and even if we look at Q3 now, they all seem to have the same structure, the same number of columns, but perhaps different numbers of rows. And this is helpful for us. If we ever have data frames that have the same number of rows and the same names of same number of columns and the same names of columns as these have, we can combine them using a function called rbind. Rbind is typed like this. It's literally the character R and then bind. And R does not stand for R, the language. It stands for row. Row bind. We're going to bind the rows of these various data frames into one big data frame. So rbind takes as input several data frames to combine via their rows. I could first give it Q1, and then Q2, and Q3, and Q4. And now, if I save this result in terms of its own object called, let's say, just total sales for the year, if I run this line of code on line 6 and I view, let's say, sales, I should now see that I have a really big data frame. And to prove it to you, let me go look at my environment over here. Let me make this a little bigger over here. So you might notice that on the right-hand side, I have Q1 and Q2 and Q3 and Q4. Each one has about 2,500 observations, and now sales at the end has about 10,000 observations, or 10,000 rows. Really, it's the combination of each of these rows stacked on top of each other. But I think it's worth visualizing, too, exactly what we're doing with rbind. So let me show you some slides to depict just what we did here. I'll come back to our slides and show you, let's take 2 example data frames, one called Q1 and one called Q2, that we want to combine by their rows using here rbind. Well, what happens when rbind runs and takes in as input Q1 and then Q2?
Well, effectively, it takes that first data frame it has, and it keeps those rows at the top of this new data frame. But then it takes the new data frames, like Q2 here, and adds those rows at the bottom of this top data frame. For instance, a bit like this. Notice how I took Q2 over here and kind of added it, bound it by the rows at the bottom of Q1, making this one longer data frame. I've done this here for Q1 and Q2 and Q3 and Q4. I can give as many data frames as input to rbind as I want. All I'm doing here is adding row after row after row to make this data frame even longer. So let's go back into RStudio and let's see what is inside of my sales table here, the entire thing. I've lost a bit of information, namely in which quarter each of these sales occurred. Like, did they occur in quarter 1 or quarter 2 or quarter 3 or quarter 4? I don't know anymore. So we should probably be a bit careful combining these and instead first maybe add a column to each of these data frames. Maybe one called quarter that tells us exactly what quarter this sale was recorded in. So in the Q1 table, maybe I'll add this column called quarter. And recall from last time, if we want to add a column, we kind of wish it, quote unquote, into existence. I simply type the data frame's name, followed by a $, followed by the column I want to exist, and then I assign it some value. Now, in this case, I would love for the quarter column to just show Q1 for every single row. And if I want that to be the case, I need only type Q1 in quotes. And now, if I reread Q1 and run line 2, and now if I, let's say, view Q1, this data frame here, well, I'll see I have a new column called quarter, and throughout all the rows, I've set that column equal to Q1. So pretty helpful. But now, if I go back to trying to combine these data frames, what might happen? If I go down to line 8 now, I'll run line 8, and oops, I see an error in rbind, which tells me the number of columns of arguments do not match. And I think it's a little obvious what's happened here. So Q1 now has 3 columns, but Q2, Q3, Q4, these other arguments to rbind, those in this case only have 2. So we need to make sure we're combining data frames that have the same number of columns. We want to join them at least by row. So let's fix this. Let's go back to RStudio and let's go ahead and just make sure that every table has its own column called quarter, and that that column is equal to whatever quarter the sales appeared in. So Q2 for Q2, and then Q3 for Q3, and then Q4 for Q4, just like this. Now I can rerun this code top to bottom using source. I see everything work just as well. And now when I view sales, I now have that other column called quarter that can allow me to differentiate between individual quarters now of sales. So helpful when I combine these data frames to keep track of where each piece of data came from. Now, one kind of last flourish here, if we can actually show us another new feature of R, is going to be trying to categorize this data. So we combined it, but one thing I want to do is figure out which rows were particularly high value sales. Maybe my boss wants me to figure out which customers are spending the most money. Well, I ideally would want to create a new column and have it be based on the values of some other column. For instance, let's say this is our table again. This one called sales. I still have the same customer ID and the same sale amount, but now I want to categorize this data to add another column that tells me whether a sale amount was a high value transaction or if it was just a regular one. So this could look a bit like this. Maybe I add this column called value for the value of this sale. And if it's over 100, I'll mark it, I'll flag it as high value. But if it's not, well, I'll just make it a regular old sale. And this could help me later on find a subset of my data that includes only those high value transactions and those customers who spent more money than usual. So let's try to actually add in this value column. And it turns out that to do so, we need to make use of those same conditionals we just saw. Come back to RStudio here, and why don't we try this? Ideally, I might create some kind of logical expression on sales. I would say if the sales, the sale amount column,
is that greater than, in this case, 100? And if it is, well, I want to create a column that has high value for those particular rows, otherwise just regular. So let me run this particular logical expression, line 15, and I'll get back this really long logical vector. I see a few trues in there, so it seems like there are a few rows where you just spent over $100, but now my job is to create a vector that, if this sale amount was greater than 100, shows high value, and if it wasn't, shows just regular. Well, I could use a conditional, but I could use a special kind of conditional that R has, one that works really well with vectors and producing vectors as well. This is called if-else, as a function now. If-else can be a function, and its first argument is going to be the logical expression to actually evaluate for every row. So here I have sales, sale amount greater than 100, and if this is true, my second argument to if-else will be the value I want to see in the resulting vector. So I want to see high value here, and the third argument will be, what is the case that's not true, else in this case? I want to see regular. And now, with these three arguments, if-else will return to me a vector where if this condition is true, I'll see high value. If it's not true, I'll see regular. Let's try it. I'll run line 15, and now I'll see a similar vector, but now all of those trues are replaced by high value, and all of those falses are replaced by regular. So it seems to me like this allows me to create some new column for my data frame. I could then assign this vector as a column in my data frame. I could say sales, $, and then maybe I'll make a new column called, we called it value before. I'll assign that vector produced by if-else now to the value column in sales, and if I run this line and now view sales just like this, I should see that I now have this new column called value. And if I were to sort visually by sale amount to find those high value transactions, I would see all of those now are marked as high value. So we've seen here how to do a lot of things in this lecture, how to subset our data, how to use conditionals to take multiple paths in our programs, and finally, how to combine data from different sources. Next time, we'll dive even deeper into functions, writing some of our very own. We'll see you next time. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Goddard Tan, and this is our lecture on applying functions. We'll take a look at functions in particular, writing some of our very own, and we'll also learn about loops, how to repeat certain segments of code over time. Towards the end of lecture, we'll combine these two ideas to dip our toes into this thing called functional programming. So let's begin. Let's start by actually looking at another program we had from before, one called count.r. And if you remember, this program was designed to count up some number of votes we typed in the console. So if I click source here, I can run this program, and I'll enter in 100 votes for Mario, let's say, and 150 for Peach, and 120 for Bowser. And I'll see that all in all, I typed in 370 votes. So this same program from before. And I'd argue this program is correct. It works just fine. But there's an opportunity for improved design here. I could write this code a little bit better. And one thing I notice in particular is on lines 1, 2, and 3, I'm repeating some functionality over and over and over again. I'm asking the user for some input, converting that to an integer. I'm doing the same thing on line 2 and the same thing on line 3. And when you find yourself repeating this kind of functionality over and over and over again, it's a good clue that defining your own function might help you. So we want to define a function here, but how do we do so? We've certainly used functions before, but to create a function is something else entirely. Well, to create a function in R, we're going to use this keyword called function, followed by some parentheses. Now, you might also think, well, I want to give this function some kind of name that I could reuse throughout my program. So to give a function a name, I could use this syntax here. Maybe getVotes is assigned this function here. So getVotes now will be the name for my function because I want this function to, let's say, get some votes from the user. Now, this is pretty good. We have a name for our function, but what we'd also probably want is the ability for our function to take some input, some arguments, and run with those arguments. So if I wanted to change how my function runs, I could supply parameters inside of these parentheses here. I could supply any number of them separated by commas. But then, even with a name and some parameters, our function needs to do something. So to specify what our function actually does, we'll use these curly braces here in which we can define our function's body. That is, the lines of code that will run when our function is run. And down below, towards the end of these curly braces, we'll say what our function should return to us, the programmer, after it finishes running. So with this syntax here, let's actually go ahead and define our very own getVotes function that can ask the user for some number of votes. I'll come back to RStudio here, and let's write this function called getVotes. I want it to have the same functionality, essentially, as what I'm doing on lines 1, 2, and 3 here. But to define it, I'll first do so at the top of my program here. So I define it first and foremost, and then I can use it later on in my program. So I'll type, like we saw, get_votes. That's the name of this function. And I'll assign it to be some new function here. And I'll provide a function body just like this. So now I have my very first function in R, albeit an empty one, right? So I want this function, again, to get some votes from the user. So inside these curly braces, inside the function's body, I should define what code I want to run when I call or when I use this function later on in my program. Well, the thing I want to do is very similar to lines now 5, 6, and 7. I want to maybe ask the user for an integer, prompting them with something like, let's say, just enter votes for now, just like that. And I'll maybe assign the result to this object called votes that is now visible inside of this function for me. And once I get those votes from the user, well, I want getVotes to return them to me, the programmer, so I could assign them to some object like Mario, Peach, or Bowser down below. So to return some value from a function, I can use the keyword return, and inside parentheses say which object's value I want to return. So here, in total, is now my function. On line 2, I'm asking the user to enter some votes, converting that to an integer and storing it in this object called votes inside of this function. And then on line 3, I'm returning the value of votes so I can reuse it later on in my program. So now, I think I've implemented lines 6, 7, and 8 here as its own separate function. I should feel free to use that function now. On line 6, I'll actually not use as.integer and read line. I'll instead use get_votes and call it using these parentheses here. I'll do the same for line 7, get_votes, and line 8 as well. And now, before I run this program again, let's walk through top to bottom what I've just done. On line 1, I have defined this function called getVotes. I've told R exactly what inputs it takes, in this case, well, none. I've told R exactly what it should do when I call this function, first line 2, then line 3, and I've given it some name, getVotes here. So now, on line 6, 7, and 8, I can call getVotes. And every time I do, R will effectively go back to these lines 2 and 3, run those, and return to me the value that I've asked it to return for each of Mario, Peach, and Bowser. So now let's run our program. I'll click source here and enter in some number of votes. I think we had 100 first for Mario, so I'll say 100, and then 150 for Peach, and 120 for Bowser. And now I see the same functionality, but now in my own function. So congratulations, this is your first function in R. But if I'm doing this, I actually think I have lost some functionality, because if I run this program again, I'll see enter votes. And before, we had this nice ability to prompt the user with some particular prompt that we wanted to. So how could we get that back? Well, one thing we could define now is a parameter to this function, some input that changes how it runs. And as you saw, we can define those parameters inside these parentheses here after our function keyword. So one thing I want to do is be able to change the prompt that I prompt the user with. So I'll call this parameter prompt, just like this. And now my function can take this input called prompt. Well, when I do that, maybe I also want to use that particular prompt the user has entered, that I, the programmer, has entered as the input to get votes, and prompt the user with that instead. So now inside this function, I have access to this parameter, this argument called prompt, that I can then use to prompt the user on line 2 here. So
let's try this. I'll now give as input to this function Mario, like we had before, and Peach, like we had before, and Bowser, like we had before. Each time I call this function, I'm setting this character string Mario equal to prompt, and then prompting the user with that prompt now. Let's see what happens. I'll click on source, and now, instead of enter votes, I'll see Mario. I'll type in 100, 150, and 120, and I'll get back the same result. So pretty handy here to be able to define parameters for our functions and change them over time. Now, one optimization still we could make is that on line 3, I'm explicitly returning votes from this function, but it turns out that in R, by default, the last computed value, in this case votes, will be returned automatically for me. So on line 3, I actually don't need to explicitly say return votes. I could omit that, and R will by default return the last computed value inside this function, which is votes. So stylistically, we often want to avoid typing return when R by default actually does that for us for the last computed value here. Let me run this program again. I'll click source. I'll type 100 votes for Mario, 150 for Peach, 120 for Bowser, and now we're back in business. We have 370 votes in total. Now, let's say I get a little bit lazy as a programmer, and maybe sometimes I forget to enter in some value for this parameter we defined called prompt, right? I could go back to what we had before using these functions without any input. But now, because my function is defined as taking this parameter called prompt, I think I might run into some trouble. If I click source here, I'll see that I get an error. Error in get votes. Argument prompt is missing with no default. So if you're defining a function and you want the user or the programmer to need to define some argument to that function, well, you're going to need to do exactly what we did here, where if I define this parameter and don't give it a default, the user or the programmer must supply some value for it. But if I'm being a little bit nice and I want to maybe catch somebody doing this and provide them with some default value, I could do that too. Up here in function, I could say prompt and give it some default value. Maybe set it equal to, initially, enter votes, just like this. So now, if me or somebody else doesn't provide some input, well, the default value for prompt will be enter votes. Let me try this. I'll click on source, and now I'll see no error. I instead see enter votes. So even though we didn't supply some input to get votes here, we defined some default value that is used instead. So prompt, when there's no value supplied, is going to be equal now to enter votes, as we've seen down below. So pretty good. If I want to override this, as I might often want to do, I could do it as follows. I could go back to what we did before and type in some input, like Mario, or like Peach, or let's say like Bowser, just like this. And because this is the first input I've given to my function, and prompt is the first parameter, well, Mario will override, let's say, the default value of prompt, and same for Peach, and same for Bowser. There are a few ways to supply arguments to functions we've seen so far. One is positionally. Here, notice that the very first argument to get votes becomes the value for the first parameter, prompt. If, though, I had more than one parameter and more than one argument, I could define them separated by commas. So maybe this would be my first argument here, Mario, followed by a comma. I could then provide some other value for the next argument if I had one in my function here. But I don't, so I won't. The other way I could define the argument for a particular parameter is by actually using the parameter's name. So this name of this parameter is prompt here. I could override that and make sure to explicitly say that this prompt is going to be equal to Mario using syntax like this. I could say that get votes, I know, explicitly has this argument parameter called prompt that I'll set equal now to Mario. And same for Peach, and same for Bowser. So now I'm able here to run this code by supplying or overriding the default value now of prompt. So I think this is a pretty good first function. If I click source and I click run, I can do 100 votes for Mario, 150 for Peach, 120 for Bowser, getting that total back. But what's interesting that I notice now is if I go to my environment on my right-hand side, I'll see a few different objects that I have. I see Bowser, I see Mario, I see Peach in total, I see get votes, the function which we defined, but what I don't see
is this votes object, or prompt. And actually, if I go down to my console and ask R to give me the value of votes as it currently is, well, I'll see error, object votes not found. Now, why is that? Well, this has to do with what we call in programming this idea of scope. And scope tells us in what context objects like these are defined. To visualize this, let's think about our environment here and think about what scope we have in terms of our objects in that environment. So here is a representation of our environment. We have those 4 objects we saw earlier. Mario, Peach, Bowser, and Total. These are accessible to me, the programmer, pretty much at all times. We also have, of course, our function getVotes. But getVotes is kind of best viewed as this black box. I don't exactly know what's going inside of it when I call that function. If you think about calling a function like sum or mean, you likely don't know exactly what code was defined to compute those values. You just know that it kind of works. You give some input and you get that output back. Well, the same thing now with our own functions. We just have to trust that we ourselves have defined these functions, take some input, and produce some output for us, and we, the programmer, can actually access those objects we defined inside the function. If we want to use those, we need to kind of metaphorically zoom in or go inside that function's context to then be able to use and see those values, like votes and prompt. But for our sake, as the programmer, these objects are only defined inside the scope of now our function, which is why we can't see them in our global environment, as we saw in R. So we have now defined our first function. We've taken in some inputs, and we've returned some values. We've also seen this question of scope here. Let me ask what questions we have so far on scope or on defining our own functions.
What if the user enters a string or a character as an input? Is there any way to handle the errors that we get?
Yeah, really good question. So up until now, we've been kind of being a good user. We've been supplying numbers to the actual program here. But we need to think defensively as programmers and think about what could happen if we entered in something that wasn't a number, for instance. So let's see what might happen here. I'll come back to my computer, and let's go back to our program called count.r. And let me close my environment. But now, think a little more maliciously as a user. What could I do to break this program? Well, one thing I could do is enter in some value that I don't think the program expected to see. So if I click source now to run the program again, let me enter in something funny like duck for Mario, or quack for Peach, or cat for Bowser. And these are certainly not numbers. So if I hit enter now, ooh, this is some pretty bad output. So what I see down below is total votes is now equal to NA, this value that means not applicable. And I see some warning messages. Now, if I look at this particular one in get votes prompt equals Mario, NA is introduced by coercion. Well, what does that mean? Well, we saw a little while ago that coercion is this process by which we convert some storage mode to some other one. And it seems like we do that on line 2 on as.integer. We convert some character string the user gave us via readline to some number or some integer in particular. But what might happen if I did something like I did here? I gave cat instead of an actual number. Well, as.integer will say 1. I don't know what the heck you want me to do with that, so I'll give you NA instead. And it will also give me what's called a warning, telling me that, look, I couldn't do what you wanted me to do with the input you gave me. So this is why now we see this value NA as opposed to, let's say, cat or duck or quack instead. So what can we do to fix this? I think one thing we could do is try to catch this process. Like if we see inside this function that we actually gotten an NA value for votes, well, we could return something else entirely. We could start there. So let's go back to our program and make that happen for us. We could use what we saw last time called conditionals, where conditionals let us test for something and take some particular action because of that test. So here, let's assume the user enters in some bad value, like duck. And now votes is NA. I don't want to do what we did before, which was return votes automatically. I'd rather first ask, is votes NA? And if it is, let's go ahead and not return the actual NA value. Why don't we return something like 0, maybe, just to kick things off? If I say if now, if votes is NA, well, then inside, I could return some special value, like 0, saying that, look, we couldn't count your votes. But otherwise, let's say,
we could go ahead and safely return votes. So if votes is not NA, we can go ahead and return votes instead. And I think this will be a little bit safer for us. If I go ahead and click on source now, let me go ahead and type in duck for Mario, quack for Peach, and cat for Bowser. And so I seem to have gotten total votes being 0. Like, that's a little bit better. It's no longer NA. We seem to have just not counted, like cat, duck, or quack. But I still get these warnings. Now, these warnings we'll see a little bit more depth in a future lecture. R does have warnings and errors that are more generally known as exceptions, but for now, we can handle them using a function called suppress warnings. Suppress warnings allows me, the programmer, to say, look, I know something went wrong, but I'm handling it myself. I know how to do this. So let's see if we could tell as.integer to not give us a warning anymore, because we're handling it a little bit later. Let's come back to RStudio here. And I could use, like we said, this function called suppress warnings, where suppress warnings takes as input a function that could give us a warning, in this case like as.integer. So now, if I give as input this particular function, like this, suppress warnings, what I'm effectively saying is that as you take the user's input and you convert it to an integer, if you encounter a warning, don't give me that warning. Just kind of suppress it, keep it low, and I myself, the programmer, will handle it later on as well. So let's try this now. I'll click source, and I'll do 100 votes for Mario, 150 for Peach, and 120 for Bowser. And I think now we're back in action, although that was some good input, so let's try the bad input. Let's go ahead and do duck for Mario, quack for Peach, and cat for Bowser. And now we see total votes being 0, but now no warnings being raised thanks to suppress warnings. So we'll see this in more depth in a future lecture, but for now, just think about suppressing those warnings, kind of silencing them, because we, the programmer, know how to handle those in our own code. Now, there's one more improvement I see here, which is that this block from line 3 to line 7, this if-else, could be simplified, could be converted to one line of code. And in fact, if you have an if-else statement, where inside the if and inside the else, you're simply returning one value or another, well, you could simplify this and use a function called if-else, just like this, where the first argument to if-else is the logical expression to test. In this case, is votes NA, just like this. And if that expression is true, if votes is NA, well, the second argument will be the thing we return, the value we get back from if-else. And then the third argument will be what we get back if this logical expression is false. It's the else in if-else. So I'll say votes here instead. So now, to be clear, line 3 is doing exactly the same work as lines 5 through 9, but it's much shorter, I would argue more readable, and so I can now get rid of lines 5 through 9 and shorten this function even more. And because R will return to me the last computed value, if else, whatever it returns will be the return value of my function itself. So if votes is NA, if else will return 0, but so will my function, and same with votes as well. So let's try this again. I'll click source, and let me go ahead and say something like duck for Mario, but I will enter in maybe 150 for Peach and cat for Bowser, and now we see our total votes is 150. And I think we've really simplified this function for ourselves here. Now, as we've done this, I think you're seeing the power of putting this functionality inside of a function. If I hadn't done this, if I had had to repeat this code over and over and over again, my code would have been much longer. You could imagine myself repeating that same conditional, if else, if else, if else, through all my prompts to the user. But by converting that code into my very own function, I can modularize things. I can make things easier to maintain and to update, which is why in the first place we would write functions like these. So we've seen how to write our very first function in R to handle some errors our user could present us with. What other questions do we have about defining these functions?
If we had the first version of our function get votes and that we were still not checking for NA values by version, would we need to actually store our computation in the votes object, or could we just return the value directly?
Yeah, a really good question. I think something gets at shortening this program even more. If we go back, rewind a little bit to maybe not handling these NAs that could be introduced, but instead just returning, let's say, whatever the number the user gives us is, I could probably shorten it even more. So let me go back to RStudio and show you what that could look like.
I will maybe get rid of this if-else here, and I'll instead maybe do this. I'll go back to what we had before, which was assigning this object votes whatever number the user types in. Now, I think you were asking, could we just get rid of this object votes? Could we simply have this, as.integer, read line, given some prompt? I think we could, because as.integer will still return for us whatever number the user has typed in, and therefore, because it's the last line of my function will instead return that value as well. So I'll click on source to run my program. I'll type 100 for Mario, 150 for Peach, and 120 for Bowser. And now I see the same result we wanted. I would argue, though, because we want to keep this value and test its actual its value later on, like was it NA or was it a number, we might want to actually store it in a separate object and then test that value a little bit later, like we did here. But a great question and a good optimization, too. OK, so our program is better. Like, it's certainly better than it was before. But there's still one thing I think that's missing, which is if I click source now and I type in maybe quack for Mario, I've missed my chance now to enter Mario's votes. Wouldn't it be nice if instead my program could reprompt me every time to enter in a number for Mario, and it won't stop, let's say, until I do comply. I enter in the number for Mario's votes. Well, for that, we'll actually need some new structure, one called a loop. And in just a few minutes, we'll come back and talk about how to implement these loops in our code. We'll see you all in 5. Well, we're back, and as promised, we're going to learn together about these things called loops. These structures let us repeat some code some number of times. Now, for this, I brought along a friend, the CS50 Duck debugger, which is great to talk to about my code, just about the illogic in my thoughts, but also great for thinking about loops. In particular, if you have a duck or any kind of object to squeeze, you can use that to think about how loops work underneath the hood. So let's go ahead and jump in and see what this duck can teach us about loops. So if you come back to my code over here in RStudio, I have a program that kind of simulates me squeezing this duck 3 times. For instance, like this. It's a bit more of a squeak than a quack, but we'll go with it for now. If I type source here, click source, I'll see quack, 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 me squeezing this duck now 3 different times. So putting what we just did physically now into text. So let's visualize this code in terms of a flow chart and see what it looks like. Well, here at the top of my program, I start it. I click source, my program begins. And the next step then is to say quack. Every arrow now indicates some next step in my program. Well, after I say quack 1 time, I squeeze once. What will I do but say quack again, just like this. And I'll quack again, just like this. And now I'm at the end of my program. I stop entirely. But let's say I want to quack my duck or squeeze it more than 3 times. If I have only this to work with, what might quickly become my problem? If I want to do this 5 times or 10 times or even more, well, I'd probably need to do a lot of copying and pasting. If I can come back to my code here to show you what I need to do, if I want to simulate squeezing this duck not just 3 times, but 5 or 6 or 10 or more, well, I need to copy line 3, put it on line 4, copy line 4, put it on line 5. And so on and so forth to repeat this code some number of times. Now, thankfully, we don't have to do this in R. And in fact, as programmers, you should be looking out for cases like these and thinking, I could probably use a loop instead. So let's see what kind of loops R offers us, what kind of keywords we could use to make a loop and to repeat this code some number of times. Well, one of the first loops we have at our disposal is one called repeat. Repeat allows us to repeat whatever code is inside of its curly braces infinitely, however many times we want it to. So let me go ahead and go into my RStudio again, and I'll type repeat now, this keyword, and I will then, inside of those curly braces, put this function cat, which will print to the screen quack. And before I run this code, let's visualize its flowchart to see how it might work. Well, here on my screen, I have this program. I'm going to start that program, and then I'm going to quack or squeeze my duck. And then I'm going to follow the arrow and quack, just like this. And then I'm going to follow the arrow and quack, just like this. And I'm going to go follow the arrow again. And I worry I might be stuck here for a very long time, because it seems like our next step is always to go back and to quack and to quack and to quack again. So before we dive into fixing this, let's talk a little bit of vocabulary. Now, what we've created here is in fact a loop. We're repeating this code over and over and over again. Now, each time we repeat this set of code,
we're calling that one iteration. So in other words, when I loop again and again and again, I'm iterating again and again and again. One iteration means one segment of my code, top to bottom, inside of that loop. And I think what we've created here is something called an infinite loop, one that will never ever end, because there's no condition telling us when to stop looping. So we'll need to figure out how to break out of this kind of loop and figure out what we could do to get out of it. Now, thankfully, R does offer us some keywords to do just that, so let's explore them now in R. If I come back to RStudio, we'll want to introduce these two keywords here, break and next. Break symbolizes breaking out of some loop. When R encounters that break keyword, it will end that loop entirely. It will stop wherever it is and end that loop. Next, on the other hand, says wherever you are in this iteration, go ahead and start the next iteration from the top. So let's try these out now in R. If I come back to my program, duck.r, I don't want to repeat this quack over and over and over again, but let's say I do, maybe accidentally, I click source now, and whoop, my computer is just stuck saying quack, 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 quack over and over infinitely forever. I could, if I wanted to, exit this program if I type Control-C. That means stop this program, whether we're in a loop or we're not. So that can save us, Control-C, but ideally I should consider a stop condition before I go ahead and repeat something infinitely many times. Now what could I do if I wanted to quack, let's say 3 times? One thing I could do is think about counting, like maybe on my fingers. If I want to quack 3 times, I could maybe start at 3, and if I have 3 here, I could quack. I could go down to 2 and quack again, go down to 1 and quack again, and then finally at 0, I'm done. I shouldn't squeeze my duck anymore. So one thing we could do is try to put this idea of counting now in code. Well, I could create an object to store the number of times I want to squeeze this duck. I could, by convention, call it I, and that will keep track of the number of times I want to iterate in this loop. So on line 1, I'll say I'm going to assign this value I to be 3. It's kind of similar to me holding up my hands and saying 3 fingers, for instance. And now, as I repeat this code, I don't want to repeat it infinitely. I want to have some condition under which I break out of this loop. And as we saw before with my fingers, maybe the condition is if I is equal to 0, well, at that point, I want to break this loop. I want to exit it and not loop anymore. But I shouldn't run this code just yet, because while I've set I equal to 3, like I have on my fingers here, what I haven't done is made a mechanism for actually dropping fingers, going from 3 to 2, from 2 to 1, from 1 to 0. So maybe after I quack, I'll go ahead and adjust the value of I. I'll set it equal to I minus 1, just like this. And then let's say maybe in the case that I is 0, eventually we're going to break out of the loop. But if it's not, why don't I go ahead and go to the next iteration? When we see the next keyword, we'll stop our current iteration and go to the top again to repeat our code, top to bottom, just like this. So the flowchart for this code looks a bit more like this. I'm going to start my program, and I'm first going to set I equal to 3, kind of like I did on my fingers here. Then I'm going to squeeze the duck, going to quack, subtract 1 from I, and ask a question. Is I equal to 0? If it's not, well, I'll go back up and I'll squeeze the duck again. I'll subtract 1, ask that same question, and if I ever get to ask that question and the result is true, well, then I'll stop my program. So let's visualize this here using some interactive stuff. I have my iPad here that can count, let's say, from 3, just like this, oops, 3, down to 0, let's say. So currently, when I is 3, what do? I squeeze my duck once, just like this. I'll then subtract 1 from I, where I is kind of this iPad here, where I subtract 1 now, and now I is 2. Well, I'll go back up and I'll squeeze again. I'll subtract 1 from I. Now I is 1. I'll ask the question, is I equal to 0? It's not, so I'll go back up again. I'll squeeze the duck one more time, and I'll subtract 1 again, and now I is equal to 0. So we'll stop our program. There will be no more squeezing of this duck. So this is one way to approach the problem of creating some loop and having it repeat a certain number of times. But R comes with other kinds of loops too. A repeat loop is great when you want to do something at least once. I want to squeeze this duck at least one time, but
if I only want to do it if some condition is true, or while some condition is true, I could use another kind of loop as well. This loop is called a while loop. A while loop lets us repeat some set of code while some condition is true. So let's see what that looks like now in R. I will remove what I currently have and instead implement this while loop. So if I want to make a while loop, I can use while, just like this, and I'll make a condition to repeat under. As long as this condition is true, I will repeat the code inside this while loop's curly braces. So I could say maybe while I is not equal to 0, I want to repeat whatever code is inside of this while loop. Well, I want to quack, so I'll say cat quack, just like before, \n, make a new line, and then why don't I go ahead and add back this kind of helper object I had called I. I is assigned the value 3, and after I quack, well, I'll subtract 1 from I just like this. I is now assigned the value I minus 1. So a bit shorter than our repeat loop, but I argue it would do the same exact thing now. So let's visualize what's happening in this program. Well, the first thing we do is we set I equal to 3, just like this, and then we ask the question. Before we do anything else, we ask the question, is I not equal to 0? If it's not equal to 0, if that is true, we're going to squeeze our duck and subtract 1 from I. And then we'll ask the question again. Is I not equal to 0? And if ever in our loop that question is false, that is, this condition is no longer true, we will stop, exit our loop entirely. So let's visualize this now. I was first set to 3. So I'll set I here to 3. And now the difference is, before I do anything, I'm going to check this condition now. Is I equal to 0? Or is I not equal to 0? Well, I is 3, so yes, I is not equal to 0. I'll go ahead and quack, just like this, and I'll subtract 1 from I. Now I'll go back to the top of my loop and ask that question again. Is I not equal to 0? Well, I is 2, so it's not equal to 0. I'll go ahead and squeeze my duck, subtract 1 from I, and then ask the question again. Is I not equal to 0? Yes, it's not equal to 0. I'll squeeze, subtract 1 from I, but now when I ask the question, is I not equal to 0? Well, I is not equal to 0. In fact, it is 0, so I will exit my loop altogether, squeezing my duck now 3 times in total. So let's visualize this. I'll come back to RStudio now, and if I run this code by clicking source, I will have quacked exactly 3 times, counting down from 3, 2, and 1. OK. So just as we have counted down, we could also imagine counting up. Maybe I start I at 1, and my condition now is to loop so long as I is less than or equal to 3. Like I could imagine 1, 2, 3 times, but not 4. So I'll say, while I is less than or equal to 3, I want to keep quacking. But now I need to actually increase I as I go. On each iteration of my loop, on each run from the code, top to bottom, I want to increase I by 1. And now let's visualize what this is doing in terms of a flowchart. Here, very similar idea, but we're starting now from 1. I equals 1, and we'll ask this question. Is I less than or equal to 3? If it is, we'll squeeze our duck and add 1 to I. If it's not, as we go back and approach that question again at the top of our loop, if it's ever not the case that I is less than or equal to 3, we'll stop. We won't loop anymore. So again, let's visualize this. But now I is first set to 1. So before we do anything, we ask the question, is I less than or equal to 3? It is. We'll squeeze our duck, add 1 now to I, and ask the question again. Is I less than or equal to 3? It is. I'll squeeze, add 1 to I. Now it's 3. Is 3 less than or equal to 3? Well, it's equal to, so I'll go ahead and squeeze, add 1 to I, and well, now it's 4. And 4 is not less than or equal to 3, so we'll go ahead and stop our loop and not loop anymore. I'll come back now to RStudio, and I will show you what this looks like now. If I click source, I'll see quack, 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 again quacking 3 separate times. So we've seen now 2 kinds of loops in R, one called a repeat loop and one called a while loop. Let me ask, what questions do we have about these loops so far?
how could we decide when to use repeat or when to use while, or it doesn't matter?
Yeah, really good question. So in general, as we'll see, a repeat loop tends to be good when you want to do something at least once. You want to quack at least once. You want to prompt the user at least once, and then check if you should repeat or not. A while loop is good if at the very beginning, before you do anything else, you want to check some condition, and you want to repeat that code while some condition is true. So you could think of a repeat being like, do this once, but then check if you should do it again, whereas a while loop is more like, if our condition is true, we should be repeating this code over and over again. Really good question there. All right, let's keep going. And one more loop we have available to us in R is one called a for loop. A for loop lets us do some piece of code for each element in some list or vector of elements. So instead of now using the while keyword, I could use the for keyword. I could say for, and it turns out that inside of the parentheses of a for loop, I need a few different components. I need still some kind of helper object to keep track of each iteration, but I also need some vector of elements to do some piece of code for each vector in that element, or each element in that vector, sorry. So I'll say for I in, and then have a vector here. Let's say 1, 2, and 3. And now I have, the same as before, my body of this loop, where inside of it, I want to quack just like this. Now notice there's no need for me now to increment or decrement I, to add or subtract 1, because this is all taken care of thanks to our for loop. What the for loop will do is first set I equal to 1, and then it'll say quack, and then set I equal to 2, and then quack again, and then set I equal to 3 and quack again. But then at the end of this vector, once there are no more elements to iterate over, well, our for loop is done. So I, as it iterates, kind of assumes the value of 1 and then 2 and then 3. And if I were to click source now, I would see quack, quack, and quack down here in my console. Now, I could simplify this just a little bit more. I could maybe make a vector that's going to be a little more dynamic than this. Like I can imagine myself typing in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to quack 10 times now if I were to click source here. But that's going to get really tedious if I want to quack more than, let's say, 3 or 4 times. So what I could do instead is use our syntax to give me some vector that is between certain numbers. So 1:10, for instance, would say, give me a vector that includes 1 through 10 inclusive, which I can show you in my console here. 1:10 gives me 1 through 10 inclusive. With this, could I actually change how many times I loop? If I click source, I'll see 10 quacks. If I change this to 1:3, well, now I'm able to see quack, quack, quack down here in my console. So a for loop is going to be the tool for you if you have some list, some vector of elements to loop over, and then you want to do some piece of code for each of those elements there. OK, so now we've seen the 3 kinds of loops in R. We've seen repeat loops, we've seen while loops, and we've seen for loops. Our next step will be to apply these same loops to improve the design of our programs. We'll come back in 5 and do just that. See you all soon. Well, we're back, and as promised, we're now going to explore how we could apply functions to make the design of our programs even better. So let's pick up where we last left off, writing this program called count.r. And we left off with this idea of wanting to re-prompt the user any number of times until they comply with whatever kind of input we want, in this case, a number. So we saw just a little bit ago that a repeat loop is a great loop to use when you want to do something at least once and then check if you should do it again or break out of the loop. Now, in this case, I do want to prompt the user at least once. I want to tell them to input some number at least once. If they don't comply, well, then I'll loop again, but at least I want to do it once. So I could use a repeat loop here, and I could use it in the same way we just saw, using the repeat keyword followed by some parentheses or some brackets just like this. And then inside those brackets, inside of this loop's body, I could be sure to prompt at least once just like this. I will ask the user for some number of votes and store it in this object called votes. But now, I don't want to run this code because this will make an infinite loop. I'll be constantly asking the user to enter in some number of votes, so I need some condition under which I would break out of this loop. And I think that condition might be
if the votes we receive is not NA. If we get back some valid number of votes, that will be not equal to NA. If we do get some weird input like duck, though, that will be NA, in which case we should keep looping. So let me ask the question, is votes, in this case, is it not equal to, is votes not equal to NA, just like this? And if it's not, well, we're going to break out of this loop. We're going to say, look, we're done. Votes is not NA. We don't need to ask the user anymore. Alternatively, if votes is NA, we could continue on to the next iteration. Now, there's one improvement here, which is that technically, when we get to the bottom of this repeat loop, get to its last curly brace in the body here, it will automatically go back up to the top, do the next iteration from the top of its body. So I'd argue that this extra next here isn't really needed. We're going to go to the next iteration regardless if we don't break out of this loop altogether. And now I think we have a good loop going. I'm going to ask the user for their votes. If, in other words, this is a valid vote, a valid number, we're going to break out of the loop, not prompt them anymore. And what can we do? Well, now we don't need to check if votes is NA, because if we get down to line 8, we know votes is not NA. I could simply return votes overall. So here I think is a better implementation, one that will prompt the user again and again until they enter some number of votes that we actually want. Let me go ahead and click source, and let me type 100 votes for Mario. But now, maybe I'll type duck for Peach, and I'm reprompted. OK, maybe I type quack for Peach. I'm reprompted. Maybe I'll now comply. I'll say, OK, 150 votes for Peach. And now we move on to Bowser. So this seems to be working here. I'll go ahead and type 120, and now I'll see my total votes was 370. Now, one more improvement is that it seems to me a little extraneous to break out of this loop and then return, because a return actually signifies that no matter where we are in our function, we're going to stop the function altogether and return the value we have. So it seems to me like I could move this return from line 8 to inside of this if statement. And now, if votes is not NA, if we have some valid number of votes, we'll not just break and then return, we'll go ahead and just simply return, because a return would, by nature, break us out of the loop anyway. We're going to stop this function altogether. So let's try this again. I'll save my program, click source. I'll type 100 for Mario, 150 for Peach, 120 for Bowser. And now I think we're in good hands if we have good input. But if I type source, let me go ahead and do duck for Mario. I can prompt it again, maybe quack for Mario, maybe 100 for Mario. Now I think we're doing well with invalid input as well. So pretty good. One other thing we could do, though, is think about these lines, 10 through 12. Well, it seems to me like for each candidate that I have, I want to get some number of votes for them. Notice how I said for each candidate. Well, if we want to do something for each candidate, for each item in some list or some vector, well, a for loop might be a great tool for us here. Why don't I go ahead and try to make a for loop now? I'll say for, as we saw before, this helper object called I. For I in, well, I want to prompt the user for every candidate that I have. And although we just saw for loops being used with numeric vectors, vectors that include like 1, 2, 3, 4, and so on, we can also use for loops with non-numeric vectors. I could give a vector of the candidates that I have and know that a for loop will loop over each candidate in that vector. So I could do something like this. I could say for I in a vector of my candidates, Mario, Peach, and then Bowser. And then I'll provide the body of this for loop. Now, what do I want to do in this loop? Well, each loop, I will first be assigned some new element to my vector. First it will be Mario, then Peach, then, not Bowser, just like this. And then I want to, in this case, ask the user for some number of votes on each iteration. First for Mario, then for Peach, then for Bowser. So I could probably simply call get votes, just like this, and maybe store it in some object called votes, like that. But now the question is, how would I show the user the right prompt? Like, I can't type in Mario here, because then Mario would show up with a prompt on every iteration of my loop. I need to make it more dynamic than that. One thing I could do is take advantage of how this object I is actually assigned the value of each element on each iteration. So on the first iteration,
I will be equal to Mario. On the second iteration, I will be equal to Peach. On the third iteration, I will be equal to Bowser. So I think I could use that to my advantage. I could take the candidate name, let's say, and maybe add in dynamically this colon space with, let's say, paste 0 like we've seen before. I could say paste 0. I want to paste together the candidate's name followed by colon space. So now, on each iteration, I will first be equal to Mario. We'll get votes for Mario by prompting the user for Mario's votes. Then, on the next iteration, I will be Peach. We'll prompt the user for Peach's votes, followed by a colon space. And then the same thing for Bowser. So I think I could get rid of, let's say, this code down below here. But what am I left with? Well, it seems like on line 14, I was summing up Mario, Peach, and Bowser, but those objects don't exist for me anymore. I only have this one value now called votes, which seems to get changed every iteration. Like the first it will be Mario's votes, the next iteration it will be Peach's votes, the next it will be Bowser's votes. What ideas do we have for how to solve this problem? Any ideas for how we could maybe count up these votes while we go through our loop?
First, I think we should put it inside the for loop or return the sum.
Yeah, so a good idea. Like we still want to return their sum. And I like what you're thinking about trying to do this within the for loop. One thing that comes to mind is maybe trying to keep a running sum. That is, let's first get Mario's votes, add them to our total, then get Peach's votes, add those to our total, then get Bowser's votes, add those to our total, and at the end of our loop, we will have a total number of votes to count up. So let's see this in action in R. I'll come back to RStudio here, and if I can't have separate objects now for Mario, Peach, and Bowser, well, no problem. What I could do instead is start my count a little bit earlier. Maybe I'll set total initially equal to 0. So before I loop, I assume, well, there are 0 votes. But then, on each iteration of my loop, what will I do? I'll ask the user for some number of votes for the candidate, whether it's Mario, Peach, or Bowser. And then, down below, I'll add those votes to the total. I will update total to be, in addition to include the total plus the new votes we've received. So I think I could get rid of now line 16, and let's think through what this is doing line by line here. Well, first, total is 0. And if I go into my loop now, I will first be equal to Mario on this first iteration. So I'll prompt the user for Mario's votes and store them in this object called votes. Let's say it's 100. On line 13, I take this object called total and update it. I add Mario's votes to it. If Mario had 100 votes, total will be now 100. Then I'll move on. I will then become Peach, and I'll ask for Peach's votes now. Well, if Peach's votes is 150, on line 13, I'll again say 100, which is the current value of total, plus 150. That's the new value of total, so 250. And you can see how we're kind of keeping a running track of our number of votes for each candidate. We'll do the same for Bowser, and I think at the end of this we will have a total number of votes for every candidate. So let me go ahead and click source now, and I'll see if I type in 100 for Mario, 150 for Peach, and 120 for Bowser, we still now have our total, but now using this loop. So I'd argue we've made our program a little more efficient using these loops and easier to read, easier to change as well. Now, what questions do we have about this program as we've written it? We've added in a few loops, a repeat loop, and a for loop. What other questions do we have about this program? Seeing none so far, so let's keep going here. And one thing else we can do with these loops is think about how we could apply them to other problems. So one problem we saw a little bit earlier was this problem of working with a table of data that had our candidates' votes in it. So if you recall, we had a table that looked a bit like this, where for each candidate we had the number of votes they received at the polls, this physical location, and the number of votes they received in the mail. So it seems like Mario received 37 votes at the polls, the physical location, and 63 votes at the mail. But then our question was, well, how many votes did each candidate receive? That is, for each candidate, what was the sum of their votes? And then for each voting method, like poll or mail, well, how many votes did we receive overall in those columns too? So to visualize, let me grab my clicker over here. To visualize, let's say that we wanted to find Mario's total votes. Well, we would just sum up the row for Mario here, And then if we wanted to find the total number of votes we received at the poll or in the mail, we would sum up each value in these columns here. So notice how, again, we're saying for each candidate or for each column. We want to sum up those votes. Well, we could probably use a for loop to accomplish this same task now. Let's go back to R and see how this could work. I'll come to RStudio, and let's make a new program, one that is called tabulate. Let me go ahead and I think I might have it open already. I'll click on tabulate here, and I'll see a blank file called tabulate.r. Now, my goal is to read in this CSV of votes that we have, one called votes.csv. So I'll use read.csv, and I'll try to open votes.csv. If you look in my file explorer here, you'll see I do have a file called votes.csv. Now let me click source here to run this program, and I should now be able to view votes, the data frame. So a similar thing to what we've seen earlier, but one thing is now different. Notice how in a prior lecture we saw we had a column called candidates. Well, now what we've done is we've decided that the row names for this data frame are the candidates themselves. So Mario is the name of this first row, Peach is the name of the second, and Bowser the third. This allows us to define our data frame as exclusively numbers. We could sum like 37, 63, 43, 107, and moreover, it allows us to better subset our data frame, as we'll see in just a bit. So let's say my goal at first is to sum up the number of votes for each candidate across both the poll and the mail. Well, in tabulate.r, I could start by doing that by making a for loop, doing something for each candidate. So I could say for candidate, let's say, in row names votes, just like this, and get a body for this loop. And what I've done here is I've decided that I no longer need to call this value I. I could call it candidate. I could call it really anything I want to, and I could use that inside of my loop here. The other thing I've decided is that instead of defining a list of the candidates, like in this case Mario, Peach, and Bowser, I could be more dynamic than that. I could decide to tell R that it should tell me what my row names are, what my candidates are, and allow it to iterate over those. So I'll ask for the row names of the votes data frame. And if I actually see them down in my console below, I'll see that I get a vector of Mario, Peach, and Bowser. So the same structure for our loop now, but different ways of asking for a helper object to iterate with and an actual vector of, in this case, candidate names. So now we have a loop to go over every candidate's name. And our next goal is to find out how many votes each candidate received across all of their columns here. Now the first thing to do might be to subset my data frame to figure out for each candidate which rows correspond to that candidate. Now we saw last time ways to subset data frames using the subset function, but now that we actually have this row name being equal to the candidate's name, we can make this even more efficient. Let me visualize this for you here. If we have our data frame called votes, and I want to find all of Mario's votes, well, if Mario is the row name for one of my rows in my data frame, I could simply use the name Mario in the place I would normally put the row's index. For instance, like this. If I say votes, bracket, Mario as a character string, because Mario is the name of one of my row names, I'll then get back the row corresponding to the name Mario. And same thing with Peach, and same thing with Bowser. So we're very quickly now subsetting our data to find each candidate's rows and their number of votes across all the columns here. Let's come back and try this out. I will show you in the console that indeed if I do type votes, bracket, Mario, and then comma space to say I want all columns, but only the row associated with the name Mario, well, I'll get back a single row from this data frame that includes Mario's votes. So if I can do this, at least in my console now with particular names, I bet I could do it in my for loop where candidate will stand in for any given candidate's name. First it will be Mario, then it will be Peach, then it will be Bowser on each successive iteration. So to subset this data, I could use votes, the data frame's name, followed by brackets, followed by the row name, in this case candidate, on each iteration updating, and then comma space, saying I want all columns for whatever row corresponds to this candidate's name on whatever iteration it is that we're on. So now that I have this working for me, I could probably put this into the function sum to get back the total number of votes across all the columns. If you give sum a data frame of one row, it will sum up all the values in that given row. OK, so now I seem to have the sum for each candidate's votes. But I still need some place to store it to look at it later. So one thing I could do is make this object called total votes, just like this. But what's the problem now? If I were to run this code top to bottom, what might I lose? And a question here is, what might the value of total votes be if I were to look at it at the very end of my loop? Any ideas here? Why can't I just leave my code like this? And what might be the last value of total votes, do you think?
Okay, the last value will be the sum of votes of the last candidate of the last one.
Yeah, the last candidate that we have in our list would be the final value of total votes. So let's actually test this out. If I go back to my RStudio here, and why don't I run this code by clicking source. And now let me check on the value of total votes, just like this. Well, total votes seems to be 120. Who had 120 votes? Seems like it was Bowser. But why is total votes equal to Bowser's total votes? Well, let's think about this going top to bottom through our loop. First, candidate is equal to Mario, and we'll subset our data frame to find Mario's votes. We'll sum those up across all the columns and store it now in total votes. But then we'll go on to the next iteration. Candidates will next be Peach, and we'll subset our data frame to find Peach's votes, sum them across all the columns, and effectively overwrite Mario's votes with Peach's. So now total votes is Peach's total votes. But then when Bowser comes along, well, Bowser will also overwrite Peach's votes. At the end of our loop, what do we have? Well, only one candidate's votes and not all of them. So it seems like we need some way of making a vector of these actual total votes. And we could do that using some new syntax in R. One thing I could do is initially make an empty vector, just like this, total votes, and set it equal to this, C followed by some parentheses. This is that same C function we saw earlier, but it means the empty vector, nothing, at least at first. And then in my loop, I bet we could add to this vector so we get back at the end not any single candidate's votes, but a whole vector of their votes. Now we'll need some new syntax for this and some new feature we haven't seen yet in R. But let's visualize what we could do with that syntax. So here is a visualization of the empty vector total votes. There's nothing here because this is an empty vector right now. But if I wanted to add some new element to it, and not just add the element, give it some name too, I could certainly do that. I could say total votes, bracket, and the name I want to give this element, and then assign the value for that element. So if I want to add to this vector, total votes, an element named Mario that has the value 100, well, I could do it using this syntax here. Well, what if I want to later add Peach's votes? Let's imagine this is the next iteration of our for loop. I would say total votes, bracket, Peach. And that would then make a new element in my vector called Peach with the value 150. And same, let's say, for Bowser. On my next iteration, I will add Bowser's votes. And now, at the end of my loop, let's say, I now have a vector of Mario, Peach, and Bowser's votes all together now. So let's try it. I'll come back to RStudio here. And let's try using this process of adding named elements to our vectors. Well, on line 5, I might say that I want to add to total votes a new element whose name is, well, whatever the candidate's name is on any iteration. So I'll say total votes, bracket, candidate, meaning that whatever the candidate's name is on this iteration, I want to add a new element with that name. And I'll give it the value of the sum of their votes. So if I click source, and now I go ahead and inspect the value of total votes by typing in my console and hitting enter, I'll see a much better output. I actually see each candidate's name in my vector, and I see the value now that they were assigned. 100 for Mario, 150 for Peach, and 120 for Bowser. So what questions do we have about this program as it exists now?
Could we, instead of adding the total votes in a named vector, could we add a new column to our votes data frame?
We absolutely could. So we could decide instead to make a new vector and add that as a column to our data frame. Just depends on what kind of output you want to do. So here we wanted this output of a named vector, but we could change this to, let's say, not supply a name to each element and instead just add some new element after element, much like this. Let me show you that real briefly here. I'll come back to RStudio. And let's say I don't want to give it some name. I just want to kind of add in successive elements here. I could say total votes becomes the combination of the current state of total votes, adding in this new element here. So a little bit tricky to parse, but let's see what happens here. I'll click source, and I'll show you the value of total votes now, just like this. And what do I get back? Well, a total votes vector that is Mario's votes, then Peach's votes, then Bowser's votes. And I could, if I wanted to, add this as a column in my data frame. I could say votes total, let's say, and then I could say make that the value of this vector here. So now if I run source, so I click source, I should see that I have this new column called total. And effectively what I've done here is if I remove this part first, is I've decided to start with this empty vector. And then on each iteration, I want to take whatever is in that current vector and simply append or add on some new element, which will be the sum of the current candidate's votes. So on the first iteration, we'll add our very first element to this empty vector here. But then on the next iteration, we'll have a vector of one element, and we'll add in one more element. On the third, add the third, and the fourth, add the fourth, and so on. So a good way to add vectors together using C as well. I hope that helps. OK, so let's go back to what we had before here. Let me do Command Z a few times to go back to our named vector. And let's see what else we could do. So if I click source, I'll see total votes again is exactly as you want it to be. But what if I wanted to sum up the columns too, to figure out for each voting method, how many votes did we receive? That is, for each poll and mail column, how many votes were there in those? Well, I could really just change my for loop. And instead of using row names, I could iterate over column names. So call names will tell me, if I go to the console, call names will tell me what columns do I have inside this data frame. And I could then change my loop appropriately. Instead of calling each column candidate on each iteration, I could call it maybe like voting method for the polling or the mail-in ballots. And then I could change how I subset my data frame. Instead of subsetting by row, I could subset now by column, like this. And I could then update the name of each of these elements to instead be the same name as the method we're counting. So pretty much the same idea, same flow, but just a different process across columns now. If I click source, I'll see in total votes that I've now counted up the total number of votes for each column. OK. So it turns out that this method of doing things in R, this kind of analysis, applying some function for every row and for every column, is so common in R that we actually have some family of functions we can use to do that same analysis. And as we move from this world of writing procedures, that is, specifying a loop like this and specifying everything we should do inside that loop, to relying more on functions, we'll enter into this world called functional programming, where in functional programming we can actually use functions to do the work of iteration for us. Now, one common hallmark of functional programming is applying some function across these individual rows and individual columns. So R gives us this function called apply. And if I wanted to have the same result we just saw with our for loop, but now using this function, I could use the following syntax. I could use this function called apply and give it 3 arguments. The first one is the data frame to work with. In this case, votes, as we see here. The next one is one called margin. And margin stands for, do I want to apply this function across all of the rows or all of the columns here? When margin is 1, that means apply some function across all of the rows. When margin is 2, that means apply this function across all of the columns here. And then, finally, the third argument to apply
is a function itself. And this is a hallmark of functional programming. We can pass functions as input to other functions. In this case, we're telling apply, here is the function I want you to use to basically work across all of these rows and all of these columns here. So when margin is equal to 1, what will happen? When I apply the function sum, well, for every row, I will get back a sum of every element in that row. When margin, though, is 2, what will I get? I'll get back the sum of every element inside each of these columns here, storing it, let's say, kind of at the bottom of our data frame here. So let's see this in action. I'll come back to RStudio here, and let's try to use these apply functions instead of doing things more procedurally, typing a loop and then everything I want to do inside of that loop. I argue I could actually write all this code in terms of a single function call using apply. Well, I want to apply this function on a given data frame, votes, as we just saw. I want to apply it across all of my rows, that is, for every candidate that I have in my data frame. And the function I want to apply is the sum function. I want to take all of these rows, and for each row, I want to sum up all of those values. Now, if I run this line of code on line 2, what will I get? The same exact result. I'll get now a named vector, Mario, Peach, and Bowser, these 3 elements here, with Mario being 100, Peach being 150, and Bowser being 120. Notice how, if I go back to my data frame, this is the same thing we had, where for every row, I've now found the sum, and apply has returned me the name of that row and the result of summing all the values in that row. Let's think about this too. What if I changed margin to 2? Well, this would find me the sum of every individual column, all the values within those individual columns. Whereas before we had to change row names to column names and change various other objects, now I can simply change 1 to 2 to work on columns here. Let me click source, and now I'll see if I go ahead and hit line 2, command enter, now I get back that same result, the names of each of my columns and the result of summing up all of their values here. OK. So we've seen a much better way now to approach this same problem. Instead of doing things procedurally, writing a loop and saying exactly what should happen in each iteration of that loop, I can rely on a function like apply, do a lot of that work for me. And moreover, I can pass a function as input to apply for it to use on each iteration that it goes through in my data frame. Now let me ask here, having seen these apply functions and how they work, what questions do we have about them?
My question, instead of using the procedural approach of like sorting or unsorting, are there any like existing function that I can use it on the data frame for sorting the data in the rows like or columns?
A good question. So one thing you might want to do is sort your data. R just come with a function called sort that can do just that. Let me show you a little bit of it here. If I come back to RStudio, let's say I want to sort this vector I'm given from apply. I could call this vector something like total votes, just like this. And let me run line 1 and then line 2. Now I have total votes being this vector of named elements across my columns. Let's say I wanted to sort these. Let me say I could use the sort function here, and I could type total votes inside as the input to sort. And now, if I hit command enter on sort, I should see, well, it's kind of already in sorted order, at least going low to high. But now if I type question mark sort to see how I could change the order here, I might see that sort has this parameter called decreasing, which is initially false, which means that we're going to count up instead of down. But now if I want to sort going low to high or increasing order, I could set decreasing, sorry, no, if I want to set the vector going from high to low, let's say, instead of low to high, I could set decreasing equal to true, and then we'll see this vector is now in sorted order. I can do the same for every candidate that I have. Let me update total votes across the columns. Let me now, on line 3, run sort. And now I have my candidates in sorted order as well. So a cool trick if you want to sort your data, now using this sort function. And you can change whether it goes up or down using this decreasing parameter here. So we've seen a lot today. We've seen how to define our very own functions. We've seen how to write our own loops to repeat code multiple times. And we've seen how to combine these two ideas, dipping our toes into functional programming, that is, using functions to do the work of iteration for us. When we come back next time, we'll actually see how to clean up our data, how to tidy it to make analyses like these even easier. All that and more next time. See you soon. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Goddard Tan, and this is our week on tidying data. Now, odds are you've seen just how messy data can get. Maybe your data is in the wrong format, or your table is the wrong shape, or maybe you have characters where you don't want them to be. Well, today we'll give you some tools to solve those problems and more by standing on the shoulders of those who've come before us. In fact, this problem of tidying data is so prevalent in R that many have solved it already. We can use their solutions in our own code. This code somebody else has written and that we can use is called a package. And we get packages that we can use from the CRAN, or the Comprehensive R Archive Network. You can also download the R code from the CRAN itself. Now we'll focus today on the tidyverse, which is a package, or really a collection of packages. Among them these, one called dplyr to transform data, one called ggplot2 to visualize data, one called stringr to work with character strings, and one called tidyr to actually tidy our data in the underlying structure that it might have. So let's go ahead and jump right in. We can actually install packages like the tidyverse using these functions here. Install.packages, and we can then load them later on to use them in our programs using this function library. So let's try it out and come back to RStudio here. I'll come over to my computer and let's open up RStudio where I have my console open. So if I want to install a package like the tidyverse, or a collection of packages like the tidyverse, I could do so with install.packages and then passing in the name of that package in quotes. So for instance, I could type tidyverse in quotes, just like this. And if I were to hit enter here, I would install tidyverse on my own computer. Now, once it's installed, I need to load it so I can use it. So I can use this function here called library, just like this, to pull the tidyverse from my library and load it into my own computer so I can use its functions and everything else therein. Now, you may have heard this term library before if you have programmed. In R, we call packages this code somebody else has written that we can use, and the library, the place those packages are stored on our own computer. So some slight difference in terminology there, but I can load this package now using library tidyverse. And I've already done that here, so I won't do it myself, but you can try it at home. Now, let's begin by thinking through what we can do with packages that come in the tidyverse. And we said before, there was one called dplyr, whose name is a bit of a play on these pliers. So maybe you've used pliers in the real world to bend something into shape, to make it the shape you want it to be. Well, it's a similar idea with dplyr, but now what you have are not these physical pliers, but actual functions we can use to manipulate and transform data. So let's see exactly what those functions are. We're going to have 6 of them actually. One called select, which we can use to select certain columns from our data frames. One called filter to filter rows. One called arrange to sort those rows. One called distinct to find unique rows. And one's group by and summarize to find groups in our data and summarize data in those groups. So we'll take a look at all 6 of these functions in turn in the context of some data set that comes built into dplyr, one that involves storms, particularly strong storms in the Atlantic Ocean region. Now, this data set comes from a group called NOAA, a US government agency that tracks storms and how they evolve. So we'll see in this data set that we have not just individual storms, but observations of those storms, of how they evolved over time and grew, so we ourselves can understand how they grow and how to better prepare for them too. So let's jump in and see what this data set looks like. I'll come back to RStudio here, and let's open up this storms data set. Now, because it comes built into dplyr, I can use it by simply typing its name. So in my console here, I'll type storms, the name of my data set, and I'll hit enter, just like this. And this is a lot of output, so let's walk through it step by step. Now, the first thing I see is that this seems to be what's called a tibble.
Haven't heard that before. So this seems to still be a table. I certainly have data in rows and columns, but this in particular seems to be what's called a tibble. Well, a tibble is a tidyverse creation, one that is similar to a data frame but more specialized. It gives us some features we can use to see this data better and work with it more easily. Now, one of the features is this prettier version of printing out what's inside our table. Here I can see a lot of rich information about this data set, so let's dive in and see what we're seeing here. Now, it looks like this tibble, after I see a tibble here, I see 19,537 x 13. And what does that mean? Well, this means I have about 19,000 rows in this data set. Well, what are those rows? It seems like they are individual observations of certain storms and how they grew over time. So here I see the first 10 rows. Looks like maybe a storm Amy. Then we have observations in the year 1975 and various months and hours and so on. Now I see x13 here, which means I have 13 columns of data to work with, namely the name of the storm, the year, month, day, and hour of the observation, the latitude and longitude, that is the location of the storm around the world, and then one called status, where status tells me what type of storm was this. Was it a tropical depression, a more minor storm, or was it a full-on hurricane, one of the strongest storms we could have? I also see this category column, which tells me for hurricanes in particular, was it a category 1 hurricane or a category 5 hurricane, where 5 is the strongest and 1 is the weakest. I see too this column called wind, which tells me the wind speed in this nautical term called knots. And I see pressure, which tells me how strong this storm was. And I still see that this might not be 13 columns. There are some that got cut off down below, so I'll see them at least named down here, 2 more variables. One looks like tropical storm force diameter and hurricane force diameter, these other terms that mean how strong this storm was on this particular observation. So this is our data set in terms of rows and columns. And notice too that the tibble shows us the type of these columns as well. So name seems to be a character, day an integer, status a factor like we saw last time. There's lots we can glean from this particular output of a tibble here. So let's jump in with a problem. And I'd say my problem is I want to try to find the strongest hurricanes and sort them from the highest wind speed to the lowest. Now, let's begin by solving this problem in little baby steps, working our way towards getting to that kind of data set we ultimately want to see. So welcome back to RStudio here, and let's think through what we could do first. Well, I want to write a program to do this work for me, so I'll make a new file. I'll call file.create and then storms.r, just like this. Well, I'll go over to my file explorer and click on storms.r and open up this file for me here. If I type storms, even in this file, I should have access to that same data set, so long as I have loaded the tidyverse using library. Now, if I looked at this table again, if I click enter here and see it, I think there are probably some columns I don't really want or need. Like I probably don't need latitude and longitude to figure out the ordering of the storm in terms of wind speed. I probably don't need pressure or these other ones called tropical storm force diameter or so on. So I want to get rid of them. And I can do so using a function that's part of dplyr. So let me go back to my file here called storms.r, and let me think through how I could do that. Well, one function called select actually lets us determine which columns we want from our table and which ones we don't. So I'll use select here. And because it comes from the dplyr package, one thing I could do is tell R explicitly, use the select function from the dplyr package as follows. I'll type dplyr first, the package name, followed by 2 colons, and the name of the function I want to use, just like this. So now this is saying I want to use the select function that is part of the dplyr package. This is not built into R. It's part of some package I downloaded, installed, and loaded here. Now the first argument to select is the data frame we want to work with, in this case storms. So I'll put storms here as the first argument, and the next one is a vector of the columns we either want to keep or remove. If I want to keep the columns, I can simply use C, just as it is here. But if I want to drop some columns or remove them, I could select them inside this vector and use either exclamation point or minus to say, I don't want those. I want you to remove them overall. So let's actually go with the exclamation point here and select the columns we actually don't want anymore in our data set. We said before we don't really want lat and long, nor pressure, nor one called tropical storm force diameter, nor one called hurricane force diameter. And my goodness, this line is getting really long. So I think what we should do is stylize our code a little bit. One thing we could do is put each of these arguments on its own line here. Let me move the first argument to its own line, the next as well to its own line, still separated by commas now. I'll put the final closing curly brace for select on its own line as well. So this at least makes it a little more readable. And now if I run this line of code, let's see what happens. Well, I'll get back still my tibble, but now with those columns removed. So select has then dropped those columns for me and simplified my data frame. But as you might have guessed, I was kind of annoyed I had to type out all of this tropical storm force diameter or hurricane force diameter. There is actually a better way, and select comes with a few helper functions we can use to select some of these columns. So for instance, some of them look like this. We have one called contains, which we could give a character string, and it will select for us all columns that contain that character string. Or ends with or starts with, which might select columns that end with or start with some given character string. And one thing I noticed, if I go back to my code here, is that both of these long column names end with diameter. So I could probably use ends with here as a helper function for select. So why don't I do that? In my vector of columns to select, why don't I use ends with and pass in the character string I want to match. So maybe in this case it will be diameter. And now this function, ends with, will match and include any columns that end with diameter. But of course, in this case, we're actually going to remove them because of our exclamation point here. And we should see that if I run this line top to bottom, we have the same result, but now in much fewer lines of code. Now, what should we do next? We have our columns chosen if we want them to be, but maybe the next thing is to work only with hurricanes. So I don't really care about tropical depressions or tropical storms. I want hurricanes in this data set. Well, that's a great job for filter. I've removed all the columns I want. Now I should remove some rows. So filter is good for removing rows and finding subsets of our data. It works very similar to subset like we saw last time, but a different kind of function name here. So why don't I try using filter, and I'll do so like this. Maybe I want to type dplyr, because it's part of the dplyr package here, and then filter. And the first argument to filter is the data frame I want to work with, similar to select. So maybe what I could do is pass in this updated data frame as the first argument to filter, just like that. And now, as the next argument, the second argument to filter, I can supply a logical expression, any kind that involves the data frame's columns. So if I looked at my table again, I would see that the status column tells me what kind of storm this was. So I could write a logical expression to say, I only now want those rows where the status is equal, in this case, to hurricane. Let me go ahead and run this and see if it works. I'll run this top to bottom. And now I see I've subset my data frame now to only those that include hurricane in the status column. Very similar to subset like we saw in an earlier lecture. Now, this is a good amount of typing so far. I have many functions involved, or really just two, but it looks like a lot. I could probably simplify this in two ways. The first one is I don't strictly need to use this syntax that tells R which packages these functions come from. I really only need to do this if I have two packages that have a function with the same name. Because if you have two packages loaded that have functions with the same name, R won't know which one you want to use. If instead, though, select is the only function I have in all my packages, I don't need to tell it that it comes from dplyr explicitly. So I could remove this as well as this up here, because filter and select are only part of dplyr. R can assume they come from that package. But I think a larger problem here is that if I were to want to do more with this data set, well, I'd need to keep nesting and nesting and nesting my code, and it's not exactly what I want to do. Already, I have to read from the inside out. I first select my columns, and I pass that to filter, versus maybe from left to right, top to bottom, which is what I'm more used to now. So thankfully, there is a solution in R, and this is called the pipe operator. The pipe operator looks like this, so one of these two options here, either the top or the bottom, and it allows us to pipe some value on the left-hand side as the first argument into a function on the right-hand side.
Now, there are two versions of the pipe operator. The first one was this one down below here, which is part of a package called the Magritar package, and that allowed people to use this pipe for the very first time in R's community, and people loved it so much they actually built it into R itself using this version up here. So nowadays, the most common version to use is this top one, but you might still see code using this bottom one. For our purposes, they are effectively equivalent. Now let's see an example of using this pipe operator here. Let's say I'm selecting some columns from storms, and I want to maybe do it like this, like I did before. I have storms as the first argument. I could rewrite this code as follows. I could take the storms dataset and pipe it into select. So now it is implicitly the first argument to select, and I can still name all my other arguments after this first one here. So storms is going to be passed into select, and I can still name the columns now I want to keep or drop. But this gets really powerful when I want to chain functions together. So here I'm going to select some columns. What if at the same time I wanted to filter some rows? Well, I could do this. I could say first pass storms to select, pipe it to select as the first argument, select the columns we want, and then pipe that result now to filter, which will filter through the rows we want to. And in the end, I'll get back the data set I was hoping for. Now I can read top to bottom, left to right, as opposed to from the inside-most function to the outside-most. So let's try this now and rewrite our code to be much more readable using these pipe operators. I'll come back to our studio, and let's try this out. As opposed to nesting these functions, why don't I use the pipe operator? I'll take storms again, just like I had, and I'll pipe it into select. Now, as we said, storms will implicitly become the first argument to select. So I no longer need to say storms anymore. I'll know that is the first argument to select. What I can instead do is just start supplying the second or the third arguments here. I could say I want to select, or really drop, these columns, lat, long, pressure, and all those that end with diameter in this case. And now I want to pipe that result, the columns I have actually kept now from storms, into filter. And of course, that will implicitly become the first argument of filter. Now I just apply the second argument, which is the logical expression. So in this case, where the status column is equal to hurricane, just like this. Let me go ahead and run this code. I'll click this, and we'll see the same result, but now in a much more readable format. So pretty cool what we can do with the pipe operator. Let me pause here and ask what questions we have on these packages, on the pipe operator, or select, or filter.
Is there any kind of joins like in SQL?
So a good question about joins, like we have those in SQL. And if you're familiar with joins and with SQL, you'd know that you can take different tables of data and combine them kind of column-wise if they have two columns that reference one or the other. Now it turns out you can do just that in R with a function called merge. There are also packages in R that you run SQL statements inside of your R code, but we won't focus on that in this lecture today. Let's take one more.
I wondered what output like CHR and DBL and the output of the Tibble represents.
Yeah, great question. So let's go back and look at our Tibble again. I'll come back to my computer over here, and let's see a little bit more this output from our Tibble. I'll run line 1 again, and we'll see the resulting Tibble, which is really just a table of data here. Let me full screen this so we can see it at large. As we said a little bit before, we have some output on the kinds of data we're storing in each of these columns, or the storage mode of these columns. Now name seems to be storing characters. CHR is short for character. DBL here is short for double, or some floating point value, some decimal value. Even though we don't quite see it here in the output, underneath the hood, year is storing actual floating point values, or decimal values. Same with month. Day seems to be storing actual integers, like whole numbers. And let's see, status here seems to be storing factors like we saw last time. So this data can have categories built into the vectors as well. So these are different abbreviations for the storage mode of whatever kind of data we're storing in each of these columns. But a good question to clarify the output of our Tibble here. OK. Well, let's keep going. And I think I've argued we've gotten pretty far already using just select and filter. But the next thing to do would be to arrange our rows in terms of the highest wind speed to the lowest. So let's see how we could do that. Now, if we want to arrange our data or sort it, arrange will be the tool for the job built into dplyr. So let's see what that could look like here.
I could simply pipe my result currently, after filter, into this function called arrange. And by default, the first argument to arrange is the table to work with, but now the pipe operator takes care of that for us. The next arguments then to arrange are simply the columns we want to use to sort our data. So if I want to sort by the wind column, maybe highest wind to lowest wind value, I could give as input to arrange the wind column, just like this. No quotes, nothing, just the wind column name. Let me go ahead and run this now and see what we see. Let me pull this up again, and we'll see, certainly seems to be arranged by wind, but these seem to be some pretty low wind numbers. So I think what's happened by default is arrange has taken the wind column, sorted our rows by it, but done so in ascending order, from the lowest wind value to the highest all the way down below. What we really want is descending wind order, so the highest wind values first and the lowest later on. So let me go ahead and go back to my program here, and let me try instead doing this, DESC, parentheses around wind, just like that. And that will take the wind column and make it in descending order, which will pass to arrange. And now arrange will be able to sort our data set in descending order by the wind column. Let me go ahead and run this now, and we should see that we have what we wanted. Wind now, the highest values at the very top, and we see we go lower and lower and lower as we go lower in our data set, at least in terms of the wind column. So pretty good, we're getting there. One thing I still see though is that, let's say some hurricanes have the same wind speed like Gilbert, Wilma, and Dorian have. Well, it would be nice if when within hurricanes that have the same wind speed, we also sort by name. So ideally, like Dorian would be first in this group, and then Gilbert, and then Wilma. Well, we can still do that with arrange as well. We could give arrange not one column to sort by, but two as well. Maybe first sort by wind, like we just told it to do, but if any two observations of hurricanes have the same wind speed, well, we could tell it now to sort by the name column. And by default, it will sort alphabetically by name. But if I wanted to do reverse alphabetical order, I could do DESC with name as well. So let's do alphabetical order, just like this. And now I suspect we'll see that our rows will be first arranged in descending order by wind value. And then if any two rows or observations have the same wind value, we'll sort those alphabetically by name. Let me go ahead and run this line here and pull it up, and we'll see exactly that. So it seems like those observations that had a wind value of 160, those are now sorted by name as well. Dorian, then Gilbert, then Wilma. So we're making some pretty good progress here. One last piece, though, before we get to our final output, which was the hurricanes sorted by highest wind speed to lowest. And maybe you notice it too. So here, what I really want are single hurricanes. But what I have are observations of hurricanes. I have many observations per any single hurricane, and it seems like I have duplicates here. I have Dorian here at least twice. I see Allen in here many times. And so my goal is to really remove those duplicate values and end up with one observation for each hurricane. Now we've seen how to select some columns, how to filter our data, how to arrange the rows. But if I want to remove duplicates, we need to rely on a new function, one called distinct, which is also part of dplyr. Now I can probably pass all of this output to distinct down below, but I think it's worth visualizing first what exactly distinct is doing for us. So let's do just that with some slides. Over here, we've seen this distinct function, but what can it do? Well, here, let's consider this example data set that includes two distinct storms. One named Anna that happened in the year 1979, and one named Anna that occurred in the year 1985. These are two distinct storms, and it seems like we have 3 observations for each of these different storms. Now I could use the distinct function to get back, ideally, the 2 distinct storms in here. 1 row for each of the 2 distinct storms. Now, I could pass, like we saw before, this storms example table to distinct. And if I were to run it, well, what would happen? By default, distinct tries to find duplicate rows in my data. But then the question is, how does it know which rows are duplicates? Well, by default, distinct looks at all the values in all the columns and determines if a row is a duplicate when it finds all those values in all the values of another row. So let's do step by step here. Row 1, Anna, 1979, 50. Do I see all 3 of those values anywhere else in this table on a single row? I don't. Let's go to the next one then. So Anna, 1979, 40. Do I see all 3 of those values elsewhere in this table on any given row? I think I do. I think I see them on this next row here by chance. Anna, 1979, and 40. All 3 of those values across all the columns match. So this would be a duplicate row according to distinct. I see also these 2 down here, which seem to be the same thing. These 2 could be duplicates because they have the same values across all of their rows. So these would be our duplicate values. Now distinct will find these duplicates and return to me only the first one it has encountered. So to be clear, this row in this duplicate group and this row in this duplicate group. And what we'll get at the end is a table that looks a bit like this, only 1 row for each of those sets of duplicates. And we now have at the end, well, not exactly what I wanted. I mean, I have 2 values now for each of my distinct storms, but I really only wanted 1. So distinct seems to have failed, at least at this first pass here. Well, thankfully, we can actually tell distinct how to determine if any given row is distinct or not. We can pass in as an argument the column we want it to look at to determine if any row is distinct or not. So let's try the name column. If I passed distinct the name column, we'd look only at the name column now to determine if rows are distinct. But what might be the problem here? So if I look only at the name column, do any of these rows seem distinct? Probably not, right? They look all the same, like they have the same name. So distinct would say, I found you an entire set of duplicate rows here, which I will then return to you the first one from. So this top one here. And I mean, that's not what I want either. So it turns out that what makes storms distinct is the combination of their name and their year. So let's then give distinct those 2 columns. Let's say distinct, I want you to look at both the name and the year columns and use those to determine if any given row is distinct. So distinct will look only now at name and year. And looking at only those 2 values, what do you see? Well, I think I see 2 sets of duplicates. These are duplicates here, and these are duplicates here. And distinct will find those for me when it runs and find these 2 sets, returning for me, for each set, the first row. So I should get back, actually, what I was hoping to get back. 1 row for each distinct storm, thanks to this function called distinct. So let's try it out now in RStudio. I'll come back over here, and why don't I use distinct, but now give it both the name and the year columns to determine if some row is distinct. I'll go ahead and run this code here, and I think I have distinct storms. Like I don't see Alan in here any other times. I don't see Dorian or Gilbert or their combination of name and year, but I'm missing the other columns. So it turns out that in distinct, we need to tell it, no, we also want you to keep the other columns too. And we can do that with a argument called .keepAll and set that equal to true. This dot might be a little bit new. It essentially differentiates this argument from any column names. So notice here how we're passing in as arguments like name and year, these column names. The tidyverse creators thought it would be unlikely that your columns begin with a dot, and so decided that one to control how distinct works will be include a dot at the beginning here. So let me run this again, and we'll see I now have all my columns back, thankfully, and I do see distinct hurricanes, or distinct hurricanes, where each one is distinct by both the name and the year. So we've seen now arrange and distinct. What questions do we have on those 2 functions in dplyr? All right, seeing none, so let's continue on. And our next task will be to look at how we could, well, actually our next task would be to kind of save this data. Like I think we're kind of done with how it's, how we hit our results here. So why don't I try to save this data now as its own CSV? I'll take the storms data set that I have, and why don't I store it in an object called hurricanes like this, so now I can keep it and reuse it later on in my code. And why don't I try to now write what I have as its own CSV? I could do so by using the pipe operator. I'll take the hurricanes data set now, which to be clear is the same table we just saw. And why don't I maybe first simplify the columns I'm choosing for it when I write it to a CSV. I'll select now maybe just the year, and let's see, the name and the wind speed columns. And I think that will make things a little simpler for me. I'll then pipe that into write.csv. Implicitly, it will be the first argument. I'll then type hurricanes.csv as the name of that CSV file, and I'll tell write.csv that I don't want any row names, as we've seen in the past. So now if I click source, we'll hopefully see, if I go over to my File Explorer, that I have this file called hurricanes.csv, which includes all that data in that tibble, but now as part of its own file. So what else could we do? Well, I think we've solved our first task. But one other one I would find interesting is trying to figure out, what was the strongest storm, the strongest hurricane in each given year? So let's start there now. I'll kind of remove what I have in storms.r so far, and I'll instead load what I now have in hurricanes.csv. I'll make a new object called hurricanes, and I'll read in my hurricanes CSV. And now if I view hurricanes, well, I'll see all my data in this data frame here. Well, I want to find, ideally, the strongest storm, the strongest hurricane for each year. And if I visually sort this data top to bottom using the year column, I might notice that every year has, well, several hurricanes. So 1975, for instance, seems to have had roughly 6 of them. 1976 here seems to have had also about 6 of them. And my goal is really to end up with a table that looks a bit like this one here. I have one row for every year, and in that row I have the storm, the hurricane with the strongest wind speed. And if you're new to programming, new to R in general, it might not be quite obvious how we get from our data frame we just saw to this data frame here, but we can think about it first conceptually. So let's try that. I'll come back over to RStudio, and let's just think through what we would want to do, how we're to do this by hand. Let me come back to RStudio and look at our table here. Well, I might notice that for each value of year, I have some number of rows. Like, let's say from 1975, I have 1, 2, 3, 4, 5, 6 rows. Now, how we're doing this by hand, I might look at all the rows that fall into this group of rows that have the year 1975. And I might then choose the one that has the highest wind speed, like Gladys, it seems here. I could then do the same thing for 1976. I could look at this next group of rows, if you will, 1976, and look at those 6 rows that have that value, 1976. I might then pick out the one hurricane that had that strongest wind speed, which seems like Belle in this case. So we're thinking a little bit in terms of groups. I would group my data by the value of the year column. Look at rows for each value of year. Now, it turns out that in R, we can not just think in terms of groups. We can actually use some syntax to apply groups to our data set. And we do so using this function called groupBy, which we'll visualize here together. So here is our groupBy function, and we'll see how it works together using an example data set here. So let's say I have this table of hurricanes, and in this case, I have hurricanes in the years 1975 and 1976. Now, as we saw, kind of conceptually back in RStudio, it would be nice if I could think of groups in this data set, where those groups are determined by the value of the year column. Now, groupBy can actually do just that for me. I can take the hurricanes data set here and pipe it into groupBy and tell it which column I want it to use to determine what groups there are in my data set. If I give it the year column, what will it do? Well, it will find for me all the groups of rows for each value of year. In this case, we'll see, well, 2 groups. One where the year is 1975, and one where the year is 1976. These are now my groups of data based on the value of year. Now, this gets really powerful when I apply a function by each group, which I can do after grouping by here. I could then pipe the result of these grouped rows into a range. And a range would normally sort my entire table top to bottom. Now I'm in descending order by wind, but
because I've grouped here, it will actually arrange these rows within each of their groups. For instance, I would get back the following. Notice how each of these rows are sorted, but they're sorted within their groups. A range has been applied to every group that was found by group by. And then for the final flourish here, I could take each of these groups and pass them into this function called slice head, which basically means take the first row you see in each group, and what will I get back? Well, the single hurricane now that had the strongest wind speed in any given year. Pretty cool. So let's try this out now in RStudio and see what improvements we could still make. Come back over here and let's try to use group by. So group by, we said, can take my data frame, my tibble, whatever it is, and apply groups to it. I'll group now by the year column. I want to find groups in my data by the value of the year column. And then for each of those groups, well, I want to arrange them. I want to arrange them in terms of descending order by the wind value. OK. And then for each of those groups, I want to slice the head off. I want to take the first row I see from each of those groups. So now, if I save this file and run line 2, I should see, well, only one value per year, and it should be the hurricane that had the strongest wind speed in that year. Now, we've seen a function like slice head here. It turns out there are others that are useful to us too. They're often used with groups. Among them are these. We have slice head, which turns to us the first value in any given group. Slice tail, which gives us the last value in any given group. And ones that are more advanced, like slice max and slice min, where I can actually give slice max a column, and it will look in each of those groups and pick for me the highest or lowest value of that column and return to me the row that has that value. So I think I could actually rewrite this using maybe slice max, because I'm looking for, in this case, the value that has the highest, the row that has the highest value in the wind column. Let me come back to RStudio here, and let me try not arranging and slicing the head, but allowing slice max to do that work for me. I'll group by year and slice max for every row, or for every group I'll try to find, in this case, the one that has the highest wind value. And to determine which value to use in slice max, I use this argument called order by that says for each group, order it by the wind, and then take the highest value. In this case, the row that has the highest value for wind. If I run this line here, I should see the exact same result, but now I'm letting slice max do a bit more of the work for me. All right, what else can we do with these groups? Well, let me actually first pause here and ask, we've seen how to group by now. We've seen how to order within groups. What questions do we have, if any, about these groups?
Okay, sir. In the first, when we declare a filter in the first 2 or 3 sections, we put integrated filter for each database. Can we use it now?
A good question. So we saw earlier we could kind of filter some rows out of our data set, and we kind of did that earlier on in our pipeline of this pipes going back and forth, if you will. We could still, though, apply a filter here. So let me go ahead and try this out now. I'll come back to RStudio, and let's say I now have, at least it seems to me, this data set that includes one hurricane per year. But I could still filter this data set. I could maybe find those that occurred maybe between 1980 and 1990. So I could go ahead and say, let's filter this result here and try to find those where maybe the year is greater than or equal to 1980, and let's say the year is less than or equal to 1990. And that would give us a subset of my data where the year is between 1980 and 1990. Inclusive. Let me go ahead and run this, and we should see that my data set has been shortened a little bit. It now includes 11 rows from 1980 to 1990. So we can apply a filter at any point in our pipeline, but it will apply to whatever we pass to it as, or through this pipe operator here. A good question. OK. Now there's one more thing we can do with these groups, and one more question I think is interesting to ask. So in the hurricanes table, actually what we have now is we can still see kind of our old value, the hurricane CSV here. And one question I have is, well, for each year, how many hurricanes occurred in that year?
it seems like for 1975, there were 1, 2, 3, 4, 5, 6. Same for 1976, but we want to figure that out for each and every year, or for each and every group. So what we're effectively doing is summarizing our data, trying to find some number, in this case the number of rows we have in each particular group. Now a good way to summarize your data by group is to use the summarize function after you group by some particular value. So let me go ahead and try this. I'll say summarize, and I'll pass in a function I want to use to summarize those groups. Now it turns out I can use functions like mean. For instance, I could ask for the mean, maybe wind speed for each group. But I might need to ask for something else here. I want the number of rows in each group, which in this case will be determined by n, where n is a function that finds for me in every group how many rows there are. So I'll pass as input to summarize this function n, and summarize will apply for each group this function n, returning to me the number of rows in each of those groups. Let's try it out. I'll hit enter here, and now we should see I still have all my years, those groups now, but I'll see only a single value for each one. I've summarized them in some way. In this case, I've summarized them using the n function, which tells me how many values there were in each of those groups. So it seems like, to translate now, in 1975, there were 6 storms, and in 1982, there were 2 hurricanes. Now I could make this a little prettier, arguably. I could actually go back down here, and I could change this from n to simply to hurricanes equals n. And this is allowing me to name the resulting value. So if I then run this again, what do we see? Well, I see a named value, a named column now called hurricanes. So I'm still doing the same thing. I'm still applying this n function over each of my groups, but because I've now typed hurricanes equals n, I'm naming the resulting column in the data frame that I get back. So pretty cool to summarize now our groups all together. Let's go ahead and just see one more thing in terms of groups. Let's go back to what we had before of grouping by year, and I'll slice now the row with the maximum wind speed value, just like this. Let me show you again the tibble we had. Notice how, in addition to the column names and their storage modes, we also have this here, which has groups. And it seems like we have the very thing we've grouped by, the year column. So if I were to save this tibble as its own object and reuse it later, it would still be grouped by year, which may be good or it may be bad. Maybe I only want to group by year in this particular analysis. So you should know about, and at least be careful about, knowing which groups are in your data. And if I wanted to ever remove some groups, I could do so using the ungroup function. I'll come back over here and show you what that looks like. I'll go back to my storms.r file, and I will then take this code. I'll pass it into ungroup, which if I run this now, will allow me to have a tibble, but now there are no more groups. I temporarily grouped by year, and while we were grouped by year, I sliced the maximum value in terms of wind for each group, and then I ungrouped. So I can save this tibble and reuse it later while applying some new groups that don't have anything to do with year now. OK. So thanks to dplyr, we've seen how to transform our data in all kinds of ways. When we come back, we'll see how to tidy our data even better using a new package called tidyr. See you all in 5. Well, we're back, and so we've seen how to organize data and transform it when that data is already pretty well organized. But odds are you'll be given some data sets that aren't as well organized. It'll be your job to tidy them up and turn them at least into the right format. Now, what is the right format for our data? Well, in R, we have this idea of tidy data, where data that is tidy should adhere to 3 principles. And we're going to walk through the principles step by step here. The first principle is this, that each observation is a row, and each row is an observation. But what does that mean? Well, if I look at this table here of hurricanes, we know that because this is a table of hurricanes, our observations are individual hurricanes. And so it stands to reason that every row in this table should be about a hurricane. And as a corollary, we shouldn't have any rows that aren't about hurricanes. So here I seem to have maybe met that guideline. My first column here, my first row here, that seems to be a hurricane. My next row, that seems to be a hurricane as well, and so on down the line. I also don't have any rows that aren't
about hurricanes. So this seems to adhere to that very first principle of tidy data. The next one, though, has to do with columns, where each variable is a column and each column is a variable. Well, let's show an example again. So if we have this table of hurricanes, it stands to reason that these hurricanes could vary in some way. Maybe they happened in different years. Maybe they have different names. Maybe they have different wind speeds. Well, the way these hurricanes can vary, those should be the columns of our tables. And more importantly, we should only have the ways a hurricane can vary as our columns. We should not have columns that aren't a way that a hurricane could vary. And I think that this table satisfies that second constraint of tidy data. I have here one column for the year, one column for the name, and one column for the wind speed of each of these hurricanes. Now, our third and final principle of tidy data in the R universe is this, that each value is a cell and each cell is a single value. Now let's see an example again. Here I have this same table, and the values now are some things like a year, like 975, or a name, like Eloise, or a wind speed, like 110 here. And notice how each of these values is in its own cell, and each cell has no more than one value inside of it. So I think that this table here also satisfies that third constraint. So this is, I would argue, an example of tidy data. But odds are you won't always have tidy data. And the process that which you might actually do to make it tidy is a process known as normalizing, converting your data into the standard format that makes your analyses just so much easier. So let's see an example of data that isn't quite so tidy. Here is a table, it looks like, of students. But I want you to look at it for a few seconds here and think, why might this data not be very tidy? What principle might it violate, or what do you think would be better designed about this data here? Feel free to raise your hand. Why might this data not be as tidy as it could be?
Okay, I think because there is computer science, which has two words or two variables, and there is a float number. I don't know if it concludes in this particular rule.
Yeah, good observation. So we have computer science here, which is maybe it has a space in the middle. We also have some floating point values. And I actually like your thinking that this value column seems to have different kinds of data. Like on the one hand, it has a 3.5, which is this kind of floating point value, a decimal value, but it also has character strings too. So that is one example of why this data isn't quite so tidy. One of the main ones I'm thinking of, though, is this attribute column. So it seems like the ways a student can vary are not so much columns as they are values in these rows. So a student could vary based on their major. Maybe they major in statistics, or they major in computer science, or they major in data science. And they could vary in their GPA, or their grade point average, how well they're doing in their classes. Mario seems to have a GPA of 3.5. Peach seems to have a GPA of 4.0. And Bowser seems to have a GPA of 3.7. But if these are ways a student can vary, well, shouldn't they be columns instead? So I'd argue that this data is not very tidy at all. And what would make this data tidier is if it was in this format here. Notice how the ways a student can vary by major or GPA are now our columns. And for each of those columns, we have the values. And to Ahmed's point earlier, notice how we now have columns all of the same type because we converted those rows now into columns. Our major is all the type character, and our GPA is all the type numeric. So this, I would argue, is tidier data. Now, let's see how we could take a data set like we just saw before that's not very normalized, not very tidy, and convert it into this example of tidy data here. I'll come back to RStudio, and I already have open this file called students.r, and it will load for me this CSV called students.csv. Let me go ahead and load it here. I'll hit enter and command enter again, and now I'll see this data set here. I should see a similar format that has those same concerns we had, namely the value column seems to have conflicting kinds of data types, both numbers and characters, and the attribute column, well, really this has values that should be columns of our data set. So thankfully, we actually have functions we can use to help us accomplish this task of tidying up this data. No need to do it by hand anymore. In fact, there is a package, part of the tidyverse, called tidy-or. Tidy-or allows us to tidy up our data and make it adhere to these tidy data principles. Now, let's see an example here. We can use an example function called pivot wider. And pivot wider is going to serve us well, because pivot wider takes columns that have values, row values that actually should be columns themselves. So for instance, let's see this table here. Notice how the attribute column has values in these rows that should be column names. Like we saw earlier, we want major to be a column name. We want GPA to be a column name. Well, we've seen these are in a column here, and pivot wider can help us take this long column of column names and convert them now to be column names themselves. Notice too that for every column we might want to make, we have a value for that column for any given student we have. So for instance, in Mario's major column, we'd like to see statistics. In Mario's GPA column, we'd like to see 3.5. And so given a column that has values which should be column names, and a column that has values for those columns themselves, pivot wider can take those and make a table that looks a bit like this. Let's focus now first just on Mario to see this visualization happen dynamically. Let's look at Mario here. Notice how Mario's major column should have the value statistics. Let's see what pivot wider does. Major becomes its own column, and what's the value for Mario? Statistics. Let's look now at the next one. Let's go back one or more. See, Mario's GPA column should be 3.5. What happens with pivot wider? Well, GPA becomes its own column, and Mario's value is in fact 3.5. So let's see now in RStudio what pivot wider can do for us. I'll come back over here. Let's take a look at what pivot wider can do. I have my students table, which looks a bit like this. It's not very tidy, not very normalized, but I can use pivot wider now. So I'll use pivot wider as follows. I'll type pivot wider, and then I'll take as input the very data frame I want to work with, in this case, students. So I'll type students here as the data frame I want to work with. And the next argument to pivot wider is going to be one called ID_calls. And this is asking me effectively for, when I pivot this table, which column is going to be the column where I should only have one value for each student. So in this case, student is telling us what kind of unique row we want to have. If I look again at this tidy data, notice how I currently have 2 values for each student, but I only want 1. And if I go back to this visualization of our tidy data, notice how in every row I had only 1 student. So this is our ID column. Ultimately, we want to end up with only 1 row for each of these students here. So I'll come back, and why don't I actually make this my ID column? I'll go back to students.r and say my ID column is the student column. I want to end up with a table that has has unique values for student in it, let's say. Now the next thing to specify is where should I get my column names from in this new table? Well, we said before that the attribute column here had the values we wanted to be column names in the end, like major and GPA. So the attribute column then should be given to names from, which tells pivot wider that when it pivots this table, it should take the column names from this column here, one that has both major and GPA inside of it. And the final thing to tell pivot wider is, well, where should I get those columns values from? Values from is another argument here, and we'll tell it that we should get the column values from, well, the column currently called value here. Notice how when we change these to columns, we want Mario's value for major to be statistics. We want Mario's value for GPA to be 3.5. So we'll say this value column is where we get those values from. So I'll type value here. And now I think pivot wider has enough information to go off of. It knows which row and the end table it should make unique in terms of the values in it. It knows which column it gets the column names from, those new column names to create, and it knows where it gets those values from for each of those columns now. Let me go ahead and run pivot wider, and we'll see we successfully have created a pivoted table that now adheres to these principles of tidy data.
And if you want a mnemonic, kind of think about how our table here was quite long. It had many values for each student here. All we've done is we've taken those long sets of values and converted them to be a little bit wider, now in terms of columns. And our table, in fact, is a little bit shorter, but it is wider as well. We have a column for major and a column for GPA. So this is an example of pivoting our data. But why would we do this? Well, because our data is now tidy, we can do so much more with it. I could maybe, for instance, try to find the average GPA across majors. And I'll do an analysis here I couldn't do if my data hadn't been tidied. Let me go ahead and go back to my source here, and let me save this pivot wider version as the new version of students. And now I could use all those functions we saw in dplyr to transform this data and find, let's say, the average GPA for each major. I'll take my students table, and I'll group it now by major. Because for each major, I want to find, in this case, the average GPA. So I will, for each group, summarize the group, and find the average GPA, just like this. Now to be clear, I'm grouping by major. I'll find probably, say, 3 groups, because we have 3 majors. And for each of those groups, I will then find whatever the average GPA was. Let me go ahead and run line 9 here. And what do we see? Column major is not found. Let me go ahead and try to save this first. Line 2, and then line 9. And I think, well, now we have a new error, which is this. We have a tibble with major, but GPA being NA. Let's see. I think we might have seen this error before. Argument is not numeric or logical, returning NA. If we go back to our tibble here, we can take a peek. Let me look at students again. And let me show students now. What do you think might have gone wrong in GPA? We were trying to find the average, the mean GPA, but what is the tibble telling us? It seems like the GPA here is a character value. It's not a numeric value, it's a character value instead. So I think I need to first convert this before I can do any kind of grouping and finding the average GPA for each of those groups. Let's go back to RStudio here and do just that. I will maybe pivot wider, just like I did before. And then once I do that, why don't I make sure the GPA column is numeric? So I'll say students, the GPA column within it will be the numeric version of the GPA column in students. I'm coercing this column called GPA to be numeric now. And if I run this top to bottom and go ahead and run line 11 now, we should see successfully we have found the average GPA for each major group. OK. So we've seen now one example of pivoting our tables to get some tidier data and the kinds of analysis we can do now that we have tidy data. I'd argue I couldn't do this analysis earlier when data was not very tidy. But let me ask now, what questions do we have on this program as it stands, or on pivoting our tables to be a little bit wider than they were before to adhere to these tidy principles?
So my question is, what happens if one of the attributes is missing? For example, if for Mario, what happens if you don't have GPA in the column?
Yeah, really good question. If you have data that's particularly untidy, that might happen to you. Why don't we actually just try it out and see? So I'll come back to RStudio, and why don't I modify my CSV? So you said, what would happen, let's say, if, actually let me go back and look directly at my CSV now. I'll open students.csv. And you asked, what would happen if we didn't have a GPA value for Mario? So Mario's row looked a bit like this, where Mario only had a major in our untidy data from before. Well, let's try it out. I'll load this CSV that now has no GPA value for Mario. And I will then try to pivot wider and see what happens. Oops, that's the wrong, didn't have my cursor in the right place. I will run line 2. And it seems like everything went OK. But let's see now what students looks like. Seems like Mario simply got an NA value for GPA. So very handy. If pivot wider didn't find a value to give to Mario's GPA column, it will instead put NA. And we know from before that NA means not available. There was no value to place here, even though there could have been. So pivot wider can handle all kinds of untidy data and handle them effectively too, telling us when something is not going to be available for us. Now there is also as well a function called pivot longer, which can in this case take columns that should instead be row values, and we can make that happen instead. I'll save this one though for you to work on your own if you want to explore more about pivoting tables. For now though, we'll take a 5-minute break and come back to see how we can actually tidy the values of the data itself when those are messy as well. We'll see you all in 5. Well, we're back, and so we've seen how to transform our data and to convert it into a tidier structure. But sometimes you'll get data where the values themselves have stray characters, and it'll be your job to clean up those values themselves. Now, we're going to take a look at this package called string-r that helps us work with character strings, helps us, more importantly, clean those up. So we have an example data set here of votes given to us for people's favorite children's TV shows. And I have a program here that counts up those votes. Notice here how it first reads in this file called shows.csv. And I'll show you exactly what's inside that CSV here. Notice how I have at least a single column called show, and underneath are individual votes for, in this case, people's favorite children's TV shows. And now, in shows.r, once I read in this data set, well, I will view it to show you what I have. I'll view shows, and here I have all of those votes for people's favorite shows. Now, down below in my program, I have a way to count up those votes. I'll say, let's group by the unique values of shows. So for every show we have, try to find the groups therein. And then let's summarize them to make this column called votes that will be however many rows we have in each of those groups. So if we had, let's say, 3 rows inside of the Avatar The Last Airbender group, that would be 3 votes for Avatar. We would then ungroup, and why don't we arrange then by this vote column in terms of descending order. So if I run line 3, what will we see? I'll see now these shows now ranked in terms of their number of votes from my CSV. So I'd argue we're getting there, but I think there might be a few problems with our data. I mean, if I were to say that Arthur is clearly the most popular children's TV show, if you're looking astutely, what might you notice? What have we done wrong here? Any ideas? What is not tidy about our data?
Yes, that all of the movies have different names, even though they are the same movie or the same show. For example, Avatar, we could argue that it's the same show, but they're spelled different or have moved places, so we have to tidy it up.
Yeah, I like what you're thinking. So if we grouped by the show name, well, group by needs to see that the value is exactly the same. And here, I mean, I seem to have Avatar The Last Airbender right here on row 3. But down here on line 10, I also have Avatar The Last Airbender. The only difference is that this one has a little bit of a space in front of it. And this happens all the time. If you're getting input from users, they'll make typos, add extra white space, and you just have to handle those things that happen in your data. So I think we should clean this up a little bit before we start counting these votes here. Let's first handle this white space we don't want. See, there's like an extra space for an avatar. Let's get rid of that on that row and all the rows as well. Now, string r comes with some functions to handle trimming white space around our character strings. Now, one of these functions is called stir_trim, to trim the white space on either side, front or back of our character strings. Let's go ahead and try that. I will take my program here again, and before I count up these shows, why don't I take the show column in shows, and I will then trim, using stir_trim, the values therein. So I'm now taking that show column in shows, trimming off on the front and back of each character string any extra white space. And I'll store that now as the new values for the show column in the shows table. Now let me go ahead and run top to bottom. I'll read shows, run line 3, and now run line 5. And I think we're getting a little bit better, but I think there's still something I noticed. So no extra white space on the front or the back now, thanks to stir_trim, but I see Avatar The Last Airbender and
avatar colon, space, the last airbender. So somebody made a typo inside the character string, and that's just so frustrating. But what we could do is use a function called stir squish, which looks at all the white space inside of our character strings and tries to reduce them to a single space character. So let's use stir squish here. Stir squish is spelled exactly like this, str_squish. And I'll go ahead and go back to my source file here. And why don't I, in the same breath as I remove the front and back white space from my shows, why don't I remove any extra internal white space? So I'll take the shows, the show column of shows, and I'll pipe that into stir trim, trimming off the front and back white space on either side of my character strings, and then I'll pass that result in to stir squish, which can take care of, for me, any internal extra white space, like the double space we saw in avatar colon space, the last airbender. And it'll convert that to a single space. Let me go ahead and run from top to bottom, 1, 3, 7. And now we should see, getting a little closer still, I see my shows column and my votes column, and now I don't think I have any extra white space to deal with. So pretty good. But what is still wrong with this data set? If we look closely, what kinds of typos or things like that have we not taken care of yet? Let me ask our group. Diane, what do you think?
I see a lot of capitalization mismatches.
Yeah, good idea. So capitalization is an issue here too. If group by looks at avatar colon the last airbender all in title case, it won't consider that to be part of the same group as avatar underscore avatar all in lowercase the last airbender. So we need to standardize on some capitalization for these character strings too. Now luckily, string R does have functions to actually help us standardize the casing of these particular values. So let me come back now to my computer, and let's try looking at a few of these. Among them, to handle capitalization, are stir to lower to convert everything to lowercase, stir to upper to convert all characters to uppercase, and one that would be good for us called stir to title, one that would help us actually put our characters in title case, where each word itself has a beginning capital letter. Let's go ahead and try this out. I'll go to source, and then I'll go to my, my file again. And why don't I try to standardize now, maybe on uppercase? I could take first, I'm going to trim the white space, squish the internal white space, and now I'll take these strings and make them all uppercase. Okay, I'll go ahead and run line 3, or run top to bottom again. 1, 3, 8. And now I'm kind of yelling when I have these show names. I think we've standardized at least on the case, but this isn't very pretty, so I probably want to use now stir to title, which will title case everything, converting their first character to uppercase, stir to title instead, and now if I run top to bottom again, what do we see? But a much prettier and much nicer kind of output here in terms of shows and votes. So now we're getting even closer, but I wonder if there's still something that we need to fix. Any ideas for what we need to fix in this data set? Let's go to Ahmed.
Group by the first word or the first sentence in the section of show's name?
Yeah, so I think, let me think if this is what you're thinking about here. So I noticed that in row 1, we have avatar colon the last airbender, and that doesn't seem to be matching with, it was down here on row 10, avatar. So because this is a votes for children shows, I think we could assume that avatar means avatar the last airbender, but somebody didn't type out the actual show name. So it'll be up to us now to figure out, how do we find these other versions of the avatar name and standardize those? Well, string R comes with some functions to help us do just that. Let's come back and take a look at those. Over here, we have one called stir detect, among others that can actually look at strings values and try to find some value within them. So stir detect takes as an argument, first, the character string to look at, and next, a character string to detect or find in the very first character string. So let's try this. I'll go ahead and go over to shows.r, and let me try this. I think we might need a new row for this. I'll try to use stir detect and look in
the show column of shows. And for every character string, for every element in this vector, I want to ask, do you see, do you detect the word avatar inside of it? Let's try it out. I'll go ahead and run line 8, and I'll get back a logical vector. So I see here some true values and some false values. Now the true values are those values for which it detected this character string avatar inside of them. But to make this a little more apparent, let me do what we did in a prior lecture and take a subset of our vector here using this logical vector. I'll take my shows, my show column of shows, and subset it using this logical vector that looks at each value and asks, do you detect the character string avatar in those values? Let me run line 8 now, and I'll see I get back a subset of that data that now includes all the strings where it detected, in this case, the word avatar. So now that I've done that, I think I could take these values and standardize their name. Any show that has the word avatar in the title, why don't we make it avatar : The Last Airbender in title case? Well, I could do that now by simply assigning this subset some new value. I'll go ahead and assign this subset a new value, which will be avatar : The Last Airbender, to standardize now on this given title. Let me go ahead and run top to bottom now. I'll read in my shows. I will then remove white space, standardize and capitalization. And for the special case here where somebody typed in a show that isn't the full name, I'll go ahead and find all shows that mention Avatar and now name them Avatar: The Last Airbender. I'll run line 8. And now let me run line 10 here. And we should see, hopefully, I think we've standardized all of our votes. There are no more here to work with. Now, what we did here with Avatar, let's think through some edge cases here. What could go wrong? What could go wrong if we did something like this, whether it's for Avatar or something else? What should we be considering as we use functions like strdetect? Any ideas for what could go wrong? Let's go to Heighton.
The name could be subset, right? So it can be named for another movie or another show in this case, right? And we might end up replacing that. For example, Avatar is also a movie.
Yeah, it is a children's TV show, but it's also a movie, and a pretty popular one. So maybe the person who entered Avatar, maybe they actually meant Avatar the movie, and now we've overridden their vote with Avatar: The Last Airbender. So it's important to be cautious and to be intentional about which strings you use to match, and particularly those you use to override in the end. So here we have seen many ways to tidy up our data. We've seen how to subset our data. We've seen how to transform it using dplyr tools. We've also seen how to tidy our data using tidyr, and now we've seen how to clean up these character strings as well. With our tidy data, we're able to do so much more, like visualizing it too. So we'll focus on that next time. We'll see you there. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Carter Zenke, and this is our lecture on visualizing data. Now, a good visualization can help you see trends you wouldn't have seen otherwise, help you compare groups in your data, and help you share your findings with others. So we're going to do all of that and more today with the help of R and with this package called ggplot2 that is part of the tidyverse. Now this name, ggplot, is a bit weird, but there's a reasoning behind it. The plot in ggplot means we're going to plot our data, which is the word for visualizing it, translating it from a table into some picture to represent that same data. And the GG in ggplot stands for this grammar of graphics, which put simply is a way of expressing ourselves graphically. In particular, this grammar of graphics gives us some individual components we can combine to create plots or visualizations from our data. What are those components? Well, the first one, of course, is going to be data itself. Before we can do anything, we need to have data to visualize. And so let me propose we use this data here, a table of candidates and the votes for each of these candidates. Notice how I have 3 of them, Mario, Peach, and Bowser, and each has some number of votes. Now, of course, data is just data. It's not a visualization yet. Our goal is to translate this table into some picture. So we'll need another component of our visualization to take this data and convert it into that picture. Now what we'll need is what we call a geometry more formally. And a geometry is simply a way of saying what kind of visualization do we want. I think it's best shown through example here. So I'll show you 3 different plots, each with their own different geometries. Notice here I have one involving columns, good for data that involves groups and values associated with those groups. I have one plot that uses points here, good for representing relationships between 2 columns in your data set, perhaps. And I have here a line geometry, one that can actually show us change over time. And so I'm curious, given these 3 geometries, of which there are many more, but we'll focus on these 3 for now, which one do you think would be good or best for the data we have here, where we have 3 candidates and some number of votes? So let's see what our audience thinks. What kind of geometry among these 3 here would you use to visualize this data in particular?
I think we will use columns to present it in more visualized example.
I like your thinking. So we could use these columns here to visualize our candidates and their number of votes. And more particularly, let me say that maybe each candidate gets their own column, and how high or low the bar goes, the column goes, that would be the number of votes that candidate received. So notice here how we're specifying not just the data involved and the kind of plot we want, but also how that data references or is represented on our plot here. How many columns we have, how high or low those columns go, those are all associated with some part of our data. Now we call this association more formally this aesthetic mapping, which is a bit of a big term, but we can break it down into smaller pieces here. An aesthetic is some visual feature of our plot, maybe how many columns there are, how high or low each of those columns go. And a mapping is really another word for a relationship. Well, what are we relating here? We're relating our data to some visual features of our plot. I think this is best shown by example. So here I have a plot, and you've often seen plots with a both vertical line and a horizontal line here. And if I look at this plot kind of naively, and you ask me to draw some columns, I might say, well, how? I mean, do they go left to right? Do they go up to down? I'm not quite sure how to draw these columns, even if you want me to. So thankfully, there are certain aesthetic or visual features of this plot that we could talk about and relate our data to. Namely, most plots tend to have what we call an x-axis on this horizontal line here. This is known as our x-axis. And most plots, too, have what's known as a y-axis, a vertical axis here. And if we have both a y, or a vertical axis, and an x, or a horizontal axis, we could talk about, well, which parts of our data go on the x-axis, and which parts of our data go on the y-axis here. So let me show you again our data. We had here candidates, 1 column, and votes, 1 column. Let me ask more precisely now, which column of our data do you think should be mapped to or represented by the x-axis of our data?
Our candidate column?
Maybe our candidates, right? Because we could have the candidates on the x-axis representing now 1 individual column for each of them. So we will map, let's say, our candidate column to this x-axis. And by process of elimination, it seems like votes should go now on the y-axis. And so we can see what it looks like to now map these columns to our plot over here. Well, if I wanted to map my candidate column to the x-axis, what could I do? I could kind of write these candidates' names on the x-axis here. I'll start with Mario down below, and then I'll follow it with Peach, who's our second candidate, just like this. And now I'll follow that with Bowser, too, our third candidate, just like that. So now we could say our column candidate is mapped to our x-axis. But now we need the y-axis. And we said, well, the y-axis is going to be represented, is going to have this votes column on it here. So how could we do that? Well, notice that these votes here fall into some range between, let's say, 0 to 200 at the maximum. So maybe on this y-axis, I could say, let's start at the very bottom with 0, and all the way at the top, we'll put 200. So now the height of these columns should correspond to the y-axis. And I think now that I have these x and y axes,
I know much more how to draw these columns. If you told me draw columns representing the number of votes each candidate got, I would know how to do exactly that. I would know they should start at the bottom and move all the way up in terms of height. So let's draw these now. I see Mario has 100 votes. So I want to put a column on here for Mario. Well, Mario's column should be of the height on the x-axis that is equal to 100, which should be right in the middle between 0 and 200. So I'll draw Mario's column a bit like this. I'll put it right in the middle here. And I'll draw Mario a column, just like that. That's Mario's column. Now I want to draw Peach's column. Well, Peach had 200 votes. I'll make Peach's column go all the way to the top of our y-axis where we put the 200 votes. And I'll make sure that that column reaches all the way up there. And finally, for Bowser, well, Bowser had 150, somewhere between Mario's 100 and Peach's 200. So I will put Bowser's column right in between those two, just like this. So this now is our complete plot. We've worked with data. We've worked with our aesthetic mappings, taking our columns and aligning them to the x and the y-axes. And now we've worked with our geometries, this actual visual representation of now our data in terms of columns. So all that's left to do now is do this in code. So we'll come back now to RStudio, and we'll look at how we can use this package ggplot2 to do just that. I have open here a file called votes.r, and I'm reading in this CSV called votes.csv. Notice here how it goes into a table that I'm calling votes. And this is the same table we saw before on the slides. We have a candidate named Mario, a candidate named Peach, and a candidate named Bowser, and each has some number of votes. Well, if I want to create a new blank plot, a bit like what I had before here, I'll go ahead and I'll use this function ggplot, just like this. And so long as I have installed the tidyverse and loaded it using library down below, tidyverse, just like this, I can have access to this function called ggplot that creates for me a new blank plot. So let me run line 3 here, and what do we see? Well, in the plots column, or in the plots tab here, I'll see this blank plot that I can then draw, put brush strokes on to visualize my data. But we haven't actually given our plot anything at all. This ggplot function has no input whatsoever. So I think it's worth thinking about what kinds of inputs we need to give to our plot so that it can visualize this data we have in our table here. Now, the first input, as we saw in our grammar of graphics, is going to be the data to visualize. So let's give as input now to this ggplot function the data itself. I'll come back now to RStudio, and it turns out that the first argument to this ggplot function, which creates for me a new plot, is the data itself. I'll provide as the first argument now this votes data frame. And now, if I run line 3, well, I still see nothing. And that is kind of expected, because we said that data, at the end of the day, is just data. We still need a way to map its data to certain aesthetic features of our plot, certain visual features, and we need to say what kind of plot we want. Well, let's do just that now in code. I'll come back now to RStudio, and it turns out that one other piece we need here is our geometry. We've given it some data, but we need some geometry to specify what kind of plot we want now. Well, the way we can do this syntactically in R and in ggplot more generally is to use this plus sign here and to follow it with the part of geometry we want, which is going to be a column geometry. Now, to get a column geometry, I can use this function here, geom_call. And there are other geom functions like geom_point or geom_line, but for now we'll use geom_call to create ourselves some columns. But notice here this plus. So you've seen plus, and we've been adding up some numbers, like 1 plus 1. But this is not that kind of addition. In fact, the creators of ggplot have what's called overloading this plus sign. It no longer means addition. It means something else entirely. In fact, it means we're going to add a new layer to this blank plot. Let me show you what I mean with this prop over here. So we had here our visualization, which had columns on top of it. But I drew these columns on the same layer, let's say, that I drew my axes. Turns out that in ggplot, our plots have multiple layers. So instead of everything being on the same page, so to speak, what we instead do is the following. Let me erase my columns that I have here, and let me instead do this. let me take out a new layer I could put on top of my blank plot here, my x and y axes, and on this layer could I draw my columns. Let me go ahead and do the same thing we did before. Mario had about 100 votes. I'll put these halfway up the y-axis. Peach had 200. I'll put those all the way up at 200. And Bowser had 150, somewhere between Mario and Peach's votes. And now, notice what I've done. I have separated my plot now into layers. One layer, of course, is my columns here. And one layer seems to be my axes. Same thing I'm doing here. We've started now with this blank piece of paper, thanks to ggplot, and we're now adding a new layer, one that involves columns. So let's see what happens. I'll come back now to our studio, and let me go ahead and run this here and see what we see. Nothing yet. I do see this error that the geom call function requires the following missing aesthetics, x and y. And so I think ggplot is running into this same problem that I did earlier. If I don't know how to map my data to the visual features of this plot, well, how can I even draw these columns? So we'll need to specify these aesthetic features, x and y, before ggplot knows how to draw these columns here. Now, it turns out we can specify these aesthetic features using a function, one called AES, which stands for aesthetics here. Now, aesthetics, the function, looks a bit like this, AES, and it takes as input any number of pairings between aesthetic values, like x or y, and the columns in my data. For instance, like this. This would be one aesthetic mapping. I'm taking one column in my data and assigning it to control some visual feature now of my plot. So let's do the same thing now using AES, this aesthetic function, and actually make it happen for us inside of R and ggplot. I'll come back to our studio here, and let's go ahead and use the AES function to tell this plot exactly how to map our data to certain visual features of our plot more generally. So it turns out, by reading the documentation, I know the second argument to ggplot is this AES function, which we know takes as input certain pairings between these aesthetic features, like x and y, and columns in our data. So one aesthetic feature is the x-axis. Which column should go on the x-axis of our data? Well, we know we're going to put the candidates column on that x-axis here. I'll go ahead and I'll say x equals candidate, just like this. This means that the candidate column in my data should now be mapped to the x-axis of my plot. Now I'll do the same for the y column. Well, the y aesthetic is going to be mapped to the votes column and vice versa. So the votes column should control the y-axis effectively. I'll go ahead and say that y equals votes, and now with these aesthetic mappings specified, I should be able to visualize this. I'll go ahead and run line 3, and voila, we have our very first plot now created with ggplot, thanks to starting with data, defining how that data controls visual features of our plot, like the x and y axes, and now using a new layer, adding in these columns. So let me ask now, what questions do we have on what we've done so far?
If we look into the x-axis of the plot that we did now in ggplot2, the order of our candidates is slightly different from what we drew in the board. So why is that, and how do we expect ggplot to order our levels?
Yeah, a really good observation. I was hoping you might notice this actually. So notice here on the plot, our names are not in the same order we saw them in our data. In our data, it was Mario, Peach, and then Bowser, but it seems like on the x-axis here, it's Bowser, Mario, and Peach. Well, what order is this? Turns out this is alphabetical order. So Bowser with B comes first, followed by Mario, followed by Peach. So we can generally expect ggplot to sort our data on either axis. In this case, because we're working with names, sort it alphabetically down below on the x-axis. But a good observation to make. Now, let's keep going, and ggplot gives us some pretty good defaults for our plots. I'll notice here that on the labels here for my axes, I see the name of the column, like candidate, and on the y-axis, I see votes for the y-axis. And even on the y-axis, it has decided for me that the range of values should be 0 to 200. So these are pretty good defaults, but sometimes you might want to override or change those defaults, which you can do by adding new layers to your plot. So let's consider how to do just that. Well, here, one thing I want to do is change this plot so I have a little more headroom up here on Peach's votes column. Maybe I want my y-axis not stop at 200, but to go up to, let's say, 250. Well, to do that, we'll need to learn about this other concept in plots and in ggplot2 more generally, one called scales. So let's learn about scales a little bit together. A scale is simply a way now of specifying how our values actually control our aesthetic mappings. And for instance, there are really two kinds of scales, one called a continuous scale and one called a discrete scale. Now, a continuous scale is for values that fall in some range. You could think of our y-axis here with some number of votes between 0 and, let's say, 200 or 250. That is a continuous scale because some votes could fall in some range. A discrete scale, though, is for values that are what we might call categorical. They fall into categories. For instance, our x-axis has a discrete scale. There are 3 distinct candidates. It wouldn't quite make sense to put them on any given scale. They're just names. So this is what we call a discrete scale. Now, scales that are continuous have what are called limits. And exactly what we've seen here is our y-axis, our y-scale, starts at 0 and goes up to 200 currently. Those are the limits of this scale, from 0 to 200. But we kind of want to change the limit here from 0 to 250 instead. And so it turns out that ggplot gives us functions to modify different scales using some of these right here. So we see scale x continuous as a function, scale y continuous as a function, scale x discrete, and scale y discrete. These change various different scales on our x or y axis depending on if they are continuous or discrete. Now, we said before, we want to change our y-axis, so that narrows our possibilities. It's either this one here, scale y continuous, or this one here, scale y discrete. But we said our y-axis is a continuous scale. It has a range of values. It doesn't have discrete values, it has a range of values. So we could probably use scale y continuous to modify now our y-axis. Let's go ahead and do just that by adding a new layer to our plot. I'll come back over here. And let's say I go back to our studio. Well, I want to change now this y-axis's defaults. And I can do so, as I said before, by adding a new layer. I'll use this plus here to add a new layer to my plot. And let me now kind of overwrite the scale I currently see on the board. I'll use scale y continuous, which will allow me to adjust my continuous y scale that I currently see. And it turns out that by reading the documentation, I know scale y continuous takes this argument called limits, just like this. And limits takes a value, which is a vector of length 2, where the first value is where the scale starts, let's say 0, and where the scale ends, let's say 250. So I'll give limits here, this vector, 0 to 250, and that should now change for me my scale on my y-axis. Let me go ahead and redraw this plot, which I'll do by running this line of code here. And now we'll see my axis has changed. So what have we done? We have first defined this blank plot, given it some data and some mappings between that data and its visual features. We have then drawn some columns on top of it, thanks to geom_call, and then we've kind of overridden the default scale, moving it from 0 to 200 to instead 0 to 250. We're kind of building up our plot as we go now using these layers. Well, one more thing we could do is override the labels here. I'll see this one is candidate with a lowercase c. This one is votes with a lowercase v. I'd love to make them capital to make them more professional. And also, I want to add a title so people can look at this and know exactly what they're looking at immediately. So I can add a new layer now to my plot to add in the labels and either override some defaults or add some new labels altogether. Well, it turns out the function I use to do this is one called labs. Labs is short for labels. I'll go ahead and add a new layer now to my plot called labs. And labs takes as arguments the kinds of labels I want to adjust on my plot. Now, for instance, I could use x equals and set it equal to a character string that I want to be the label for my x-axis. I'll call this one candidate with a capital C. I could also give it a label for the y-axis by saying y equals, and then some character string here. I'll go ahead and call this votes with a capital V. And then for my title, why don't I use this, election results, making it very clear exactly what we're visualizing for any viewer who comes in. I'll go ahead and now build up my plot step by step again by running all these lines of code. And now I should see my plot as it should be. I have all my candidates on the x-axis, my votes on the y-axis, and those labeled now appropriately. I even see my title up top, election results. So we have started with a blank plot, added columns to it, adjusted our scale, and added labels. Let me ask, what questions do we have so far on how we've built up this plot using ggplot's layers here?
Are we going in this lecture to know how to design or to change the layout of these statics, like the votes and the candidates columns and the columns representation to the user?
A good question. So you might be asking, well, how could we change these aesthetics? And often you'll get to this plot and say, I don't exactly like how this works. Maybe I actually want my columns to be on the going like across vertically, let's say. We could absolutely change our aesthetics here to change what this plot is doing here. We could do so by changing these values x and y. Maybe I would make x equal to votes and y equal to candidates, and that would map my columns so they go now left to right as opposed to up to down. That's one way we could change our plot visually. The next way we'll see, though, is how we could change our plot in terms of colors. And I think that might be what you're alluding to here, which is our plot looks pretty nice, but it's pretty gray. It's like black and white. We could probably do better in terms of colors. So let's do just that. Well, I'll come back now to our studio, and let's see how we could change the fill color, that is, the color filling these columns, depending on the candidate's name. Well, notice here I said I want the color to depend on the candidate's name, which seems a lot like these aesthetic mappings. I have some visual feature, in this case the fill color of my columns, that I now want to be dependent on the value in the candidate's column. Well, I can do this using the AES function like we saw earlier, and there are more aesthetics than just x and y. There is, in fact, an aesthetic called fill that can change the fill color of each of these columns. So here, I want to change the fill color of these columns themselves. So what I'll do is pass in the AES function as input to geom_call itself. And here I'll specify, I want to change the fill aesthetic, the color that fills these columns, and I want it to depend on the candidate column in my data. So what I've said here is I want to specify a new aesthetic mapping, one that applies only to columns. I want to change their fill color and have it depend on now the candidate column. I'll go ahead and I'll run this update to our plot. And now we'll see some color, which is pretty nice. Notice how every candidate has their own color, which is because, as input to geom_call, we said the fill aesthetic should depend on now the candidate column we have. Each candidate should effectively get their own color. But when we work with color, it's important to be mindful that people who might look at this plot might be looking at it with some form of color blindness. And so when we convey information with color, we should make sure we do it as accessibly as we can. And thankfully, in R and ggplot, there are ways to adjust colors to make sure they're friendly to those who might look at this with some form of color blindness. So let's see how to do that now. We come back to our plot here, and actually notice on the right-hand side, I've created kind of a new scale. I have here different colors assigned to different candidates. This is, in fact, its very own scale, one called a fill scale. We have our x scale and our y scale, and now we have a new one called a fill scale, determining what colors will belong to each of these candidates here. Well, if I want to change this scale, I could do it in a way that's very similar to the way I changed the y scale, by adding a new layer to my plot and overriding the default. And actually, thankfully, R comes with this scale called the Viridis scale, which is known to be very friendly to many different forms of color blindness. If I want to use the Viridis scale, I can do so using this function here. I'll go back to my plot, and I'll go ahead and add this additional colorblind friendly scale in. I'll say I want to adjust the fill scale I just created, the one you see on the very right-hand side. And I want it to instead be the Viridis scale which is going to be set to the discrete version of that scale. So recall how we had both continuous and discrete scales, continuous being on a range, discrete being individual values. There's a special scale called Viridis discrete, or Viridis D for short, that allows me now to say I want to take these discrete colorblind friendly colors and make them the colors I'll see for each of my candidates. I can do this, followed with a plus sign, and now I've added in this new layer that overrides the default colors and makes them more colorblind friendly. Let me go ahead and build this plot again, and here I'll see my colors change to be more friendly now to those who might be looking at this with some form of color blindness. And there's one more thing we could do here. Notice how on the right-hand side, this scale has a name, candidate, but I want this to be capitalized, so I could change this by passing into scale, fill, Viridis D, the title I want for this scale. Let me come back and do just that. I'll come back over here and say, I want this Viridis scale to instead be named now candidate. I'll go ahead and rebuild my plot, and I'll see on the right-hand side, I've changed not just the scale's colors, but also its title. Now, while we're thinking about aesthetics and how nice this plot looks, one more thing I could do is change its theme. ggplot comes with several themes, and by default or by convention, these themes are often applied at the end of our plot. After we've added our layers of columns and adjusting scales and adding labels, we can change the theme of our plot. So I'll go ahead and add a new layer, one final one to my plot here, and I can use this family of functions that all begin with theme underscore. And there are many themes to choose from. You could do theme BW or theme classic. These are all available in a reference on the ggplot package website. But here I'll use theme classic, which is more minimalistic here. Let me go ahead and say I want my theme to be the classic theme in ggplot. I'll go ahead and rebuild my plot now. And here I'll see that I've kind of changed the aesthetics more so visually. I've dropped the gray background. I've simplified my scales. And I think things just look now much prettier thanks to this theme layer here. So now we've updated the aesthetics by changing now the colors of each of these candidates and changing the general theme of the plot. What questions do we have and how we built this plot up from a blank page to adding columns, to changing scales, to adding labels, and now changing the theme at the very end? What questions do we have?
Can the layers be in any order, or do we have to follow a specific order for them?
A really good question. Can these layers be in any particular order, or is there some defined one we have to use? Turns out the only thing that has to come first is this ggplot function. This gives us, metaphorically, that blank page to write everything else on top of. We could put these other layers in any other order we wanted to, but there is some convention. Generally speaking, we go from a blank page to adding our geometries, like these columns here. Afterwards, we'll adjust our scales if we need to. Here I adjusted the fill scale, the one we see on the right-hand side, and I adjusted the Y scale, the one going vertically now here. After we adjust our scales, should we adjust our labels if we want to? Here I did just that. I adjusted the labels here, saying my x-axis has the candidate name down below, my y-axis has the votes name on this left-hand side here, and my title is election results. And by convention at the end, do we add in our theme here to say, I want to take all this I've just done and style it in some particular way. In this case, this classic theme, which is more minimalist in spirit. But a really good question on the ordering of these layers here. Let's take one more question on what we've just done so far.
Is there a way to get rid of the legend on the right, since it is redundant with the x-axis labels?
Yeah, a good question. So here you might notice that I have one color for each of my candidates, and I have this so-called legend on the right-hand side called candidate that tells me which colors these are associated with. Well, because I only have one color for each candidate, and I already have their names down here, you could probably argue that this is redundant. So I want to remove this. And it turns out I can do that using a parameter of geom call, one called show.legend, which by default is true, but we could change to false. So let me go ahead and do that over here. I'll come back to our studio, and let's say I want to make sure that this fill aesthetic of my column does not produce a legend on the right-hand side. Well, I could say I want to specify the show.legend parameter and have it be not true by default, but false instead. And because this is getting a little long here, let me go ahead and put each of these arguments now on their own line, just like this, and move this parenthesis to its own line. And now I should see, if I were to rebuild my plot top to bottom, that I've removed that legend, and now I just have those candidates on the x-axis and different colors now for each of them here. But there's one more problem I would say with this too, which is in our original plot, we had something like this. We had Mario, and then Peach, and then Bowser. If you look here, we had different ordering than we see in our plot. Here I have Mario, Peach, and Bowser, but on this plot here I have Bowser, Mario, and Peach because by default, as we said before, ggplot will order these values in alphabetical order by name. Bowser, Mario, and then Peach. There is a way to reorder these explicitly if we wanted to, using what we'll call factors, but we'll save that a little bit more. I'll save that for a little bit more later on. Now, we have here our plot, let's say, good enough for now, and I want to save it so I could share it with a friend. Here, this is currently all in RStudio. I'm seeing it here, but I want to maybe get an image file I could share with somebody else. Well, I could do that as well with a special function called ggsave. It lets me save my ggplot to my own computer. So let's see ggsave in action now. I'll come back over here, and why don't I take this entire plot I've built and now store it in an object. And by default, for plots, we use this p name for plot objects, where I'll say everything we've done here, starting with a blank plot, adding in each of these layers, will be stored now under the name p, this object here. And I could, later on in my code, still add more layers. As long as I've saved this plot as this object p, I could say, well, p, and let's go ahead and add in some new layer down below. But we won't do that. We'll instead save our plot. Well, we have a function called ggsave that lets us save our plots. And ggsave works a bit like this. I'll type ggsave here as the function name. And it takes quite a few arguments to save this plot to my computer. The first one is going to be the name of this file, in this case votes.png, let's say. And the next one is going to be the plot I want to save under this file name. Well, here I want it to be the plot p I just made, so I'll say the plot parameter to ggsave is equal to the p, this argument here. We want this to be the plot we save. I'll then say how wide and how tall I want this image to be. Here I played around with this a little bit before, and I found that if the width is around 1200 pixels and the height is around 900, so a 4x3 kind of square, this looks pretty good for this kind of plot here. And I'll also specify that these units are pixels, just like this. I also have inches and so on, or centimeters and so on, but here I'll use pixels. And so thanks to all of these parameters here, the file name, the plot to save, how wide and how tall, and what units we're working with, if I were to run ggsave and go to my file explorer, well, now I would see votes.png. And if I click on it here, I'll see my own file here, now saved to my computer, visualizing all of this data. So we've seen so far how to visualize our data using columns. When we come back, we'll see how to use another geometry, one called a point, to visualize relationships among columns in our data. See you all in a few. Well, we're back, and so we've seen so far how to visualize our data using columns, but now we'll take a look at a new kind of geometry, namely the point. A point is good for when you want to visualize a relationship between two columns you might have in your data, and those columns are both on a continuous scale. So to illustrate this point, no pun intended, we have here this data set of candy. Namely, we have names of candy and their price percentile and their sugar percentile. Well, what does that mean? Well, a price percentile is best illustrated through example here. So let's say I bought this Hershey's milk chocolate bar, and I went and bought it at the store, and it turns out that this milk chocolate bar is more expensive than 92% of candies. So the Hershey's milk chocolate bar, this is a pretty expensive candy overall. On the other hand, a Reese's peanut butter cup, well, this is more expensive than 65% of other candies. So a little less expensive than this, but still not that cheap either. Now, on the other hand, Sour Patch Kids as a candy, this is more expensive than 12% of candies. So a little bit on the cheaper end as far as candies go. So this is price percentile. It's a relative measure of how much this candy costs among other candies in general. But we also have sugar percentile. Well, if we take this same candy, this Hershey's milk chocolate bar, it turns out that it has more sugar than 43% of other candies. And this Reese's peanut butter cup seems to have even more sugar. It has more sugar than 72% of candies. So in general here, a higher number for any of these columns, either price percentile or sugar percentile, means this candy is more expensive or has more sugar than other candies comparatively. So let's see how we could visualize now this data. Well, I have here this plot where on the x-axis I have price, and on the y-axis I have sugar. And it might make sense for us to go through these candies one by one to plot them as individual points on this plot here. So here, let's look at, again, this Hershey's milk chocolate bar, which has a price percentile of 92 and a sugar percentile of 43. Where would this candy go on this plot? Well, I could look first, let's say, at my x-axis, which has this price percentile variable here. If I see that this candy has a 92 price percentile, that would be kind of over on the right of my price axis here, this x-axis, close to 100. Now it has here a sugar percentile of 43, which seems like it would go a little bit below 50. So maybe somewhere, if I point at the x-axis and the y-axis, somewhere right around here. I'll go ahead and draw that point here for the Hershey's milk chocolate bar. And maybe as we add these points, we could ask ourselves, if we pay more for these candies, do we actually get more sugar? Assuming sugar is what we want. We'll see. So the next one was this Reese's peanut butter cup here. It turns out that compared to other candies, this is in the 65th percentile for price and the 72nd percentile for sugar. So a good amount of sugar in these. Let's go ahead and plot this point on our plot here. Well, on the x-axis, it's the number 65, so a little bit past 50, let's say, maybe right around here. And the sugar percentile is 72, so probably somewhere in the top right or so. Why don't we say maybe right around here would be our Reese's peanut butter cup now plotted on our plot here. Well, there's still more candies to go. We have as well Sour Patch Kids, just like this, which is relatively less expensive and also doesn't have that much sugar compared to other candies. So this would probably go somewhere in the bottom left, I would say. It's pretty low on both the x and the y axes. So if we look here, it has 12 on the price percentile, so kind of closer over here, and a 7 on the sugar percentile, so also pretty low over here. I'd say we could plot this point right about here for Sour Patch Kids. So it seems like we're seeing a bit of a trend maybe going on here. What if we tried now Swedish Fish? Well, Swedish Fish, similar to this Reese's peanut butter cup, they're pretty high in price, but also pretty high in sugar. So let's plot this one too. I'll come back over here and say, well, 76 is somewhere in the middle between 50 and 100, so around here on the x-axis, and the 60 is just above the 50 here on the y-axis. So let me go ahead and plot this as our Swedish Fish point. So maybe some relationship here. We see as price goes up, maybe our sugar intake goes up as well. Well, we'll see. Now, one thing we could do with this plot is think about some edge cases, which is here I have plotted 4 different candies, but let's say along comes another candy, this one called Hershey's Special Dark. What do you notice about Hershey's Special Dark as compared to other candies on our list so far? One thing I notice here is that Hershey's Special Dark has actually the same price and sugar percentile as Hershey's milk chocolate. So it brings the question, well, how do we plot this data point? Well, if I look at this chart here and I want to plot Hershey's Special Dark, I'll go ahead and look at it and say, well, the price percentile is about 92 and the sugar percentile is 43. That would put it right here. So I'll go ahead and plot it just like this, and it seems like these points overlap. So although we've plotted supposedly 5 candies, I see here 1, 2, 3, 4 points. So it seems like I'm now missing a point because these two here are overlapping. So there are a few ways to solve this. One, as we'll see in ggplot, is actually to do what's called jittering these points. We might be familiar with jittering, like kind of you have the jitters about you being nervous or excited here. It's kind of the same idea with these points. I could take this point here and I could do what's called jittering it. I could say, well, I don't really care if it's exactly where it needs to be. As long as these 2 points are just slightly separated, that's good enough for me. I'll erase this point here, but keeping track where I had it. I'll put 1 point slightly below and 1 point slightly above, and now we see 2 distinct points, even though they have the same value. We kind of jittered them around so they have a non-overlapping visual here. So as you go about plotting these points, keep in mind, if your data has these overlaps and you care about seeing each individual point, you might want to do what's called jittering them so you can see all of them and not just some of them in terms of overlaps as well. So one thing left to do now is to translate this into code. So let's go back now to RStudio and see if we can make a plot like this with ggplot. Come back now over here, and let's take a look. Here I have a file called candy.r, and the first thing it does is load for me this file called candy.rdata. Now inside candy.rdata is this data frame called candy. So if I were to run line 1, I'll now see that I have this data frame called candy. And inside is much more than just 5 candies. I have lots of different candies in here, and their price and sugar percentiles. So let's see if we could visualize them using ggplot. I'll come back now to candy.r, and of course we'll begin with our ggplot function to begin with a new blank plot, just like this. I now have my blank canvas that I can add layers to. Well, the first thing I might want to do is say to ggplot what candy, or what data frame are you using here? In this case, the candy data frame. So I'll pass as first input here, candy, and then I'll also assign some aesthetics. I should probably assign the x and the y axes as we saw here on my chart. I'll say aesthetically, I want the x-axis to match the price percentile column, and I want the y aesthetic, that vertical bar, to match the sugar percentile column, just like that. And this is getting a little long as a line, so I will, on one line, put the candy data frame, and on the next line, put these aesthetic mappings, let's say. And this is the very beginning of my plot. In fact, if I were to run what I have right now, I would actually see that ggplot has constructed for me a plot that has these axes. Notice how on the bottom I see price percentile, and on the y-axis I see sugar percentile. Very similar to what we have in our chart here, but just different kind of numbers that we're seeing in the individual axes here. Here I have 0, 50, 100. Here I have 0, 50, 100. Here I have 0, 25, 50, 75, 100, and so on. So same thing, but different numbers on this plot here. So what more could we do? Well, we want to visualize these points, which we can do using a new kind of geom. We saw geom call last time. Let's see what geom point could do for us. I will add a new layer to my plot, let's say. I'll come back over here, and I will add this geom point layer, which will draw for me these points according to every individual row that I have. Geom point will look at my data frame and make a new point for every individual row I have of candy inside this data frame. I'll go ahead and I'll run this, and what do I see? Well, now I see lots of individual points representing the candies I have, their price and their sugar content. Now, the relationship seems a little bit less clear here. If you pay more, maybe you get more sugar, maybe not. Depends, it seems, on the candy. But I'd argue we're running into the same issue we just saw with this physical plot here, which is if any two candies have the same price and sugar percentile, well, they're going to be overlapping each other. And in fact, I can show you a few points that do just that. If I come back now to my table and show you in the candy data frame, let me sort this by price percentile and scroll down a little bit more. Here I'll see that between Hershey's Crackle, Milk Chocolate, Special Dark, these all have the same price and sugar percentile. So these would appear as only one point on my plot when I ideally want to separate them, even just a little bit. So to do just that, I can use a geometry not called geom point, but one called geom jitter, where we said we were going to jitter our points, meaning kind of move them around a little bit randomly, but still, so they're still in the same, roughly the same place that they're supposed to be. So I'll use geom jitter here, and I'll run this top to bottom, and I'll see ever so slightly my points have changed. And I now am more able to see individual points, particularly around these you might see just a bit of separation. Around these you might see a bit more separation here too. You can tell ggplot how much to widen or to change the height of these points here, but for now we'll leave it as the default, where we can now see a little bit more of these individual points. I'm going to go ahead and improve this chart some more. Here I want to probably add some labels, like renaming my x-axis and my y-axis, adding a title. And let's go ahead and set our theme too. I'll come back now to RStudio, and let me change this. I will add in a label layer, and I'll set the x label equal to price, the y label equal to sugar, and the title of this chart will be simply price, price, and sugar. And then finally, I'll go ahead and adjust my theme. I'll again use the classic theme here, and we should see my chart is now coming into shape. So What have we done? We have started again with this blank canvas and given as input our candy data frame. We've told ggplot we want to map the price percentile column to the x-axis, as we just did here. And we want to map the sugar percentile column, as we just did, on the y-axis here. We're going to go ahead and add in these points and jitter them just a little bit so we can see those individual points too. We're going to add labels and set our theme. Let me ask, what questions do we have so far on this point geometry, jittering our points, or anything more related to this plot here?
When does this plot is preferred over the column?
Yeah, really good question. And it's one you probably will run into very frequently when you're visualizing your data is what type of visualization is best here. Now, when we have data that involves both categorical and continuous variables, like we saw in our candidates, remember we had called the x-axis a discrete scale or a categorical scale. It had individual candidates, and each of those candidates had some continuous value associated with them, their number of votes. That's a good kind of data to use for a bar chart or a column chart. Here, though, we have actually two continuous variables, two continuous scales. On the x-axis, I see a range of values between 0 and 100. And on the y-axis, I see the same thing. Well, if you have a continuous range of values on both your x-axis and your y-axis, that's going to be a good hint. You probably want to use something like points, for instance. You could imagine using columns here, but I'm not exactly sure what that would look like. Maybe I need to have two columns for each of my candies, one for sugar content and one for price content, which wouldn't quite show me the relationship between price and sugar. Here I argue that this shows us much better the relationship between price and sugar when both are continuous, that is on this individual scale here between 0 and 100. But a good question and one to consider as you go off and design your own plots too. Now let's go ahead and tidy this up a little bit more, and maybe I can go ahead and actually do one thing, which is the title doesn't appear to be showing here. I have price and sugar, but I didn't set the title of it here, so let me go ahead and go back and change that. I will update the label layer to instead say the title is price and sugar. Let me rerun this, and we'll see price and sugar up top. But now, one kind of fun thing I could do is change the color that I see on these points. And it turns out that there is an aesthetic that I can apply to my points here with geom jitter, one called color. Now, one color I kind of like is this one called dark orchid. And in R, you can actually have access to certain colors that are known by given names. So there's one called dark orchid, and we'll see here that RStudio has automatically shown me what color dark orchid is. But you also have more primary colors like blue, or like red, or like green, and so on. And it turns out that this color aesthetic, when applied to this point here, well, actually it'll change the color of these points we're seeing. So I'll try to make these points, this color dark orchid, which kind of evokes some candy here for us. Let me go ahead and see what that does. I'll go ahead and run this, and now I'll see that my points have changed to this color dark orchid. Now notice here that we're not specifying an aesthetic mapping. An aesthetic mapping tells ggplot to map some column in our data to some given aesthetic, like X or Y, or even color if we wanted to. What I'm doing here instead is saying, well, all points should actually get this same color. If I want to apply any aesthetic to have only one value, I don't need to use the AES function. I can simply say the aesthetic name, and then the value I want it to have inside the geometry I want to apply it to. So in this case, I want to change the color of these points that are jittering about and change it to dark orchid in particular. Now, one other aesthetic we could change to is one called size. Well, these points have a certain size, a certain radius, a certain size on this page here that I could change using this aesthetic called size. So let me go back and do just that. I'll come back to RStudio, and let's try changing the size of these points to be maybe a little bit bigger. I could set size, which is by default somewhere between 1 and 2. Let's use like 1.5 or so. I could change this perhaps to maybe 2 to make it just a little bit bigger. I'll go ahead and visualize this, and we'll see my points are now just a little bit bigger. I can make them even bigger. I can make them maybe size 4 or so, just like this. And now we're better able to see our points because they're bigger, but there's still a lot of overlap here. So one thing you could do is maybe make them smaller to reduce that overlap. I'll come back over and say, let's change this from 4 to maybe like a 0.5, make them pretty small. And now we'll be better able to see these individual points. I think I'll leave it somewhere around 2 or so to make this chart more visually interesting, but you can have access to this aesthetic called size to change what your plot looks like in terms of how big these dots actually are. Now a few more we can work with. One is all going to be called, in this case, fill, and one is going to be called shape. We've actually seen fill already when we filled in our columns, but we can also supply the fill aesthetic if we change the shape of some of our dots here. So let's go back to looking at our dots, and let me play around with this aesthetic called shape too. Let me go actually and put this above size to keep these arguments in alphabetical order here. I'll say that shape is equal to, well, what do I want? I mean, it turns out I can't specify something like triangle like this, and I can't use something like square like this. I actually have to put in some numbers here, and if I look up on the ggplot reference what numbers correspond to which shapes, I can actually see which shape I want and type in the corresponding number. Let's go through a few of these here just to see what they look like. I'll change shape to be 1 and see what I get. I'll go ahead and rebuild this chart, and now I see my dots are still there, but they're a little more translucent. I see here that they have the color on the outside, and on the inside they seem to be transparent. I actually see through to the white background at the bottom of this page, if you will. I could change to a different shape too. Let me come back and try maybe the second shape option we have, shape equals 2, and now I get triangles, which is kind of cool. I could also use maybe shape 3, and now I get some plus signs. There are lots of shapes you can play around with and use depending on how you want to visualize your data and change things aesthetically. Now one shape I like in particular, particularly for this kind of data, is going to be shape 21. And I only know that because I looked it up online. I went through the shapes in ggplot, and I found that this shape corresponds to the number 21. So let's see what that looks like. I'll come back over here, and I'll try shape equals, in this case, 21. Let me go ahead and rebuild my plot, and I'll see those translucent points again. But it turns out that actually this shape 21 allows us to specify both a color and a fill, where the color, to be clear, is this color on the outside of the dot, and the fill is the color on the inside of the dot. So I could have kind of a two-tone dot here with some border around it that's a little bit darker and some fill that's a little bit lighter to make it more aesthetically pleasing. Well, let's try setting the fill aesthetic here. I'll come back to our studio, and let me change, in this case, the fill aesthetic to be a color that I found in R's manual called just regular old orchid, like this. So my color, my border of these dots will be dark orchid, and their fill, the color on the inside of them, will be this kind of pinkish purplish color called orchid. I'll go ahead and rebuild this plot, and now I'll see some kind of two-tone dots. I see here that I have that ring around them in dark orchid, and in the middle I see that color orchid for their center fill. So here we've now played around with different aesthetics for our dots, including color, fill, shape, and size. There are more at your disposal too, but more on that another time. And this, I think, is a pretty good plot. We've built it up from scratch, adding in our dots, our aesthetics, our labels, and our themes. Let me ask what questions we have on designing plots now with points.
Is there a way to randomize the dots in the color of the dots in the plot?
To randomize the color of the dots? Yes. So one way we could do it is specifying a new aesthetic. So if we ever want to vary a certain aesthetic, like let's say color or fill or shape or size based on some data, whether it's random or not, we would need to specify an aesthetic here. So you could imagine specifying a new aesthetic mapping, one that involves color and is associated not with a column in your data set, but some random data you give it. And you could certainly do that to make sure the color is randomized across these different dots. But a good question too. One thing I'm seeing is that I think people are trying this and seeing that shape, I can actually specify a text input to it. So let's try that. I'll come back over here, and I said that we couldn't do something like type in square, or triangle, or things like that. But let's just try it and see. I'll go ahead and type in square, and I do get squares. Maybe triangle here, and I'll type in triangle. Whoops, triangle. And I'll see I get triangles. I could try circle too, just to see what we could go off and do. And now I see circles, so it seems like some basic shapes you can specify, but in general, what we'll tend to do is specify these shapes by numbers, looking them up in ggplot's reference now to determine which shape it is we want, like 21 that has both this fill and this color aesthetic here. Pretty cool. OK, so we've seen now how to visualize relationships between two continuous variables, in this case price and sugar. When we come back, we'll see how to visualize change over time in the context of hurricanes. We'll see you all in 5. Well, we're back, and what we'll do next is visualize data that changes over time, otherwise known as time series data. And we'll do so in the context of a particular hurricane named Hurricane Anita that happened in the Atlantic in 1977. Now, here's a picture of Anita making landfall in Mexico, and thankfully it did so in an area that wasn't very heavily populated, but it still unfortunately did much damage. So by looking at this data and visualizing it, we can actually hope to learn how hurricanes like these evolve and change over time so that we can better prepare for them and ultimately respond better to them in turn. Now, here are some observations of how Hurricane Anita grew over the days that it was active. Here, I have a column called wind speed, or just called wind, and it's representing wind speed in terms of knots, this kind of nautical term for how fast the wind is blowing. I here have a column called timestamp, too, that tells me on what date this observation was taken, and what time, too. So here I'll see that this one was taken in 1977 on August 30th around 12 noon. And the wind speed of Anita was known to be about 50 knots in total. On the next day, on August 31st, also at 12 noon, the wind speed was about 75 knots in speed. So here we can see how Hurricane Anita is evolving over the days, that it's growing actively too. Now, how could we plot this data? Well, we could do it very similar to what we saw before, putting points on our plot, like we did with candies here. Maybe on the x-axis we have our timestamp, and on the y-axis we have the wind speed. That's exactly what we have over here. So here I have a plot where on the x-axis I put the date, in this case August 30th, August 31st, September 1st, September 2nd. And on the y-axis I now have the wind speed in knots, going all the way up to 160. Now, to plot this data, I could go point by point and add it to this chart here. Maybe for the first one I see, this happened on August 30th, 12 noon, the wind speed was 50. So if I look at this plot, I might look and see, well, August 30th and the wind speed being about 50, or right up here. Now, true to how ggplot works, let's go ahead and add a new layer to our plot here, one for these points we're adding. I'll go ahead and put this over my axes, and let me go ahead and draw this first point. I'll say August 30th is equal to wind speed of about 50. So I'll put it above August 30th and kind of beside, let's say, where 50 might be, right around here, let's say, for our first observation. On the next day, Anita strengthened, and it was about 75 knots on August 30th. So I'll go ahead and add that here. I'll go over to August 31st and say it was about 75 knots. I'll go maybe just below 80 on my y-axis, somewhere right around there. And then on September 1st, well, Anita blew about 90 knots here. So 90 would go well above September 1st, and maybe between 80 and 120, so somewhere around there, let's say. September 2nd, Anita blew 120 knots, so let's go over and add that one. I'll put that one kind of right beside 120. Let me put that one right here, and let me lower this one just a little bit to be sure. Make sure we're accurate here. And this, I think, represents the points that Anita would have as it grew in wind speed over time. Now, one thing I could do to make this even more apparent as change over time is maybe connect these dots with a line. And so I could very much do that by adding a new layer here to my plot. I'll add this on top, and I'll decide, well, I want to connect these points to show how Anita grew over time. I'll start by connecting these first 2 points here. This one between August 30th and August 31st. I'll draw this line here, and now I've seen how I need to change between August 30th and August 31st. I'll do the same now for August 31st to September 1st, just like this, and the same again for September 1st to September 2nd, just like this. And now I argue I'm better visualizing change over time. I'm seeing how this hurricane strengthened over the days that it occurred and how it grew to be a full-fledged hurricane. So let's see how we can make a plot a bit like this now using ggplot itself. I'll come back now to our studio, and let me go ahead and open up this data file called anita.rdata. And inside anita.rdata is this table here, one called Anita, that tells me many observations of how Hurricane Anita grew. And here, see, I have more than the observations we saw on our slides. I have multiple for each day even. Let's see, on August 30th, I have the midnight observation, the 6 a.m. observation, the 12 noon, the like 6 o'clock observation. There's a lot of observations here in more detail of how Anita grew. But we still have those same columns, timestamp and wind. So let's use them now to visualize this data in terms of a plot. I'll start, as I usually do, with our ggplot function to give myself this blank canvas to work with. I'll then pass in as the first argument to ggplot the Anita data frame, just like this, and I'll assign these aesthetic mappings. I want to make sure that the timestamp column falls on the x-axis and the wind column here falls on the y-axis. So I'll assign them in terms of these aesthetic mappings now. I'll say that x equals timestamp and y equals wind, just like this. And of course, given what I have now, I have my scales on either the x and the y-axis, but now I want to add in my points that I just made originally over here. I'll add a new layer, now syntactically in ggplot with this plus sign, and I'll say geom points, what I want to add to this first layer. And now, with this more complete set of observations, do we see exactly how Anita grew over the days that it was considered a storm, all the way from August 30th or so to September 3rd or so. But we ideally want to connect these points, showing change over time. And thankfully, we do have another geometry we could use, one called geom line. So let's do just that and use geom line to connect these points. Well, similar to what we just did over in this demo table here, by adding a new layer to our plot, I could do the same. I could have more than one geometry on my plot. I could have one for points and one afterwards for, let's say, lines, just like this. Geom line draws lines between all of the data points that we have. So let me go ahead and run this here, and I'll see now all of these dots are connected by lines. And in fact, my plot has multiple layers similar to this one. One layer are these lines, one layer are our dots here, and the bottom layer is our aesthetic mappings in our blank plot here. So I'll go ahead and remake this plot right here, and we'll see the same over in ggplot to be sure. Now let's spruce this up a little bit more. I want to maybe change the labels here, give it a title, so I'll do just that. I'll come back over to RStudio and add in a label layer. I'll say, let me go ahead and add some labels, make sure the x-axis is, maybe let's call it date like we did over here, and I'll go ahead and say the wind column is just called wind, but we'll call it maybe wind speed in knots to be more specific, and then we'll go ahead and say the title is going to be Hurricane Anita, to be clear what we're visualizing here. Let me rebuild my plot, and I'll see all of those labels now in place. So we're getting pretty far, but what else could we do to improve the design of this plot? Well, I'd argue that we could play around with some colors here and make sure it looks a little more amusing, a little more interesting to look at. And one thing we could do is experiment with the color for these points. So we saw before that we might want to change colors of points. We can do so by setting this color aesthetic inside of our geom point or geom jitter. Both of those are drawing points for us. Well, inside, let's say, geom point, I can go ahead and say I want to set this color to be equal to, well, one I found is called Deep Sky Blue 4. I looked this up online, and it was a pretty cool R color, kind of symbolizes hurricanes, at least for me. I'll go ahead and reload this plot, and we'll see I now have these dots here, now colored too. But if you look a little bit closely, I'll see that this line is actually overlapping these dots. And I'm not sure that's what I want. I think what I really want is for this line to be behind these dots. And so similar to thinking of our plot in layers, it seems like I drew the points first underneath the line layer. And so the line, of course, will kind of overwrite or be on top of the points. If I want it vice versa, I should change the order of these here. To the question about ordering earlier, if you want your geometries in a certain order, one on top of the other, well, ordering does matter in that case. So let me switch now geom line with geom point. Come back over here, and I'll decide now to change this to have first the lines drawn, just like this, and then the points drawn on top of them. Let me rebuild my chart, And now, subtly, we'll see that the lines are behind the points, and the points are now in front of them. So here we've seen our very first chart using both geometries, point and line. Let me ask, what questions do we have about how we visualize this hurricane and its growth so far?
It's in formatted in the graph, but it is not well formatted in the data file.
A good question about the format of your data. And so it kind of harkens back to last time we were learning about clean data, making sure our data is clean before we actually can visualize it here. The reason I'm able to visualize this plot is because I have my data in a certain order. I have each individual column that I can then map to individual axes here. If my data were not in that shape or in that format, I couldn't do what I'm doing here. So it is important to make sure your data is in the right format in order for you to visualize it in the way you want to visualize it. But more on that actually last time when we saw how to clean data as well. Well, let's keep going and making our chart more visually interesting. And we've seen now these points, but what about these lines? How could we change how they look? Well, it turns out that geom line, or this line geometry, has its own aesthetics we can play with too. And I'll show you two of them in particular. Let's come back now to our studio and play around with a few of these aesthetics. One of them is called line type, and one of them is called line width. And kind of true to their name, line type changes the type of line, let's say whether it's solid or dashed, for instance, and line width changes how wide this line might look. So I'll come back now to our studio. Let me try to adjust the style of this line. Well, maybe I'll first play around with the type of line, and I can probably do so by specifying some number, much like we did for shape. There are a few different line types, among them the solid one that we see here, dashed, dot dash, and so on. Let's just see what a few of them look like. Here, line type 1, if I build this, well, line type 1 is exactly what we already have. Line type 2, what's that? I'll visualize this, and now we'll see kind of a dashed line. I'll see that there are some translucent parts to this line, and I see dashes now between each individual, well, dot and really on the line in general. Let's try now maybe line type 3 and see what that looks like. Line type 3 seems to be, well, more so dotted. I see not full dashes in my line, but now individual dots separated by spaces. So there are many line types. I encourage you to play around with them, look in the reference, and see what kinds of types of lines you can create with ggplot. Now, one other one we saw earlier was line width. How wide or thick should this line be? Let's play around with that too. I'll come back now to our studio, and let me change my line type back to 1. I kind of like that one the most, and I'll use line width now, where line width might be, well, let's just try 1 and see what that gives us. I'll hit enter here, and my line is a little bit thicker than I'd say it was before. It is pretty thick here. I can see it kind of connecting these lines still. I can make it even more thick, or probably I'd argue I want it to be a little bit thinner. So I'll make it smaller than 1, maybe something like 0.5 or so. I'll go back over to line width and say I want it to be 0.5 in size. And I'll see this seems more reasonable in terms of a width for my lines. And I encourage you to experiment with these line widths and see which one actually best represents your data. So here, we played around with these line geometries, but we could probably still improve this chart a little bit more. I think I want these dots to be a little bit bigger. And we saw how to do this just last time. I could specify in geom point a size for each of those points. Not just a color, but also I want to say the size of these is just a little bit bigger than usual, maybe a 2 instead. And now just barely, these dots are a little bit bigger, and I think we're now seeing our data just a little bit better. I'd say this looks pretty good. Now, let's go ahead and add in our theme here. Let me go down to the bottom and say I've added in all of my geometries, my points, my labels. Let me go ahead and say I want this classic theme to tidy things up here. And now I'll see my chart, as I'm pretty sure I want it to be. Now, this is pretty good as a chart, but I think there's more we could do to it. One thing we could do is figure out when exactly Hurricane Anita became a hurricane. In fact, hurricanes start as these lesser storms, known as tropical depressions or tropical storms, and they grow to be hurricanes. Well, here, we don't quite have a sense of exactly when Hurricane Anita became a hurricane. But it turns out that hurricanes are considered hurricanes when they reach a wind speed in knots of 65 knots. So it seems like any dots that are above this 65 mark on my y-axis, well, that indicates when Anita was a full hurricane. So if I want to add not just data points, but some arbitrary line, well, I could do that just as well here too. Effectively, what I would do is add a new layer now to my plot. I'll do that on our visual here. I'll take this plot, and why don't I draw a line indicating when this hurricane became a hurricane. And we know it does so when the wind speed is greater than or equal to 65 knots. So I could draw maybe somewhere between 40 and 80, right around here or so, a line, maybe a dotted line saying that above this line, Hurricane Anita was in fact a hurricane. Now, similar to what I just did, by adding a new layer to my plot, I can do the same in ggplot. And I'll use this geometry called an H-line for a horizontal line. We also have a V-line for a vertical line, but here we'll focus on this horizontal line here. Let's come back now to RStudio and see what it would look like to add this H-line, this horizontal line. Well, I probably want it to come after I add in my lines and my points. I'll go ahead and add this layer after I specify my points here. And I can do so by using geom underscore hline. For this horizontal line I want to add to my chart. I'll finish this off with a plus to make sure to add my labels later on. And now there are a few parameters I can specify in terms of this hline. One I could specify is still the line type. It is a line, so it has that same aesthetic of a line type. I could change that for hline perhaps to this dotted one we saw earlier, which was line type 3. But let me go ahead and try to visualize this. I'll go ahead and run, and I'll see I actually get a warning, or really an error. Geom hline requires the following missing aesthetics: y-intercept. What is a y-intercept? Well, as the name kind of implies, it is the place that this line intercepts or crosses with this y-axis. In our case, we said that whenever a storm gets to 65 knots or higher, that means it is a hurricane. So it seems like the place that this line intercepts the y-axis is, well, 65 knots. So I could, as a parameter to hline, geom hline, say that the y-intercept should be 65, meaning 65 knots. I'll come back now to RStudio and do exactly that. Let me go ahead and say that the y-intercept of this line should be 65. Exactly that. And then I'll go ahead and say, let me run this top to bottom. And now I have a pretty neat graph. I see the evolution of Hurricane Anita. I see what days it was considered a full-fledged hurricane. And I also see what days it was not a hurricane, but a tropical storm instead. So we've gone from an empty plot to adding in many geometries. We've added in dots and lines and horizontal lines and so on. We've added in our aesthetics in terms of X and Y and color and so on. We've added in our labels and our themes too, making this final plot. What questions do we have on what we've done so far?
Hi, I was asking if it is possible that we do the color designing, the color visualization. Like anything above the 65, you change the color, or maybe change the line color or something.
I really like the way you're thinking. Yeah. So you're considering what could we do to make this plot more colorblind friendly? And that's a really good consideration when you're working with different colors. Having those colors mean something distinct in your data. I would argue that in this data set, this plot, the colors are more aesthetically pleasing. They aren't really showing me information in this plot. But if I wanted to, I could choose colors that are friendly to those who are colorblind. And actually, a good thing I could do is if I used multiple colors beyond just, in this case, black and blue, well, I could choose colors that are distinguishable to those who might have some form of color blindness. And for that, I could actually look up what colors I might be able to use to make sure that that works for various forms of color blindness. The Viridis scale might be a good place to start. But here, because I just have black and blue, I'd argue that this is going to be good enough for now. But a great question here. OK, so we've seen now, all in all today, how to visualize groups of data and values associated with them. We've seen how to visualize relationships between two different columns in our data. And we've also seen how to visualize data over time. When we come back, we'll see how to actually test our programs to make sure they work as intended. But more on that next time. We'll see you later on. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Goddard Tan, and this is our lecture on testing programs. We'll see today all the ways our programs could go wrong, learn how to handle these things called errors, and see how to test our programs to ensure they behave as we intend. So let's jump in and see all the ways a function I've written could go a little bit wrong. I have here in RStudio a function I've defined called average. And this function average is defined in this file called average.r. And the purpose of this average function is to take as input a vector of numbers and return to me the single average number it finds across all of those numbers in that vector. So notice here how I'm using the built-in functions sum and length. And you might know, if you're familiar with averages or means, that that's defined as basically taking the sum of numbers you have and dividing by the number of numbers you have. So that's exactly what I'm doing here with sum and length. And let me go ahead and presume that I figure that sum and length are correctly implemented. I can rely on these functions just as well in my own function called average. Now, it turns out there is already a function called mean, which does this very same thing built into R. It returns to us the mean or the average of some set of numbers. But our goal today is to write our own version of that function called average, so we can kind of see the design decisions that went into writing a function like mean in R. So here is my average function. Let's go ahead and try it and think about what could go wrong, actually. So I said before that this function average should take as input a vector of numbers. But we've seen some ways a user could give us not numbers, but text. If you recall using readline, you might know that readline by default takes as input text and hands us back text. So maybe we might have forgotten to convert that text to a number. I could run average in my console here, first defining it up above on line 1. I could run average, and let's say I've forgotten to convert some input from the user to a number. And I instead have now a vector of characters, or character representations of these numbers here. So I'll pass as input this vector 1, 2, and 3, but those are not numbers per se, they're actually characters here. I'll go ahead and run average, and well, now I'll see this error. This is probably not the first time you've seen an error. Probably when you're programming, you've seen lots and lots of errors, but let's give these errors a more formal name. So these errors are more formally called exceptions. And an exception occurs when something exceptional happens in your program, but not in a good way. It happens when our program encounters some situation, some scenario it doesn't know how to handle, and instead it stops entirely. So a question then becomes, how could we handle these exceptions or these errors in our code? And one way to do so is to handle them more proactively, preempt them, and do something else instead of encountering this error or this exception. So let's see if we could take that approach now in our own function here called average. I'll come back now to RStudio, and let's think through what exactly caused this exception. Well, if I look at it here, I'll see that I gave the sum function, it seems, some invalid type, character of argument. So it seems like the problem was, in fact, that I gave as input to the average function this vector of characters. So what could I do to check for this before I maybe pass this input down into sum and length? I could probably use something like a conditional to ask some question. But what question would I ask? Well, I probably could ask, is this vector numeric or is it not? And maybe I would consider the case where it isn't numeric, where I might get an exception and handle that case in particular. So here, before I run line 3 now, trying to sum up these numbers and finding their length and dividing therein, why don't I go ahead and try to ask the question, is, let's say, this vector x, is it not numeric? Just like this. So I'm going to make use of now this function is.numeric, which asks the question, returns me true or false, is x a vector of numbers or is it not? And when I use this exclamation point here, I'm essentially asking, is the vector x not full of numbers? And now I have the option here of handling that error before it might happen down here on line 5. So what could I do to handle this error? Well, a convention sometimes in the R world is to return a special value, one like NA. So if we give as input to our function average a vector that doesn't include numbers, I could say, no, let's stop here and just return NA instead of getting this error ultimately. So I'll go ahead and do just that. On line 3, I'll say if we find that this vector x is not full of numbers, is not numeric, I'll go ahead and return NA instead. And hopefully I'll now avoid this error by kind of preempting it and handling it up above. Let me go ahead and redefine my average function now to update what it has included here. I'll go ahead and run the same thing I did before, giving as input to average this vector of characters, and I'll see I'll get back now just NA and no error. Now we've handled it, preempted it before it has had the chance to arise in this case. But if we're going to do something a little unexpected here, like return NA when the user might have thought they were getting back a number, it's worth thinking about how to alert the user to that fact. Right now, we're handling this error silently, if you will. Meaning we're not going to raise anything to the user. We're just going to hand them back NA. And unless they looked at the return value, well, they wouldn't know anything in particular was wrong or that they had done anything wrong. So let's think through how we could alert the user here and let them know what it is exactly we're doing here. Now, one way to do that is to make use of this function built into R called message. Message allows you to essentially send a message to the console while a function is running. So let's see if we could use message here. I'll go back now to my function, and maybe before I return NA, I could let the user know what it is I'm about to do. I could decide to send them a message using the message function. And it turns out that as input to this message function, I can provide the character string showing the message I want to tell the user. Well, I want to tell them what it is I'm doing and probably tell them why I'm doing it. So first I'll say that maybe this input, x here, our vector, I'll say that x here must be a numeric vector. So this is the cause of why I'm returning NA and not, let's say, the actual average. And now I could say what I'm doing instead. I'm going to return NA instead. Now, if I were to run this function, I need to first redefine it, go back down my console, and provide the same input. And now let's see what happens. I'll see that message. So now we're not being silent anymore. The user who's run this function, they would get back NA as their return value, but now they would know it. They would say x must be a numeric vector returning NA instead. So we've kind of gone away from being silent, and now the user knows exactly what has gone wrong, perhaps, in this function. So a little more intuitive now. But it turns out that by convention, message is often used when things are going just smoothly. We're trying to tell the user exactly what's going on. It kind of tells them a bit of a progress indicator, gives them an idea of what their function is doing. It's meant to be used in cases where something has not gone wrong. But I'd argue in this case, like something has gone wrong. We gave as input to the average function an input it should not have been given. So there are ways to take a message and to escalate it, if you will, in severity, to let the user know that actually something has gone wrong. There might be a potential issue here. Now, if we were to escalate this message, we could instead convert it into something called a warning. Now, a warning is good when your function encounters something that is a potential issue. It's a bit similar to if you've driven a car and your check engine light pops up. Whether you're driving that car, you'll know that, well, your car could still continue running, but you might want to check under the hood and make sure everything is going as you expect it to. So a warning tells a user that something has gone wrong that could be a potential issue. And I think this is more in line with what's happened here. The user has given us a value that they really shouldn't have given us. So let's, instead of messaging them, warn them and tell them that, look, you should not have done this. You should make sure this is exactly what you want in the end as far as the return value. So I'll convert message here to a warning instead, just like this. And now that means that the user will not get a regular old message. They'll get a warning indicating some potential issue. I'll go ahead and back to line 1, and I'll redefine this function. And now what will happen if I run it again with that same input, I'll see I get not a message, but a warning message. In this case, I see warning message in my function, and its input here, the exact message I typed on line 3. X must be a numeric vector returning NA instead. So this is a way of alerting the user that they might get some value they didn't expect because there was a potential issue, which is they didn't give us an actual numeric vector. So a warning then is good for some potential issue in your function that it could still recover from. We could still return NA here. But there is one more level of severity, going from a warning to a full-fledged error. I think we could here have a discussion of whether a warning or an error is best for this scenario. On the one hand, I could argue that this function average is supposed to fundamentally take a vector of numbers and return to me a number. If I haven't done that, my function cannot accomplish its goal at all. In that case, I might not want to just warn the user and return NA.
I might want to just stop entirely and say, look, you've given me an input and I have no idea what to do with it. I can't handle it at all. I'm going to stop my function in its entirety. So let's see what it would look like if we actually not just warn the user, but stop the function entirely. Now, just so it turns out that R has this function called stop that allows us to raise or to throw this error. So let's upgrade now our warning to a full-fledged error using stop, letting the user know that we simply cannot proceed with the input they have given us. I'll go back now to my average function, and let me go ahead and use stop, much like I used message and warning. I'll give it an error message in this case, but now what I should do is not return NA. In fact, if I were to run this code, I would never get to line 4, because as stop implies, my function will stop on line 3. It will not continue. It will not return any kind of value in this case. Why don't I go ahead and remove line 4 now? And now what will happen is this. We're going to ask the question, is this input numeric or is it not? If it's not numeric, well, I will throw or raise this error that the user will now see. Let me go ahead and run or redefine this average function, pass as input the same thing we've been doing so far, and now I'll see, well, an error. And we're kind of back where we started, giving an error now, but this one is more precise. It's one that we've raised or thrown ourselves, and it tells us exactly what has happened and why it has happened. Here we see error in our function average. X, the input, must be a numeric vector returning NA instead. And actually, that's probably not true anymore. So this stop on line 3 doesn't seem to return us anything, at least not NA now. So let's go ahead and remove that message here to make sure that the user doesn't anticipate an NA. Why don't we just say X must be a numeric vector. I'll go ahead and redefine it, and now rerun it, and we should see exactly the error we were hoping to see here. So we've seen now how to talk to the user and message them about these kinds of potential issues in their functions. We've seen message, we've seen warning, we've seen stop. Let me ask now what questions we have about any of these functions so far, and how we convey or communicate about these errors that could happen in our functions.
What's the difference between using message versus print versus cat to display an error message?
So a good question. We've seen so far these functions like print and like cat, and now this one called message that all seem to show us some text in the console. Well, a message is a more special kind of text output that we could later on choose to suppress. So you've probably seen so far suppress warnings. There might also be a function called suppress message you could use to hide those messages as they come up. There is no such feature, though, for print or for cat. A message is more particular and exclusive to showing the user a message they could either view or decline to view later on. Good question. OK, so let's consider other scenarios here that we could try to address in our function. We've considered so far what happens if we don't get the type of input we're expecting, in this case, a non-numeric input. But there are other scenarios we should probably consider and anticipate. And one of them might be if our input has NAs in it. So we've seen that the mean function, if it's given some input that has NA, well, it returns to us NA instead. So if we want our function to do the very same thing, maybe we could have a check here. Maybe after I check to see if the input is numeric, I could ask another question. I could ask this one here. If any, let's say, if any of the values in this x vector are NA, just like this, why don't we go ahead and do something else before we run now line 8? But what is it I should do if any of these numbers are NA? Well, I could, of course, return NA like we decided to do earlier, but now there's a question here. I don't want to silently return NA, and I have 3 options. I could either message the user, I could warn them, or I could throw an error using stop. Let me actually ask our audience here. What would you use? Would you use message or warning or stop in this case? How might you try to handle this particular input?
I think it because is that if something or an error happened, it will show the user when the error.
A good point. So we've seen that message is good for just conveying information when there's nothing really wrong going on, whereas a warning is good to mention a potential issue the user should take a closer look at.
And I'd argue that in this case, a warning is probably better. We're doing something a little unexpected. We're returning NA as opposed to, in this case, the average the user might have been expecting. So I think a warning would be best here to alert the user that there might be some potential issue here. I'll come back to RStudio, and let's go ahead and actually implement now this warning. I'll do it the same way I did before with warning here. Before I return NA, I'll give a warning. And in this case, I'll say as follows, that X, our input now, contains one or more NA values, just like this. So now my function is looking a little bit better at handling these kinds of cases I might not have anticipated. First, if we get a non-numeric input, we're going to go ahead and stop. We fundamentally cannot continue with a non-numeric input. Then we're going to ask the question, if any of the values in our vector x are NA, well, we're going to warn the user and tell them that x contains one or more NA values. They might not know that yet. And we're going to ourselves return NA by convention here. If, though, none of these conditions are true, we're going to go down to the bottom here, and we're going to return the average just as we would otherwise. So let me go ahead and run this definition for the average function. I'll go ahead and give it, let's say, some faulty input like we saw before. I'll get the error like we see. Why don't I try now giving it an input with some NAs? I'll give it 1, the number, 2, the number, and 3, NA. Let's see. Now I get NA back and this warning message down below. Well, let's try a normal input, average, and I'll give it 1, 2, and 3, all numbers. Here we'll see the average of those numbers, 2. So I think our function now is much better designed. We're able to handle these edge cases that the user might have given us, and now we can alert them to exactly what we're going to do to handle those cases. Now, when we come back, we'll see how to actually test this program, this function in particular, and make sure it's behaving like we intend. We'll come back in 5 and see how to test programs like these. Well, we're back, and we've seen so far how to preempt a few potential errors in functions we've written. What's next is actually test our code to make sure it behaves as we intend. And we'll do so by writing what we'll call unit tests. Now, a unit test is some code that we write ourselves to test some unit of our program. But what are those units? Well, programs are composed of individual units called functions. So unit tests now are code we can write to test individual functions inside of our programs. And we'll go ahead and write some unit tests of our own by now testing our average function. So let's go ahead and do just that. I'll go back to RStudio. And I will, by convention, to test this function average, create a new file called test-average.r. So I will go ahead down here and I'll say I want to create a new file called test-average.r, and I'll see that file was created for me. If I now go to my file explorer over here, I can open up test-average, and I'll see a blank page in which I can write my tests for this average function. Well, again, by convention, what I'll do is write a function to test this code that I've written now in average.r. In particular, this function average. I can call it test_average, just like this, and I'll make sure it is a function. It doesn't take any inputs for now, but within this test here that I've written, this function I can use to test my code, I'll then provide one or more test cases. Now, a test case is some representative scenario our function might encounter. And we want to ask the question, did our function return the right value for this particular scenario? So if I want to ask a question, like I could do that using a conditional, as we've seen. So maybe I'll ask the question here, if, let's say, average, and they call our function, and give it as input this vector we saw earlier, 1, 2, and 3, all numbers. If the return value of average given this input is equal to 2, well, what should I say? I could probably say in this case that average, my function average, passed the test. And I'll give it a little smiley face just for fun here. Otherwise, though, if I don't get that value back, what should I show to the user or to myself here, the programmer? I could probably say something like, well, average failed the test, and give me a little sad face to make sure I know what's going on. So this is my first test for this function average. Notice how I've defined one test case. My test case is when I give average the input 1, 2, and 3 as a list. I then expect that I'll get back the value 2, and if I do, I'll say that average passed the test. If not, I'll go ahead and say we failed the test. And now for cleanliness here, let me go ahead and say \end, add a new line to each of these messages here. And why don't we go ahead and try to run this test average function? Well, before we do so, we probably want to note a few things. One is I've only defined the test average function here. I've defined it as having this test case here. But if I want to run it, I should still call this function probably down at the bottom of my file down here. I'll say, let's run test average. And one thing you might notice, if you're being particularly observant here, is that I'm calling the average function, but at least within this file here, testaverage.r, well, I don't see average defined. Well, what we don't want to do is this. I don't want to go over to average.r, copy and paste this, and put it over in testaverage.r. What I can do more simply is run source within this file. I could say source, and then the name of the file I want to run before I run the rest of the code now in this program here. I'm going to run now the code in average.r, which will give me access to this average function, and I can then later on call it in this file. So we're kind of, if you will, importing this function into this file here. We're not able to use any function we've defined in average.r in this new file, testaverage.r, because we've sourced it, we've run it before we run any code in this file here. So I think this is all we'll need to test our average function. Why don't I go ahead and run this test here? I'll go ahead and click on source to run this file now, and we'll see average passed the test. So it seems like, in this case, if I give my average function the input 1, 2, and 3, it will return to me the value 2. Well, what are some other test cases we could think of? Like ideally, we'd think through some representative cases that we should know how to handle, but also ones that kind of cover a broad range of scenarios. Here, I've been testing positive numbers, but it would be worthwhile to test if average can work with negative numbers too. So let's add a new test case. I might just kind of copy and paste this for now. I'll take my test case here and add a new one down below. And why don't I change now the input to the average function? I'll give it now some negative numbers. Some more representative examples here, -1, -2, -2, and -3. And what should I get back? Well, -2 is the average of -1, -2, and -3. That's what I should expect. Here I've tested now both positive and negative numbers, but it's probably worth testing 0 too, which is neither positive nor negative. I'm trying to think of scenarios that might go beyond the usual cases, but are still important for me to be able to handle appropriately. So why don't I make a new test case, one that involves 0. I'll go down here and add a new one. Maybe I'll do -1 and 0 to use that number, and then 1. So now we're going between negative and positive and neither negative or positive. And the average here should be, well, 0. So here I have 3 test cases in this one test function. First I'll test positive numbers. Then I'll test negative numbers. Then I'll test positive, negative, and neither positive nor negative numbers, hoping for the right output in each case. I'll still run my test average function down below. Let me clear my console, click on source, and now I'll see average seems to have passed all 3 tests. So my code seems to be doing pretty well here. But if we wanted to keep going and adding more test cases to this, I'd argue that we'd get pretty bored pretty quickly, and it would be a lot of copy paste. Like I've already written here 21 lines of code to test a function that was 10 lines of code. And if we wanted to test our programs and every time had to write 3, 4 times the amount of code to test that function, well, nobody would test their code. And we want people to test their code. So thankfully, people who are in the R community have developed their own package to allow us to make testing easier and arguably more fun. So a package that is canonical in the R community to test your programs is called test that. It allows you to test that your function behaves as you might expect. So let's go ahead and use test that now to improve the design of our tests and make it easier to write test cases like these. Now, test that comes with a function called test_that, which allows me to make a new test for my code. But before I can use it, I of course need to install test that. So if you haven't already, let me go down to your console now here and say install.packages and install test that. Once you've installed it, you then need to load it. So I'll go ahead and load test that just like this by doing library followed by test that. Now I'll go ahead and enter here, and I'll see that I've now loaded test that. I now have access to functions like test underscore that. So I think what I've written here so far, I mean, is pretty good. It at least has some good test cases, but I don't need any of this to use test that anymore. I'm going to go ahead and delete most of it, but still include now my average.r import, if you will. I'm taking whatever I've written in average.r and making myself able to use it now in test average.r. Now we said before that test that comes with a function called test underscore that. And we use this function to define a new test for some function that we have. So I'll go ahead and go back to test average.r, and I'll go ahead and use test underscore that. And the first input to test that is a description of the test I want to run. So here I'll say I want to test that. I want to test that, that average, let's say, the average function here calculates the mean, or in this case, the average of these numbers. So this is kind of an English sentence now. I'm going to test that average calculates mean. Well, the next argument is the set of test cases I want to run to ensure that average calculates the mean appropriately. By convention, I'll put these test cases inside of these curly braces as the second argument now, and I can now provide several test cases inside of this one function that I've decided to create here. Now, how could I say or express a test case? Well, test that comes with some functions we can use, and we really use them by expecting or saying what we expect to happen when our function returns us some value. One of these functions here is expect equal. We could expect that when our function is run, we should get back a return value that is equal to some other value, much like we just did with our conditionals earlier. But now I'll use expect equal. I'm going to go back now to my code, and inside of my, my test here, I'll go ahead and define a few test cases. The first one will be, I want to expect equality between the return value of the average function when given 1, 2, and 3 as input, and this value 2 on the right-hand side. So to be clear here, the first input to expect equal is the argument, the value we'll get back from, in this case, our average function. And the next argument is the value we expect to find as the return value of average. I'm going to expect those are now equal. And this is our test case. There are no conditionals, nothing else. We're going to go ahead and just use this to test, did average return to us 2 when we gave it as input a vector of 1, 2, and 3? Well, let's now add our other test cases. I could copy paste this and change the input. I'll do -1, -2, and -3 to test now for negative values. The expected value is -2 now. I'll do the same now, but for -1, 0, and 1, the expected value now is going to be 0. And why don't we go ahead and just add some more test cases? Because now it's just so easy for us. One thing I could do is test maybe more than an odd number of numbers. Like I've always been testing 3 here. Maybe I'll test 4 as another scenario. I'll go ahead and do, let's say, -2, -1, 1, and 2. So now we test both positive and negative numbers, but now we're giving an even number of numbers as input, and we should get back, of course, 0 in the end. So this then is our test of our average function. Let's go ahead and see what could happen here. Notice how at the top of RStudio, I now see a button called Run Tests. This means we're going to run every test we see in this file. I could alternatively, though, go down to the bottom of my console and just source this file to run it. I could say source test average.r, and let's see what kind of output we get. I'll go ahead and run this, and test passed. A little gold medal here to say our function worked as we intended it to. Here I can see that average will return to me all these values for each of these test cases, making it much easier now to write test cases like these, thanks to test that. Let me ask now, what questions do we have on defining these test cases and using a package like test that?
Do we have to source average.r? Because if we have a huge file and we only want to test one function, then it would be like a good idea to source the entire file.
A good question. So notice here how I actually ran source test average.r because my goal was to run these tests here top to bottom. Test average.r already sources or runs, if you will, average.r, giving me access to any functions inside of that file here. When we come back another time, next lecture, we'll see how to make packages of our code, and we'll see how to write tests that don't require us to put source up top. But so long as we're not writing packages and just testing our code, we're going to need to include source average.r up top to give us access to average so we can run it inside this test file here. What other questions do we have on test that or testing our code so far?
When is an appropriate time to write tests?
Yeah, when is it appropriate to write tests, and what time is appropriate to write tests? So there are, suffice to say, many varying philosophies on this. There is a kind of a movement or philosophy called test-driven development, which argues you should write tests before you even write your code. And by writing your tests, you kind of get your mind around what you want your code to do, and then you write code to pass those tests. On the other hand, folks might say, well, I just want to get something done. I'll write the code, and then I'll test it. There's arguments on both sides to be made. It's going to be up to you and your team to decide when you want to test and how you want to test. This is just telling us how we could test now using packages like test that. But good question on when to test as well. OK, so here we've written a pretty good test case, or many test cases here, for our average function. But there are still other scenarios to test. And in particular, we saw what could happen if we gave average some input that included NA values. Well, we could just as well test the result of average when it's given some NA values as we could some regular values like these. So let's go back now and add some new tests and test cases to our file here. Now, if I want to test what average does when it's given some input that includes NA values, well, I could keep adding test cases here to my single function, or my single test, average calculates mean. But if I were to keep going and adding more and more tests, like this function would become quite long. So ideally, what I want to do instead is maybe divide up my test cases into a way that makes logical sense. Here, I argue, I'm going to have all my test cases that are giving average some pretty typical inputs. Numbers, going to find the average of them and get it back and check for equality. But if I'm going to give average some new type of input, like inputs that include NAs, well, maybe I should make a new test for that. And I can do that by including more than one instance of this test that function. I could say I want to test that now. Average, let's say, how do I want to word this? I want to say test that average warns about NAs in input. So we saw before that our goal when we wrote the average function was to test and to make sure that it gave us a warning when the input x included NA values. So we could write some test cases to make sure that that is what is happening with our average function. So here's my description of this test. I'll go ahead and give myself some space now for test cases. And well, I want to test that average raises or throws a warning here. And it seems like expecting equality might not work, because this allows me to test two distinct values, but a warning is something else entirely. Well, thankfully, in test that, we have access to other expectations we can say, one including test warning, or expect warning in this case. We can say we want to expect a warning from this function, or expect no warning at all. So let me go over here and say I want to expect that I'll get a warning from the average function when I give it some input like this, maybe 1, NA, and 3. So some input that involves an NA. I could do the same thing down below, and I could say, why don't I give it maybe all NAs here, a vector of 3 NAs. And now I could expect that when I run average in this way, well, I expect I'll get a warning. So let's go ahead and rerun our tests now, testing for both a calculation of the mean and a warning from average. Let me go ahead and run this, and what do we see? Test failed. So let's see what happened here. If I scroll back up, I'll see that one test passed. That seems to be my first one here. Average still seems to calculate the mean. But if I look down below, my next test is that average warns about NAs in the input. And in fact, what I've gotten, it seems, from average is not a warning, but an error. Error in average. When I gave it NA, 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 x must be a numeric vector. So although I expected a warning on line 12, it seems like I got an error instead. So that's probably cause for me to go back to my code and see what could happen so I could fix it and make sure it adheres to these expectations of my function. Let me come back now to average.r and think through what could be going wrong here. Well, we got, it seems, this error that x must be a numeric vector, when we wanted, it seems, this warning down below. So maybe what happened is that when I gave it a vector of all NAs, maybe it found that that vector is not numeric, which it might well have done. So let me go ahead and go down my console here and test this. I could say is dot numeric and give as input NA, 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 and ask, is that numeric or not? So it's not. So because this vector of NAs is not numeric, I would first throw my error that x must be a numeric vector. But what I really want to do is return NA if I get a vector of NAs. So I think I should probably reorder here this handling of my errors. Let me go ahead and reorder this and put this up top first. So now what we'll do is first check, is NA, or is the vector we got as input to average here, does it include NA values? If so, we'll raise a warning and return NA, and then we'll check if it's numeric. I think this might help us solve our problem here. Let me go back to test average.r. Let me rerun these tests with our updated version of average.r, and we'll see all the tests passed. We have a little confetti, some rainbows. We seem to be moving along pretty well. So what questions do we have on this new version of our test? We've expected how average will calculate the mean, and we'll expect we'll get a warning now. What should we do next? And what questions do we have before we move on?
When the user get a warning, can we use pass to get the user to re-romp the input he have a warning in or an error?
So I'm hearing a question about handling these errors or warnings as they come up in our code. And it turns out that R actually has a function called try and a function called try catch. So let us handle errors and warnings as they arise in our code. We won't focus on those today, but certainly learn more about them if you're curious about them too. OK, let's keep going here and see what else we should test. So I argue that we've tested that average returns to us the right value to calculate the mean, that it also warns about NAs in input, but what else could we test? Well, it seems like we should also test that average actually returns to us NA if we give it an NA value. Here we're only expecting a warning, and we're not so much testing if we're getting back the right return value. So let me do just that. I'll go ahead and add a new test case, one that tests that average returns NA. I'll test that here. Average returns NA with NAs in our input, just like this. And I'll go ahead and add some more test cases. Well, here, it seems like expect equal might work for me. I'm going to test that the return value of average will be equal to an NA value. So I'll go ahead and expect equal. I'll go ahead and give the same kind of input I gave down below here, 1, NA, and 3. I'll expect that to be equal now to NA. And let me go down over here and say I expect equal between this vector of just all NA values and the NA value itself. Let me go ahead and actually make this a vector, just like that, and make this a vector as well. And now I'll be passing into average those same inputs down below, but now I'm testing to see if the return value is NA. I'll go back to my console now and run these tests that I've just added, and we'll see something a little bit curious. I'll see test passed, and I'll see test passed, but I'll see a warning, it seems, in my second test, that average returns NA with NA as an input. And I get back a warning that x contains one or more NA values. Well, that is kind of expected, because if we look at our average function, we'll see that if we do give our function NA values, we're going to throw this warning. But what we're testing in this test is not so much that we get a warning or not. We already did that down below. We're testing if the return value is equal to NA. So this would be a good chance for us to use a function like suppress warnings. We're saying we don't really care about the warning we get. We just want to test the return value in this case. So I'll wrap the average function, in this case, inside of suppress warning, suppress warning, suppress warning, sorry, let me make it plural up above. And now I think we should probably solve our problem here. I'll go ahead and rerun these tests, and now we'll see I have 3 tests passing overall. Well, what else could we test? We saw before in average.r that we also want to stop. We want to end our function, throw an error if we give it some non-numeric input. We could just as well test for that. I have this other set of functions, thanks to test that. One's called expect error and expect no error. Those test if my function has stopped given some given input. So I could use now expect error. Let me come back to test average and go down below and say, I'll test that. Maybe average stops if x, our input, is non-numeric, just like this. And now I'll go ahead and expect that I'll get back some error if I give as input to the average function some value that is not numeric. Maybe something like quack, just like this, or something like that test we saw before, 1 as a character, 2 as a character, and 3 as a character. So this is non-numeric input. Let's see if we get back the error from average. I'll go ahead and run. I'll first save my file. I'll then run test average, and now we'll see 4 tests passing 2. So here we've seen how to write test cases for our code thanks to expect warning, expect equal, and expect error. What other questions do we have on testing our code using these kinds of test cases, and test that more generally?
One thing which comes up very much in computer science is floating point inaccuracies, right? So can we account for that?
A really good question, actually an excellent segue to what I was just going to talk about now. So it seems like in our code, we are testing integer numbers. Like I have here 1, 2, and 3, and we get back a whole number, like 2. Same for all these other test cases. But to your point, we've missed an important kind of test case, which involves these floating point or decimal numbers. And due to what you've said about decimal numbers and the way they're represented, there are some special considerations to take into account before we can test those kinds of numbers. So let's see what we should take into account before we test, in this case, floating point or decimal values. So let's actually go ahead over here and think through how we could test it, at least hypothetically. I could use here expect equal still, and give now as input the average function, but I'll give it some floating point values. Maybe in this case, I will try to test these, 0.1 and 0.5, taking the average of this, which will be 0.3. Now, it seems to us as humans that if we were to do this kind of calculation, we would get the following kind of answer, that 0.1 plus 0.5 divided by 2 is equal to exactly 0.3. This is the average of these numbers, 0.1 and 0.5. But it turns out that computers can't do math exactly like this, that there are actually an infinite number of floating point numbers, of decimal numbers, and only a finite number of bits we can use to represent them, which leads to this problem known as floating point imprecision. We have so many decimal numbers to represent and only so few bits to represent them that we can't represent all of them precisely. And in fact, a computer, even one running R, might perform that same calculation and arrive at this. 0.1 plus 0.5 divided by 2 is equal to 0.299999, lots of 9s, then a lot of other values after that. So not exactly 0.3. And so because of this, we need to allow for some tolerance when we test our floating point values. But before we do that, let me kind of prove to you this is what's happening in R even. I'll come back to my computer here, and let's get an idea of this imprecision that happens in floating point values. I'll go back down to my console here, and if I were to print, let's say, this value, 0.3, I'll get back 0.3. But if I push R just a little bit, and I ask it, what really is 0.3? I could say print 0.3 and show me now 17 digits after the decimal point. Let's see what we get. 0.299999999. So it turns out that 0.3 is just one of those decimal numbers we can't properly represent due to having so many floating point values and so few bits to represent them. Now, because of this reality, like we said, we need to allow for something called tolerance when we're testing code like this. Now, tolerance is the range of values I will accept above or below my expected value as being equal to that expected value.
mathematically we could say this, maybe my expected value is 0.3, but in terms of numbers I'll accept as being equal to 0.3, I'll say any number between this range here, plus or minus, let's say, 1 times 10 to the negative 8th, some small number here. Now this number is our tolerance, and we can change it if we wanted to, too, depending on our needs for precision or how we're presenting these numbers here. I'm going to come back now to RStudio and show you that expect equal actually has a parameter called tolerance that we could use to change this value here. I'll come back over and let's look now at expect equal. If I clear my console and go here and say, in this particular test, I want to set some tolerance here. I could say, as another parameter, tolerance, and set it equal to some small value, let's say 1 times 10 to the negative 8th, which I represent now as with 1e negative 8 here. Now it turns out that test that gives you some default tolerance that's already been decided, so I'm actually going to rely on them to choose my tolerance for me here, but you could, if you wanted to, override it with this parameter called tolerance. So we've seen now this idea of floating point imprecision and this idea of tolerance, which we can use to better test our floating point values inside of our tests. Let me ask now what questions we have on either of these topics here.
Why writing code, spending much time to test another code, while you can go to the code that you wrote and just test it simply?
A really good question. So maybe you're in the habit of kind of just testing your code in the console, for instance, kind of like I did earlier. If I come back over here, maybe I wrote the average function and I decided, I'm pretty confident this will work. I'll, assign it to be the average here, and I'll just run a few test cases like average, C, 1, 2, 3 here. Okay, that seems to work. Maybe I'll do average and then maybe C, -1, -2, -3. That seems to work as well. Now, the reason you might not do this and instead spend more time to write your own test is simply just robustness of your tests. Notice I can very quickly test for a lot of different scenarios in my tests here and make sure that my function works as it expects. It's also very useful if you're collaborating with others. Let's say you're both somebody else and you are both writing the average function. Well, you could collectively decide on what tests you will run to make sure that the average function is correct. And if somebody later were to go into the average function and make a change, they could test to make sure that their change did not break the code altogether. So this is a good way to standardize what it means for your code to be correct as well. But a good question on why I would even spend time writing tests like these. Okay. So I think we've so far seen a lot of good tests for our code now. When we come back, we'll see how to test not just numbers like we did here, but also strings as well, and focus on these two philosophies, one called test-driven development and one called behavior-driven development. We'll see you all in a few. Well, we're back, and so we're going to next focus on testing these return values that will be strings, as well as focus on a few philosophies of testing, namely test-driven development and behavior-driven development. Now, what is test-driven development? Well, it is an answer to when and how we should write our tests. And central to this philosophy is that tests should be at the heart of your development process. In fact, it even argues you should probably be writing tests before you write the code. Now, let's consider here, I want to write a function that says hello to a user, one like greet. Well, to make that happen, I should probably first write the tests for that code and then write the code itself. So let's do just that now over in RStudio. And come back over here and create a file that will test this function called greet that doesn't yet exist. I'll do file.create, and then I'll say I want to create this file called testgreet.r. And I'll say it was created here. I'll go ahead and go to my File Explorer and open up testgreet.r, and now I could start defining some tests to test this code that doesn't even exist yet. But why would I do that? Well, by writing tests, I make it much clearer to me and to others what it is I want this code to do. And once I have in mind what I want the code to do, I'm better able to write that code itself. So the very first thing I probably want to test here is what that test the greet function, that it can say, let's say, hello to a user, just like this. That's the core part of this greet function I'm going to write, that it says hello to a user. And now I could define some test cases to make sure that this is the reality. Why don't I go ahead and define at least one, and I'll say I'm going to expect that if I were to run greet and give it as input Carter, I would get back as the return value now
hello, comma, space, Carter. So here is my very first test and test case for this function greet that doesn't yet exist. I'm going to say that I want to be able to use greet in a way that it passes in a user's name and returns to me then the user's name, but with a prefix of hello, comma, space. So that is our very first test. Let me go ahead and make sure I include this eventual file that I will create called greet.r, in which I'll define greet itself. And once I've done this, well, I could probably start developing. Let me go ahead and now go back to my file explorer, and I could either create a new file by hitting this plus button here, or I could go ahead and do file.create. I'll use greet.r, not hello.r, and then I'll go ahead and go to File Explorer here and open up greet, this blank canvas for me here. And now I could define my greet function to do exactly what I see it should do in my test. Well, I'll say I have this function here called greet, and I'll define it as a function that takes some input. Maybe in this case, the input is called to, because we're going to say hello to someone in this case. I'll go ahead and say that this function should return some value. And we've seen this function called paste before that concatenates strings. I bet that's what we might need here. I'll use paste, just like this, and I'll paste together hello, comma, and then whatever value is supplied as input to this function under the argument or parameter 2. And notice how paste here will take care of the space between the comma and whoever we're saying hello to. So now, thanks to my test, I have a very clear idea of what this code should do. And if I were to run this now, test greet.r, we'll see that the test passed. So it seems like now greet is working for me. I could go ahead and add more test cases. In fact, this is an iterative process. I might write some tests, write some code, write some tests, write some code. Here now, I could test other names. Maybe I'll say expect equal. I'll greet Mario and hope to see hello Mario. I'll do maybe Peach as well, and hello to Peach. I'm just choosing some representative names I might get now and pass into this greet function. Let's do Bowser as well. So now, with these expanded test cases, I'll go ahead and test my code again, and I'll see that it still seems to be working. And now if I were to modify greet in my greet.r file, I could very quickly test to make sure I didn't break it with any changes that I had made. So this is one philosophy of development, test-driven development. But there is a related philosophy that is so interesting to learn about, one called behavior-driven development. So test-driven development focuses on designing these test cases for our code, giving it representative cases and seeing if it actually follows through on the expected values. Behavior-driven development is slightly different in that it requires us to first define what it is we want our function to do and describe its behavior. Now, test that allows us to use behavior-driven development and actually gives us a few functions we can use that kind of operate a bit like an English language to define what it is our function's behavior should be. Let me show you what I mean. So I'll come back over here. And the two functions we have in test that to engage in behavior-driven development are these, describe and it, where describe is a way of describing what it is we want our function to do, and it is a way of saying that our function should do something in particular. So let's go ahead and switch now to this philosophy of testing. I'll avoid using test that, and now I'll start using describe. So in particular, describe lets me do something like this. I want to describe now my greet function. And by convention, stylistically, I'll include these empty curly braces here. And now I can say inside these curly braces what it is I want my function to do. Inside these curly braces, I'll describe what my function now should do using this it function. I could say that it, in this case, can say hello to a user. And as a second argument now to it, I'll provide some test cases that show examples of it saying hello to the user. Namely this. I could say maybe I have this object called name. I'll set it equal to Carter. And I'll expect that when I run greet and pass as input name, I should see hello Carter. Similar now to before. But notice what it is we've done. We've kind of used a bit of English language in the form of these functions. Here, I'm going to describe my greet function. Well, what should it do? It can say hello to a user. And here's an example of it doing just that. So pretty cool. Let me go ahead and now run test greet using this other philosophy here, test_greet.r, and I'll see that that test has passed. Well, what else could our function do? What kind of behavior do we want it to exhibit? Well, maybe I could also say that it, describing greet now, can say hello to the world, just like this. And now I'll provide an example of it saying hello to the world. I'll expect equal that when I run greet without any input at all, I'll say hello to the world. I'll get that back out as a return value now. So here we see a fuller version of a description of greet. First, it can say hello to a user, and it can say hello to the world. And by convention, I'm using this can say here because when we use it reads more like English to say it can do this, it can do that. So by convention here, we're just using these that grammar here, but I could use any kind of text inside this it function here. Let me go ahead and try to run this. I'll say source test_greet.r, and we get, seems like, if I scroll up now, that one of our tests has failed. So here we see error in greet. Greet can say hello to the world, but we can actually get back an error, and not in this case hello world. Error in greet, argument 2 is missing with no default. So let's look now at greet.r and see what could have happened here. I ran greet with no input, and if I go look at greet itself, well, now it kind of makes sense because I didn't supply a default value for 2 if none is supplied. So what should I do? Maybe supply a default value here. I can go ahead and say that 2 has a default value of world and fix this code after I have described it how it should work already. Let me go ahead and now rerun these tests with this updated version of greet, and we'll see that both of my tests have passed. That greet can say hello to a user, and it can say hello to the world. So we've seen now how to test these strings for equality, how to use test-driven development and behavior-driven development. So what questions do we have on test-driven development or behavior-driven development? Seeing none, so let's focus on one last topic for today, one called test coverage. Now the goal of today has been to help you write tests that systematically test your code. And one measure you can use to figure out how much of the code you're testing is one called test coverage. When you have programs that are composed of not just one function or two, but many, test coverage can tell you how many of those functions you've tested reliably. Now we've seen today how to spot errors in our programs, how to handle those errors, and how to write tests to test our code to ensure it behaves as we intend. When we come back, we'll go ahead and see how we can package our code up and share it with the world. We'll see you then. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Goddard Tan, and this is our lecture on packaging programs by which we can share them with the world. Now together, today we'll make a package called duckSay. And the goal of duckSay is to take as input some character string and output a textual representation of a duck saying that character string. So for instance, if I typed in hello world, I might see in my console now this duck saying hello to the world. Now, if you're familiar with CS50 or with programming more generally, you might have heard of a package or a program called cowsay. And cowsay is very similar in spirit. It takes some piece of text and outputs in your terminal a cow saying that text. Now, cowsay is not an R package, but we will take some inspiration from it to make our own package, one called duckSay. But to do so, we need to learn more about packages. And up until now, we've been users of packages. We have seen how to install, how to load, and how to use functions inside of packages. But what we haven't seen is the source code behind our packages. How are they made? Well, it turns out when you download a package from something like the CRAN, what you get is a single binary file. Thankfully, you yourself don't have to write binary to create a package. You can instead use what we'll call source code, the individual .r files and folders that compose your package.
And when it comes time to share your package with others, we'll take this source code and build it or compile it into some single file you can share around the world. But let's focus first on source code. I'll come back now to RStudio to make some source code for this package. And by convention, we write the source code for some package inside a folder that has that package's name. So if I want to make a package called duckse, I should first create a folder in my working directory called duckse. To do so, I can use this function here, dir.create, to create a directory, in this case called duckse. I'll hit enter here, and notice how in my file explorer, I see a new folder called duckse. Well, I want to make all my future files and folders inside of this folder here, my future package. So I'll set now my working directory to duckse. And now it's a bit equivalent to me going inside of this folder by clicking on it and seeing this blank slate in which we can begin writing the source code for our package. Now, this blank slate is a bit scary at first, but thankfully there's a structure to how packages are organized in R. Let's take a look at what a typical package might look like. So in general, for making a package in R, you will tend to have these files and folders here. One, first of all, called description in all caps, which describes your package. What is the name of it? What version number is it? Who wrote it? And so on. You'll also have a file called namespace, which you'll use to define the functions in your package some end user might be able to use. And then you have some folders here. One called man, which stands for manual. You'll put inside that folder the documentation for your functions, some instructions on how to use them. And here we have an R folder too. We'll actually place your .r files that have your function definitions inside of them. And of course, we'll need some tests to test our code, so we'll put those in this folder called tests. Now, if you're running a more advanced package, you might have other files and folders too, but these are the core ones that say this folder here is an R package. So let's begin. Let's begin with our description file and describe the package we want to create. I'll come back now to RStudio and create for this folder here a description file. I can do so with file.create, and I'll choose to make a description file in all caps with no file extension. Notice how now, inside my duckse folder, I have this file called description, which I can open up and see, well, another blank slate. And so it turns out here too, there are some conventions on how to organize our description file. In fact, our description file will be composed of individual fields that tell us some information about this package. But what are those fields? Well, the ones you need to know about, you need to include in your file, are these here. One called package, which is the name of our package as we want somebody to install it. We've seen install.packages, and we'll often include the name of the package we want to install as the input to that function. Well, this is the name we want the user to type in to install.packages to install our package. We also have to say the title of our package, which is a bit more English friendly. You could capitalize things, include spaces, and so on, but similar idea to the package field as well. We have here a description as well. What is the description of our package? What does it do? And so on. And a version number. What version is it? If we change over time, is version 1.0, 2.0, 3.0, or so on. And then finally here we have some information on the authors. Who wrote this package? What was their role? And then a license file. That is, what is the legal terms in which you can actually use the code if you want to install this package and use it yourself. So let's now add these fields to our description file and make it an R package. I'll come back now to RStudio, and let's go ahead and start by naming our package. Well, we said before, our package will be called duckse. So in the description file, I'll add this package field followed by a colon, and I'll say that our package is named, in this case, duckse. Just some English text here. Then I'll add the title, and I'll choose to maybe title case our package here. I'll call it duckse, just like this, and I'll give a description to it as well. I'll say the description of this package is going to be say hello with a duck. The purpose is to say hello with a duck. And this is the first version of the package. I'm just starting out on my journey of developing this package. But now I need to include some more information too, like who wrote this package and what are the legal terms in which we can actually use the package too. So to define who wrote the package, I could use this field called authors at R. And whereas up above, we've been using some English text, just regular old characters and so on, in this field, we can actually use an R function to define who wrote the package and what role they played.
Now to add a new author to this package, I use a function, one called person. And if I look at documentation, I would know that the first argument to this person function is the person's first name. So my first name is Carter, and the second argument is their last name. So in this case, my last name is Zenke. And there are a few other parameters as well that this person can have, namely an email. I could say my email here is carter@cs50.harvard.edu, and this lets people know if they want to contact the package author, they can email me at this email here. And then we should also specify what role each person played. So there's a parameter here called role as well. Now because package authors can play more than one role, role will take as input a vector of roles. And there are actually a defined set of roles, which you can learn if you look at the documentation here, but I'll focus on a few in particular. One role is an author of the package, somebody who contributed to it in full. And we denote somebody as an author by typing in AUT. This abbreviation here for author. So in this case, I'm saying that me, Carter Zenke, I'm an author of this package. Now there's more roles too. One role that is important as well is the creator of the package, which we note with CRE. This abbreviation for creator. Now creator and author seem pretty similar in meaning, but in R they have two distinct meanings. An author is anybody who at any time contributed to the package. A creator, though, is the person who now maintains the package. They're in charge of updating it, making sure it's up to date, and so on over time. So these two are distinct, and there has to be at least one creator of some package, a person who's maintaining it over time. So these are two main roles, but there's one more as well. I should also say that I am the copyright holder for this code. I own it, and I'm the person who owns the license that I will then specify underneath myself here. So these three roles, author, creator, and copyright holder, are the ones you'll need to create a package in R. But now let's think through the license field, license down below. Well, if you're a lawyer, you could maybe write your own license, but in general, it's best practice to rely on some standardized license that already exists. And in fact, if you want to share your code for free online, for others to use freely as well, there's a whole community that has created various licenses, one called the Free and Open Source Software Community. This community has created several licenses that you can just use and adopt or adapt to share your software online for free. Among the typical licenses are these, the MIT license, developed by our friends down the road, and the GNU General Public License, similar in spirit to the MIT license as well. Now the MIT license begins as follows. Permission is hereby granted, free of charge, to any person obtaining a copy of this software, basically to deal in the software without restriction. So saying you can share this code freely and you can use it freely as well. So I might want to adopt this license for my software here. And I'll go ahead and say that in my description file as well. I'll come back over here to RStudio and say, I want to build on top of the MIT license. I want to license my software under this language here. So I could simply type in MIT as the template for my license now. But it turns out that in R, there's a bit more we need to specify here. I should also specify the year in which I created this software and who the copyright holder is inside the license itself. This is particularly to the MIT license as well. So if I want to add on to this MIT license, I can take MIT as my template, but then add on some other file that gives some more information about this license. I could say MIT plus file and then license in all caps. And this is convention. If I want to add on to my license, I do so with a file called license in all caps. And now this says the entire license for my software is the MIT license as the base, plus some file that I'll include called license. Well, let's create it now. I'll go down to my console here and say file.create. I'll create a file called license, no extension here, open it up, and now add in some placeholders that I should fill. For the MIT license in particular, I need to say again what year it was that I created this software. So I'll say year in all caps and the year I created this software, and then the copyright holder as well. In this case, I'll say just the duck say authors, referencing again this authors field in my description file. So now we have the basic bare bones structure for our package called duck-say. We have a description, a license, authorship, and so on. Let me ask, what questions do we have so far on packages in R and creating those of our very own?
Which are the best practices to enumerate the version number? And when do we choose when to increment the number to the left of the point and the one to the right of the point?
So a good question about version numbering. I want to change the version number that we're using. Let me show you what we're doing now and show you another process called semantic versioning too. I'll come back over here, and here I'm using just 1.0 for simplicity, but actually it turns out some in the R community use a convention known as semantic versioning, and that versioning system actually allows for 3 numbers here. Now by convention, each of these numbers has some certain meaning. In this case, this last number is known as the patch version. If you make some bug fix, you would increment this number here. This middle number is known as the minor version. If you add in some new feature, like a new function, for instance, you would increment that number too. But it turns out that this first number, like 1 here, is known as the major version. You would only increment this if you made some change that broke the conventions you prior used in your package. And somebody who's relying on your package would actually have to update their code too to still use your package. So this is one set of conventions for versioning here. We'll go back though and use 1.0 just for simplicity. OK. So we have here now our basic bare bones R package, but our goal is to also add some source code. And we can do it in the same way we've usually written source code before, by first writing some tests, writing our code, and writing documentation for our code. Now we saw before, if I want to test inside of my package, I want to run some unit tests as well, I should write them inside of this folder called tests. And we could certainly create this folder ourselves, but as we get into the weeds of structuring our package, we might want some help. So thankfully, there is a package that helps you write packages in R, one called dev-tools. This package helps us, give us some tools to write our very own package, and among the functions it has for unit testing are these. One called use-test-that. So we saw test that last time. It's a package for unit testing our software. If I want to use the test that package to test my code, all I have to do is use test that. And then, once I've done that, if I want to create some testing file for a function, I could simply use test. And that will create for me a new testing file for my function. And then finally, once I have all those tests written, if I want to run those tests, all I have to do is run the test function as well. So very helpful for us for structuring our package and running our unit tests too. So let's begin by writing some unit tests for our duck-say function. I'll come back now to RStudio, and let's try to use test that. Well, because this function is part of the dev-tools package, I'll first need to load, if not install, the dev-tools package. So here down below, I'll use library dev-tools to load the dev-tools package, assuming it is installed. I'll hit enter here. And now let's use test that to configure our package to run tests with the package test that. Well, I'll use down below here, use test that, and I'll hit enter, and we'll see a few things have happened actually that I'll see in my console down below. Now the first thing I see is that my descriptor file has been added to. I see now this new field called suggests, and as part of suggests, I now see test that. This means when somebody installs our package, it will be suggested that they also install test that at a version greater than or equal to 3.0. Well, why would we suggest test that? Well, maybe the user wants to test our code themselves, in which case they'll need to use test that because we used it ourselves as well. If you want somebody, though, to not just suggest some code or actually be suggested to use your code, you could also make it required they install some other package as well. So I can make a field called requires, like this, and list any packages I want to require the user to install to use my own package. Now the user here likely won't be testing our software for us, so only suggest it, not require it. But if you do want to require some code, some package, you can actually use requires as a field in your description file as well. I also see here config/test that/addition. This just means that when our tests are run, we'll be sure to use the version 3 of test that. But a few other things have happened as well. If I look down below my console here, I'll see it's created some new folders for me, namely one called tests over here. If I click on tests, I'll see a new file, testthat.r, and a folder also called testthat. If I open up testthat.r, this is a file that was automatically created for me, and it includes some configuration for testthat as I run my tests inside of this package. We'll leave this alone for now. But notice how I also have a folder called testthat, and it's inside this folder that I will actually write my unit tests themselves, similar to what we saw last time.
Now that this structure has been set up, I actually write my tests now and see what's suggesting that I use test to create my very first unit test for my function. Well, here I want to use test, and I want to create a test for, in this case, a function called duckSay. So I'll enter as input to use test the function's name, duckSay, just like that. I'll hit enter now, and I'll see a few things happen again. One, I now have this new file called test-ducksay.r, which is inside my test.that folder, which itself is inside my tests folder. And now I can modify test-ducksay.r. It's given me here some basic structure for my test file, but I don't want to use this so far. I'll just remove it. And now I want to think about how I could describe ducksay. What do I want it to do in this testing file? Well, we saw last time we could use some code a bit like this to describe how I want ducksay to run. I could say describe and then use ducksay here to say I'm going to describe how I want ducksay to run. Well, what do I want it to do? I think the first thing I want it to do is to work with cat. So I could say it can print to the console with cat. And now I'll include some tests to see if ducksay can print with cat. And what I mean by this is as follows. If I use cat here and gave as input ducksay, I should see the output of ducksay in the console. Ducksay will simply return to me some character string, but cat will take care of outputting it to the console. Now, how could I make this a test? I have the code I want to have run, but I want to test that it's doing what I want it to do. Well, it turns out that similar to expect equals, which we saw last time, there is a function called expect output that can expect when I run this code, I get output in my console. So I'll use this function expect output, part of test that, to say I expect that when I run this code, cat with ducksay, I'll see some output in my console, anything at all. And that seems to be our first description now for ducksay. But I think we could still do a little better, get more specific if we will. So here we could say it prints the console with cat, but what should it print? Well, it should print hello world at least. So I'll go ahead and say it can say hello to the world. That's another feature now of ducksay. And I'll say that, well, when I want ducksay to run, I expect to see hello world in the output. And we saw last time one called expect equal with ducksay here. And I could say, I expect that ducksay will return to me a string that is equal to hello world, but I argue this might not work as I intend it to. Because if we look at our output here, here's our intended output of ducksay. Why might it not work if we were to say, I expect this output to be equal to hello world? Well, it seems like this is not strictly equal to hello world. I have hello world and then some duck at the end. So what I would rather do is ask a different question. Is hello world somewhere in this output we've gotten back? Not is it equal to hello world, but is hello world somewhere inside of it? Now, thankfully, there is another function besides expect equal, one called expect match. I can expect to find a match of hello world inside this output of ducksay. Let me come back and try it out. I'll come back over here, and I can use expect match like this. I'll say expect match now between the return value of ducksay and this character string hello world, and that will treat this as a pattern, hello, comma, space, world. And if it finds that pattern inside the return value of ducksay, well, this will be true, no errors at all. If I can't find that pattern, though, in ducksay, we'll raise an error, and our tests will fail. So again, expect match is good for trying to find this pattern, hello world, inside the output of ducksay right here. So I think these tests are in pretty good shape. I now know exactly what I want ducksay to do. It should work with cat, and it should print out some output that says hello to the world. But now that we have our tests, we need to write our actual code. We need to write the function ducksay itself, and for that we saw we could use this folder called R. In general, when we're working with packages, we're going to write all of our .r files inside of a folder called R. But again, rather than structuring this ourselves, we could rely on DevTools to do it for us. I could use a function in DevTools called use_r and pass in the function name I hope to create, and then I'll get a .r file to write my function definition in. So let's try this now that we've written our unit tests. I'll come back now to RStudio, and let's see if I can use R to create for me the function duckSay and the file I should define it in. I'll go to my console now and use R. And then go back up in my File Explorer to duckSay as the folder here. And I'll try to create now this file to define duckSay in. I'll say I want to create this new function duckSay and the R file for it. I'll hit enter now and see a few things happening. One, I see I have a folder called R, brand new thanks to use R, and I also see I have a new file, ducksay.r, which has been created inside of this R folder to keep things organized in this case. I can close my description here and let me save it first, and then I'll go ahead and remove test ducksay here and focus now on ducksay.r. Well, how should I write ducksay? If I look at my output here I have my intended output. I notice that I really have 3 lines of output I hope to return from this function. I have hello, comma, space, world, the top half of my duck, and the bottom half of my duck. And these are all character strings. So let me actually ask our group here, what function we've seen so far do you think could help us combine these strings? If I want to have 3 different lines here, hello world, top of my duck, bottom of my duck, what function could I use to combine these strings and perhaps return them from my ducksay function?
Maybe the paste function?
Yeah, maybe paste. So we saw before that paste is good for combining different strings, and we can actually use paste here, but instead of separating now with spaces, we could separate with new lines, our \n escape character. So let's try that out. I'll come back now to my file, and let's define for ourselves the ducksay function using paste. I'll say here, I want to make a new function called ducksay that currently doesn't take any input at all, but inside of this function, I will return the result of calling paste on 3 different strings. The first one will be my first string here, one called hello world at the very top of my output. And then the very beginning of my duck here. I could give it a little beak, some eyes, and now the top of its body here. And then underneath, I could use the bottom of the duck, which will look a bit like this. Some underscores and then a /. And now, I think we have what looks to be our intended output, thanks to paste. But as we said before, paste's default is to combine these strings using a space. And we want a new line instead. So I should change now the sep parameter to paste, as we've seen before, from a space to a \n, this new line character that says I want to separate each of these character strings by a new line, effectively hitting enter each time on my keyboard. So I'll save now this function, and when ducksay runs, it should now return to me this output. But I've defined ducksay here, and I want to use it. It turns out I can't do that just yet. We saw earlier this idea of a namespace file, which tells us which functions in our package an end user can use. And so now we've defined our ducksay function, we should actually include it in our package's namespace, the list of functions that an end user could use in our package. So let me now create this file called namespace. I'll say file.create namespace down below, and I can then see in my folder called ducksay a new file called namespace. I'll open this one up, and what should I include in namespace? Well, by convention, we have a function here called export. Export says take a function that I've defined and make it available to the end user who installs this package. In this case, I'll export the ducksay function just like this. So to be clear, I've now defined my ducksay function inside a file called ducksay.r, which itself is inside an R folder to keep things organized. And then, once I've defined it, I want to make it available to a user, which I'll do through the namespace file and say I want the ducksay function in particular to be available to our end users here. Now, once I do that, I can make use of another DevTools function, one called load_all. Load_all. That says whatever functions I have exported from my package, like ducksay here, I want you to load them so I can use them right here in my console. I'll go ahead and load all, and I'll see this is loading the duckse package now. What I can do now is use duckse in my console. I could say I want to cat the result of calling duckse, just like this. And let's see what we get. Fingers crossed. We get a cute duck saying hello to the world. And now we could test our code more thoroughly too. I could run test as well in my console, and now I'll run those tests I created. Let me open up inside my tests and test that folder here. Here were those tests. If I now run test the function, thanks to DevTools, I'll be able to run all the tests I defined in this file. There's one more thing here too. Last time we used source at the top of our file to give this file access to a function like duckse in duckse.r. But now that we've used load all and exported this function from our package, we can simply load all and then run the tests, and they will have access to that function called duckse. No more using source so long as we're inside a package that we've exported our functions from. OK, so we've seen now how to define unit tests for our package, how to write code that adheres to those tests. Let me ask, what questions do we have on what we've seen so far? Either on testing our code, writing our functions, or defining our package more generally.
When you run the test program on the terminal, what's the meaning of the colored letters FWS?
Good question. So if I look over here in the console, I'll see some pretty output, let's say, from test that. And let me walk through it step by step here. So here I see testing duckse. That is the function we are testing, right? I'll also see F, W, S, and OK. Now these are different kinds of results we can get from our tests here. It seems like F corresponds to fail down below. Fail, we didn't pass this particular test. W stands for a warning. We saw last time how our tests can sometimes raise warnings. Well, this would be the number of tests that gave me a warning in this case. S stands for skip. It turns out you can skip tests if you want to. And then OK means this test passed with flying colors. So here I see these two tests, they both passed, and I'll see a 2 in the OK and a 2 total that are passing down below. If I had more than one function to test, I might see more than one of these and see the total number of ones that were passed, skipped, warned about, or failed overall down at the bottom of this results here as well. So I hope that helps clarify what exactly we're seeing as a result of using test. But great question there. OK, so I think we're in a pretty good place, but there's arguably one more thing to consider now. So I've seen that my code can both print to the console with cat, and it includes hello world in the output, but an important thing here too is, does it include a duck? So let's see that as well. I'll come back now to RStudio and update these tests now. Let me add a new one, a new test that says duckse, it can say hello with a duck, just like this. And I think I could probably use a very similar structure to what I used before with expect match. In this case, though, I could expect a match between the output of duckse and the duck that I have to show to the user. So I could use expect match, like I did before, and then enter duckse, just like this. And now I want to expect a match between my duck pattern and whatever I see in the return value of duckse. But I'll probably need a new object for this duck. I don't want to type in the whole duck as an argument here. I could go up above here and define myself a new duck, similar to how we did it before. I'll paste together the top half of this duck with a cute little beak and a top here, and then the bottom half of my duck, 1, 2, 3, 4 underscores, and then a forward slash. And that is my duck, so long as I separate each with a \n, just like that. And now I think what I could do is expect a match between the return value of duckse and this duck I've created over here. Now this, you think, might work. But I'd argue there's one more thing to consider here, which is, I told you earlier, expect match will take the pattern we've defined here and look for it in the return value of duckse. In this case, this is our pattern. Well, these patterns are more formally called regular expressions. And I won't get into them today, but in general, one thing to know about them is that these characters, parenthesis and a dot, have a special meaning inside of regular expressions. They don't actually mean literally a parenthesis or a dot. They mean something else entirely. So if I want to treat this pattern not as this thing called a regular expression, but exactly as I see it here, I need to set the other parameter equal to true instead, one called fixed. Fixed says, I want you to treat these characters here not as part of some regular expression, but instead exactly as we see them here, a greater than sign, a parenthesis, and a dot, or a period. So more on those another time, but for now, let's just say I want to look for exactly this pattern inside the output of duck-say. I'll leave this as is now, and I'll go down below and run my tests with test again, and now we'll see all 3 tests are passing. None are failing, none giving us warnings, none have been skipped. All, in this case, have passed. So we've fixed our tests. We've written our code. One next step is to document how to use our function. Maybe a user is new to our package. They don't know what to do. We want to give them some guidance on how to use our functions. In fact, you've probably seen to access documentation you can use question mark followed by the name of some function. And right now, if I use question mark duck-say, well, I don't see anything. There's no documentation for duck-say. Well, let's go ahead and fix that. Thankfully, I can define my own documentation for duck-say by putting it inside of this folder we saw earlier, one called man, where man stands for manual. But what will go inside this man folder? It turns out a variety of files all ending with .rd, where .rd stands for our documentation. In fact, inside these files, we'll write not just plain text, but we'll actually write something called a markup language. Now, a markup language is not a programming language. There are no functions and loops and so on. It's instead a language for formatting some text. Now, for instance, R's markup language looks a bit like this. I can give each of my documentation files some particular parameters, like title, description, and usage here. Here, title says, what is the title of my documentation? Description says, describe this function for me. And usage says, how should I use this function too? There are other commands we'll see here, but our .rd files will look a lot like this, and we'll then render them or convert them to those same files you're used to seeing when you use the question mark down in your console. So let's try this out now. I'll come back to RStudio and try to make some documentation for duck-say. Well, I want to probably first create for myself that man folder to put my documentation inside of. So I could use that same function we saw earlier, dir.create. And I'll create for myself the folder called man, short for manual. And it's inside of this folder that I will store all of my .rd files. I'll say file.create now, man/ducksay.rd. And this is convention. I'm putting this file, ducksay.rd, inside the man folder, and I'm calling it, giving it the same name as the function it should document. So this file, ducksay.rd, should document the same function, ducksay. I'll go ahead now and create this file, and if I open now my man folder, I should see ducksay.rd right there inside. I'll open it up, and what do I see? Well, nothing yet. But I'd argue we could go ahead and use R's markup language to create some documentation now for duck-say. Now, I've read the documentation for creating documentation in R, and there are several different keywords you can use to create your documentation. Among the most important ones are these here. One is /name, and inside these curly braces here will include the name of our function we're trying to document. In this case, duck-say in particular. This is the name of the function we're trying to document. The next one, most important one, is going to be /alias. /alias is what you want the user to type in their console to see your documentation. For instance, if I go down my console now and I use question mark duck-say, well, my alias is duck-say, literally this right here. If any user were to go to their console and use question mark duck-say, they could see this documentation that I have now created for them, as long as they've installed my package. So I'll say my alias is similarly duck-say as well. And now here comes our title. What is the title of this function? Kind of in more English characterization, like capitals and spaces and so on. We'll call this function duck-say, just like this, and provide a description. I'll say that this is a duck that says hello. And just like that, with these 4 lines of markup language, we can actually already see it being rendered or converted into our documentation file. If I go down my console now and run question mark duck-say, I'll see my very first R documentation file. Notice how here, the name of this function is actually included in my documentation right up here. The alias is also included, what I used down here. I said !duckse and got this documentation file. The title is there too, /title duckse. We see that right here, and so too is the description, a duck that says hello. So we could keep adding to this documentation using this same syntax here. There are other kinds of components we can add to our documentation file as well. In fact, let's go ahead and add a few more. Let's add one called usage, which tells people how to use our function. I'll use /usage here, and this will say how I want users to use it, in fact. So I'll say duckse here. And by convention, in usage, we include the function's name, some parentheses, and if there are any parameters, we include those in the function's parentheses as well. But currently, there are no parameters. I'll also include a section called value, which is the return value of this function. What does it return to us? Well, it returns to us really a string representation of a duck saying hello to the world. And then finally, we can also include some examples of how to use this function, in case people are unfamiliar. I could say examples here and provide some examples of how people could use duckse. Maybe I want them to use it with cat, so I'll show them, look, you can use duckse like this. Take cat and pass as input duckse, just like that. And now, with these other pieces of syntax here, I can say !duckse and see the new, whoops, let me save this file first, and then run !duckse, and I should see the now rendered version of what I'm seeing on the left-hand side over here. Notice how we have some new pieces. I see usage now, I see value, and I see some examples as well down below in my documentation file. So we've seen now how to document our functions using these markup language here. What questions do we have on how to document our code and how to render it in our console? OK, seeing none, let's keep going then. And I think we're now in a pretty good spot. So we now have the ability to write our own functions, to test them, and to write documentation for those functions. So what should we do now? Well, ideally, we want to package it up and share it with the world. And in fact, this process of taking what we have as source code and converting it into a single file has a particular name. This name is called building our package. Building our package, taking it from source code into a single file we could share around the world. Now, there are a few options for building our source code into that single file. Among them are these. Build, which is a DevTools function that takes our source code and gives us some single file at the end. But build, it turns out, is actually a wrapper on top of a base R command called rcmd build. They have the same purpose. rcmd build, though, works in your actual computer's terminal, not in the R console. So we'll instead use build to keep ourselves inside the R console and build our package into a single file. So we'll still rely on DevTools now and use their build function in particular. Let me come back now to RStudio and show you how this exactly works. So notice here how I'm inside of my duckse folder, my duckse package now, if you will. Let me go ahead and close my previous files here. And let me run this command called build, thanks to DevTools. If I run build, I'll see some output here, and I'll see down below the file I have gotten from building this source code into a single file I can share with others. I see it's called duckse 1.0.tar.gz. And if I move up one level in my folder structure, I'll see this file actually right next to the duckse folder, duckse 1.0.tar.gz. And this is a funky kind of file name, but this stands for essentially a zip file, if you will. It's very similar in spirit. It's also called a tarball sometimes. So this is basically a single file in which we can share our code, email it to somebody, post it online, etc. This is all that source code in our folder now in one single file. So we've done pretty well so far. But before I share this, I think I've forgotten kind of one important thing, which is the duck actually only says hello world right now. It doesn't take as input any given kind of string. So we probably want to update our code and rebuild this package again and again. And in fact, you'll find a package building process often iterative. You build it, you add something new, you build it again, add something new, build it again, and so on and so forth. So let's go ahead and update our package and rebuild our code. Let's come back now over here and consider how we could make this duck say any given phrase that we have. Well, I'll go back to my duck-say source code inside my folder here. I'll go back to my tests folder, open up now my tests for duck-say, and let me add one more description for each of these for this function here. I'll come down below and I'll say I want to make sure that this can say hello, or can say any given phrase rather. Duck-say can say any given phrase. And now, to exemplify this, I want to include this test here. I expect a match between running, let's say, duck-say with a given phrase like quack, like that, and I expect to find quack anywhere inside of that given return value, just like this. So now again, I'm saying that duck-say should be able to say any given phrase. If I run it with duck-say and pass as input quack, I should see quack inside of that return value. So it's a good test, but I need to implement it now in code. I'll come back now to my duck-say.r file, going back to my main folder, inside R, where we store our R files, open now duck-say.r, and I'll see my function definition. Well, I could do this. I could say duck-say now takes as input a given phrase, just like that. And I'll make sure that instead of hello world, we say that given phrase. But now, per my tests, I still want to run duck-say, or be able to run duck-say like this, without any arguments whatsoever. And I still expect to see hello world when duck-say is run without any arguments here. So I could go back to duck-say now and say that phrase has a default value of hello world, just like this. If I supply a value, well, I'll see the phrase there, hopefully. And if I don't supply a value, well, I'll hopefully see hello world there instead. So let me test my code interactively now. I've updated my function here, so I should again run load all. I'm going to update my function after I've redefined it here and make it available to myself in my console. I now have access to the latest version of duck-say. I can run cat duck-say and then give as input quack, and hopefully we'll see quack on top of our duck. So it seems to be working just right now. Let me go ahead and run test and see what I can see. I'll see that all 4 of my tests are passing. So I've updated my tests, my source code. What else should I update? Well, my documentation. I'll go back now to my duck-say package folder, open up man, open up duck-say.rd, and now update my documentation. I'll then say now that the return value of duck-say is no longer a duck saying hello to the world. It's really a duck saying the given phrase. And similarly, I should probably update now my usage. By convention, we include the function's name, remember, some parentheses, remember, and also the parameters to this function. So one parameter now is this one called phrase, and I've given a default value of hello world. So this is, by convention, how I would write that out in my documentation. I would give the parameter and its default value with an equal sign separating them. And then finally, down below my examples here, I could give one more example of using duck-say. Underneath this here, I could say you can also, if you want to, give duck-say some input, like quack, just like that. So this, I think, covers us in terms of our function itself, our tests, and our documentation. I can test my documentation by re-rendering it, $duck-say, and now I'll see it on the right-hand side. I will, in fact, see my updated usage, my updated value, and my updated examples down below. So I think we're in a pretty good spot. Let me now rebuild this code. I'll simply use build again, just like this, and now I should see my updated version of my package now in a single file. And to be clear, if I wanted to share this code with somebody else, I would need to rebuild it every time I modify it to put all those updates inside of duck-say, this folder, into this new file, duck-say 1.0.tar.gz. Okay, let me ask, what questions do we have on iteratively updating and now rebuilding our package over time?
Is there a command in R which rebuilds the package for us as soon as the file changes?
A good question. So there's a command in R that rebuilds the package for us as we change it. Not that I am aware of. So I'm familiar with dev tools in particular, and I don't think there's a function that lets you do exactly that. I know in other languages there can be functions like that, but not that I'm familiar with in R. A good question, though. Okay, let's keep going then. And so we've rebuilt our package. We now have it as a single file. I think what's left to do now is to really use our package. So let's see if we can create ourselves a new program that uses exactly this package. Maybe I will make a program called greet.r that will, instead of giving a user just a plain old simple hello, give them a hello from a duck. So I will move my working directory up one level, go out of my duck.say folder. I'll use set wd and then in quotes here, ... That means move me one level higher in my working directory. So I'm presently in duck.say, but now I'll be right next to duck.say, if you will, in the same view I have on the right-hand side here. I'll now create for myself a new program called greet.r, just like this, and I'll see greet.r show up over here. I'll open it, and now let's write this program together. Well, now that I have my very own package, one called duck.say, I could use library to load my function duck.say. I could use library here and say I want to load this library called, or load this package called duck.say. And once I've done that, what do I want to do? I want to ask now the user for their name. So I could use, let's say, something like readline. I could say I want to ask the user for their name. I could use name and then store inside readline, just like that, and ask what's your name. Readline, as you've seen before, will take their input and return it to us, storing it in this object called name. Then I could create a greeting for them. I could say, maybe let's have a greeting here. But the greeting will actually be the result of calling our function duck.say, which is inside this package called duck.say. I'll use duck.say here and pass as input, in this case, well, the combination of hello and then, let's say, the user's name. And now, down below, I could use cat, of course, to print our greeting. So top to bottom, I'm loading this package we created called duck.say. I'm asking the user for their name. I'm then using the function we defined as part of duck.say, called duck.say as well. I'm going to pass in the concatenated version of hello and their name, and then I'm going to print the result of calling duck.say here. But before I can do this, I have built my package, but what I haven't done is installed it. So I've built it. I could share this file with others, but I still need to install it on my own computer. And if anybody wants to use this package as well, they need to install it on their computer too. So thankfully, there are tools we can use to install packages in R. We've seen one already, one called install.packages. In fact, you can use install.packages to install packages, not just from the CRAN, but also from an individual file, like the one we have here. You could also use a base R function called rcmd install. You can use that in your terminal, but we'll stick now to using install.packages because that keeps us inside the R console itself. So let's now install our package with install.packages. I'll come back now to RStudio, and I think I could use this single file I now have, the compiled version of my package, and I can install it now with install.packages. I'll say install.packages. And I'll now use the file name itself, duck.say 1.0.tar.gz, this tarball, this kind of like a zip file I can use to store my package contents. I'll install this here. And now that it's installed, I see done. I can now run source in greet and type in Carter. Voila, I now have a duck that can say hello to anyone who enters in their name, thanks to this package I made called duck.say. Well, we've seen now how to build our packages, how to install them, and how to use them. Now the only thing left to do is to share them with the world. So if you want to share your package with the world, you have a number of options. You could use the CRAN, so long as your package adheres to their guidelines. You could use a service like GitHub, which is a tool for sharing software and collaborating with others. You could even share your package over email with a friend. Now, however you choose to share your code, I hope you keep in mind just how much you've learned over the course of this course and how much you have to share with the world. In fact, you began by learning how to represent data using vectors and data frames. You graduated to transforming data using subsets, conditions, and logical expressions. You then saw how to make your analyses more efficient by using loops and functions and dipping your toes into this paradigm called functional programming. And in the second half of the course, you saw packages like the tidyverse and all they could do, how they could tidy your data, help you visualize it, and help you test your programs too. All that's left now is to take all you've learned, package it up, and share it now with the world. We're so excited to see what you'll create. This was CS50’s Introduction to Programming with R.